Welcome, everybody, to the second North American Hail Workshop. Our first one, as you probably know, it was in 2018, and there have been 3 European Hail Workshops, one in 2014, one in 2017, and one 2021. But before that, for about 40 years, it was just a dearth of work on hail, even though hail became a more significant, financially significant problem. So there's this renewed interest. A lot of it comes from modeling capabilities, new observational tools, and the desire to really provide early warning for impending hailstorms. And so in today's talk, and I want to thank my 2 co-organizers, Becky Adams-Celine and Ian Giamanco. And then we have a number of members on the steering committee who are here: John Allen, Victor, Ted, Menzel, Katharina, and I probably missed one, but that's okay. And so we have a fairly tight schedule. And so we'll limit each talk to 15 minutes and 5 minutes for discussion. And then, of course, offline, there'll be good opportunities to talk. So in any event, hope everything goes well, and thanks for coming and attending. Thanks for attending.
All right, thank you. We'll go ahead and start our first session just a touch early here because, you know, we always run overtime despite our best efforts. But yeah, could our early career panelists come up? This will be a new view looking at hail through the lens of an early career scientist. All right, thank you. All right, so we have here Brenna Meisensaal from IBHS. She's a research project scientist. Bryn Roberts, Lord Ronalds, I'm sorry, from Zesty AI, and she is a data scientist. Cameron Nixon from Central Michigan University. He is a grad student working with John Allen. And Yuju Lin from Penn State University. She's a grad student working with Matt Kumjian. And I believe they've each prepared a short introduction. So if we could pull up their slides.
So right now I'm working on adding more realistic features to hail model, basically, because recently a lot of hail models in use assume hailstones are smooth and spherical, which is clearly not realistic. So the current work I'm doing is trying to add the non-sphericity and rough features to a hailstone. And in this, we can also add hailstone tumbling, which will affect our collection kernel and feedback to our hailstone mass. The aspect ratio and roughness will apparently influence the hailstone heat transfer coefficient, diffusion, all that. It will all feedback to hailstone mass. So right now, this is kind of what I'm working on based on the detailed explicit hail growth model by Comger and Lombardo 2020. Oh, I didn't introduce myself. I'm usually from Penn State University. I'm a PhD student working with Matt. Should I say more?
That's okay for now. Thank you.
Okay.
All right, and I think, Brenna, you're next.
Hello, I'm Brenna Meisensaal. I work at the Insurance Institute for Business and Home Safety. And this isn't just my project, but this is kind of encompasses what our company does in general with hail. So one of the main things is we go out into the field and collect hailstone data with our disdrometers, and we take that data back into our lab and get the realistic density of hailstones for different sizes, and we use that data to create our own hailstones and use them to impact shingles because we focus on building components. So we use them to impact shingles and try to understand damage for homeowners and insurance companies, and kind of a little glimpse. One of the projects I'll be talking about is a high concentration of hail project that I will be presenting on Thursday, understanding smaller stone impacts, so 1 inch and below. And then we are trying to develop this new algorithm that analyzes the images of shingles to understand the amount of granular loss, and then dents and ridges, trying to understand that damage in a numerical form.
All right, thank you. Okay, Cameron?
Yeah, well, hey guys, I'm Cameron Nixon. I work with Dr. John Allen over at Central Michigan University. And I figured to, I guess, introduce myself and my work. I just write a simple little philosophy that I've kind of held here, that forecast parameters hold skill, but not secrets. And, you know, because I'm biased, the hodograph holds those. And I'm a very wind shear oriented person. And so today, or for my talk, at least by the end of the week, you'll hear a lot of hodograph related things and how to predict generally the likelihood of hail given a certain shear profile and shear structure, and then how that relates to the thermodynamics.
All right, thank you. And now Bryn.
Hi, I'm Bryn. I totally forgot to make a slide. So I got my PhD in atmospheric, mainly climate science at Colorado State University. And now I'm working as a data science specializing in risk modeling at Zesty AI. And essentially what I'm looking into, we started off just trying to figure out a way that we can predict which homes are going to make a hail claim and how big that claim size is going to be. And along the way, we're starting to look into aspects of hail climatology that haven't been looked at. Brenna already touched on one, but the impact of high frequency small hailstones. And does that matter? We often use like a 1 inch or 2 inch threshold when talking about hail damage. And it turns out that these high frequency small stones have a huge impact in terms of who's going to make a claim and how often those claims come around. So that's what I've been working on. Yeah, that's about it.
All right, well, just to start us off with a question here, what is one piece of quote unquote established hail knowledge that you think maybe needs to be rethought, given that you're bringing a fresh perspective as early career scientists?
I think I just said one. I know looking into literature, especially on the insurance side of things, that size threshold is a big component. You think of 1 inch or 2 inch hail, like a singular event causing massive damage or just enough damage to make a hail claim. And we know, looking at the data and having lived in Colorado for a while, it's those high frequency small hailstones that really wear down the roof. And we need to be including that.
I have to go off and agree, especially because that's exactly what I'm researching right now. From our disruptor data, so for my project, we're impacting shingles with approximately 500 hailstones, and that is extremely mild compared to what is actually seen. Our disruptors, which are a 1 foot by 1 foot probe, is capturing maybe 900 stones in about 10 minutes, and it could go up to thousands. So we're already seeing damage on roofs from just the project that I'm researching right now. And this is likely going to be into long-term damage that possibly could make the shingles more susceptible to dents and ridges, or I'm sorry, yes, dents and tears from higher, larger hailstones, the 2 inches, maybe more severe storms.
So I guess coming from the, do you have some? Okay. Coming from the forecasting side of things, I know I like how we're split here, forecasting versus impacts.
We didn't plan this.
No, but it occurred. I guess the sole focus on hail, or at least the primary focus on hail amongst forecasters, has been the thermodynamic side of things in forecasting, right? Your CAPE, your lapse rates, for those of you savvy. And I guess my kind of passion is relaying that it's definitely two-sided, and perhaps even the shear profile has just as much, if not more, impact on the potential for hail than thermos do. And there's a lot of things that I, like, without giving away any secrets, like are really almost kind of counterintuitive for how we actually think the ingredients do come together for hail. So it's really interesting how the past kind of 10 years or so, we've really kind of flip-flopped in terms of the necessary ingredients that are thought of as being good for hail.
I suppose I'm more on the individual hailstone stuff right now, like more on the microphysics things of the hailstone itself. What I would say that by adding or like modifying hailstone models, I am seeing a huge difference in health statistics in the end, especially for the medium to large hailstone, that side, which might be interesting if we're talking about like slightly smaller hailstones. I guess one thing I really learned in the past few months is that sometimes if you only introduce one piece of knowledge into a hailstone model without introducing the nuances around it, you might introduce more errors rather than making the hailstone model better. For example, even though right now I'm focused on non-spherical hailstones, even if I just introduce the non-sphericity of hailstones into the model without like tumbling, without like all the surface stuff, then I'm actually making it less realistic. Yeah, my talk is in the afternoon and I will talk more about this.
All right, any questions from the audience? Could you come up to a microphone just so our virtual folks can hear too? Thanks.
I am Joshua Putterman. I'm the CEO of Extreme Event Risk here in Boulder. I work with Dr. Tom Jagger and Dan Powers from Collabs. They're my partners. Berkshire Hathaway, we did a hail risk probability analysis in 2015 for 11 calendar years. And we were looking at the state of Oklahoma, all 77 counties over an 11 calendar year period. And then we went back in 2019 retroactively, which any consultancy worth their weight does not go back and look at their risk probabilities to see if they're accurate. And we were very accurate. We were 94.5% accurate to the actual NOAA storm data for hail for 2015 through 2019. But what we found is our frequency estimation compared to the actual hail was way off. It was the intensity we got right. And we were looking at hailstones of 1.2 inches or greater or 1.7 inches or greater. And obviously Berkshire, they took our data and we believe they went to the state insurance regulator in Oklahoma and fixed their premiums. We left it from once we gave them our data. But what I've heard from you, particularly in the state of Colorado, it's more the frequency of smaller stones and damage rather than the intensity of larger stones. Am I correct on that? That's my question.
So far, that's what I've been seeing, and I know Brandon's been working on it. I know that one of the drawbacks for the SPC, the NOAA data set, is that there's no reports really of hail less than 0.75 inches. It's kind of the cutoff.
Okay.
So you might be missing some of that. You know, if your frequencies are underestimated, that might be why. But you said you're using a threshold, right? 1.2.
Well, we were at the time. We were using a baseline, and when we started this in 2015, the data we were getting, and you know, I just oversee the work. My partner actually was getting recorded data for hail going back 60, 70 years from a hail database where people actually recorded the size of hail over the previous 60 years. And so
like golf ball or softball.
Yeah, like that. And so, okay, so that answers my question though. Thank you. I appreciate it.
That's an interesting point. Thinking in terms of a forecasting perspective, are there things we need to change when forecasting to ensure we account for, say, some of these more intense impacts that come from smaller stones?
Cannot speak to the forecasting side.
So could you repeat the question?
Thinking of this from a forecasting side of things, are there things that we need to change about our forecasting to account for the fact that hailstones less than 3/4 of an inch can have a large impact?
Yeah, I mean, I think that's the issue. And I think that's like one of the leading problems up till now has been getting a data set of small hailstones. So I think we're relatively less experienced with the smaller stones than we are the larger stones.
And of course, tough to find observations of those as well.
Exactly.
Right. Yeah, there's another question.
Hey guys, my name is Prescott Bishop with Gallagher out of Dallas. I got a question for those on the kind of more insurance side of things. I know kind of traditionally a lot of catastrophe models sort of use this max hail size, as we alluded to, as kind of the primary hazard to damage function relationship. But you also mentioned that the frequency is also important. Can your hazard to vulnerability functions sort of be boiled down to a single variable like kinetic energy, for example? Or do you think it's really like a multivariable function?
I would love to get my hands on kinetic energy data. Do you want to take this one?
I don't think it's just one variable. Yeah. I don't have too much, but
I do think looking at it, I've run different tests where you just use a very basic machine learning model, like a gradient boosted, and you just give it frequency and see how it can map out onto hail claims. You give it just mean size, see how it maps out, max size. And overall, if you compare, let's say, using just frequency to just using like a climatological mean size does do better. But if you look at it in terms of frequency of all size hail, small hail, and compare that to, was there a singular large hail event? Frequency does way better.
Interesting. No, a quick follow-up question. Is there, do we know if Doppler radar is capable of detecting sort of more of the frequency side of things in addition to the max?
I believe so. From what I've read, the radar products are quite good at kind of giving you a really overall view of where hail frequencies occur, and probably a little bit better than SPC because of some of the limitations of just people reporting. If there's no people, is there hail? So I think radar is good for that. But my understanding, and this is where I'm lagging in the research maybe, is that it doesn't do a great job on mean size or just getting hail sizes right. And that is a component, like to your first question, I don't think you can boil this question down to one variable. Kinetic energy might be it, but I think you do need to take into account, the size of hailstones, the fact that we use diameter, but they're not perfect spheres comes into play too, and frequency, you do need that. So radar products could be the answer for that.
Okay, that's good to know, because I've seen the radar products that are basically the derived max size, but not so much the mean size or the frequencies. Be interesting to see those derived products as well.
For sure.
I imagine it's out there. So thank you.
Yes, I was talking to somebody about that. Yes, we're on it.
Thank you very much.
Andy.
Because it really is, the maximum hail size is interesting, but it's the one which has the peak in the kinetic energy distribution with size, which is the important one to look at. And one way to kind of go about it is if you have two radars at different wavelengths, dual wavelength ratio provides a pretty good indication of what the median, the mean, median mass weighted, and actually the good one would be median kinetic energy weighted. But if you had dual wavelength, but really just looking at mesh, maximum estimated size of hail, that's probably not the ones that are doing the most damage because they're very rare.
I'm not arguing that a singular event of large hailstones doesn't cause damage, but in the grand scheme of things, when you look at hail loss across the states, it's not the biggest numbers.
Okay. Did I hear a question from the virtual folks? Doesn't look like it. Well, following along from this, then, it seems like there are a wide range of potential observations, hail observations, that you might need in order to better inform either risk or your forecasting skill, or if your hail model is doing well. What are some of those observations that you would recommend we seek out?
Definitely need to see more high concentrations of small hail in the field.
The full size distribution, maybe?
Yes.
Yeah. Okay.
It is interesting looking at the SPC data when I realized that they didn't include less than 0.75 inch. That's not entirely true. California really wanted in on this. So basically all reports of hail smaller than 0.75 inches are out of California since 2016. But it would be nice if those just get reported across EU.
I would say,
Yeah.
and like half of that's in the reporting too, but the other half, like you will get scenarios where like someone might report like an off-size hail and then it's recorded as something that is discretized. So.
And when sorry, I keep talking, so you go ahead.
No, I just want to say it would be very interesting to see some sort of hail size distribution sampling. I know it's like not that realistic to actually have it, just because of the spatial like distribution. But yeah, like if something like that can be done, I think it would be very interesting to compare to like hail modeling.
Can introduce one of those size components instead of softball, it's football because it's shaped. Be nice.
Yes, and so I know IBHS is doing a lot of work with three-dimensional modeling. Oh, is somebody, did I miss
There was somebody trying to ask.
yes. Who was it? Oh, it was John.
So I have a question that ties across you and our two industry panelists. More thinking, how does industry treat the fact that hail is not regular in general? I mean, we know that the UL standard and a couple of the other standards are based on relatively uniform spherical ice balls that have constant density. Where do you see that potentially going in the future to maybe incorporate some of those better measurements if we had that information?
Go ahead. So I work more, I don't interface directly with the insurance companies in my capacity. I think what I'm trying to look at with this research, and it's a month old on my side. So it's more information, and more information is always good. And I think just a better understanding. I know that hail claims going through the roof has been considered kind of a fraud thing, and that might be part of it. But I think helping insurance companies to understand that there's more going on than just the traditional CAT modeling could help a lot. How it helps, that's on them.
Sorry, I heard, I heard UL testing.
Yeah, so.
Sorry.
Yeah, you might have to.
Very
Is it
little.
work? Sorry, it's me being quiet. Not used to talking in public. So how do you see some of these new measurements perhaps contributing to the way the industry treats hail impacts, right? I mean, I know IBHS has done a lot of work with real hailstones as opposed to these sort of uniform spherical ice balls. But that's not true across all industries. So what measurements do we need beyond just just the frequency to sort of get a better picture of this and allow industry maybe to think more about that resilience across a lot of fields as opposed to just roofing?
Yeah, so we used to do a little bit of UL testing. We have we do have part of that at our facility right now. But there is a difference between the UL testing and what we do. UL, like you mentioned, it's a spherical steel ball. And that, I think ours is a 2-inch steel ball that creates completely different damage than a 2-inch hailstone that we've created in the lab. And our hailstones are pretty close to being realistic hailstones. Yes, ours are still spherical because we don't have the capability yet to get all the lobes and but density, kinetic energy, mass, diameter, all of those come into play when we're trying to create realistic damage. And we've noticed that the UL steel ball testing creates worse damage than if you take a 2-inch steel ball versus a 2-inch hailstone.
I want to ask a question. What do you think is the reason? Like, what do you think is the reason for the difference in like damage?
Well, for one, the 2-inch steel ball is a lot heavier than the hailstone. So that the weight of it absolutely has something to do with it, but also the material. It's a steel ball and then you have ice.
All right, DJ?
I noticed in each of your kind of introductions, you're all working with a mix of kind of more traditional, like I guess physics-based modeling, statistical modeling, machine learning. And I'm curious if you could speak to some of the strengths and weaknesses you've experienced with each approach, and what are you for your hail modeling work, what directions are you going to be favoring going forward?
Sure. I really want the radar data. I think in terms of like what I'm focusing on, getting a separate source, like I kind of kid about the radar, but it is important given the gaps in SPC to have a secondary source of data, even just to confirm that what we're seeing, I mean, in insurance, it is where people live. So maybe some of the limitations in SPC don't matter as much, but it would be more cohesive to have more information. You can't have enough data, right? We just want more data.
I could say the same for us too. Claims data mainly.
Oh, yeah.
Yes, please share your data.
I feel like I would just repeat what they would say. Really, it's just been a numbers problem.
I guess I work less with like real life data, but I think it would be interesting to actually put the more complex, like explicit treatmenting models in like detailed microphysics models to actually parameterize them and put them in bulk models. That's what I'm also kind of working on right now.
Maybe a machine learning emulator type thing usually?
Learning?
Yeah, maybe a machine learning emulator that, could emulate some of these microphysical impacts that you're seeing.
Cameron, aren't you working on like some stuff? But
Oh yeah, for sure. Yeah, self-organizing maps.
Mm-hmm.
Yeah.
Another question from the audience? I am curious. So say you have some more, say you get these better data that you're asking for. So you've got some more realistic hail observations and you've got more hail size information, small hail size reports. What do you do with that? How does that result in improvements?
Understanding whether, like, for small hail size, I guess it's looking at the claims data, understanding maybe if this is causing damage, we know kind of what damage is causing, but maybe how long is it taking for it to replace a roof? We deal with insurance companies, we deal with the public. It's something that we would like to know.
Yeah, I would say very similarly. And on top of having claims data, having accurate roof age data would be super helpful because you can tell how, like she said, how much faster they're replacing that roof. And is it actually, sorry, that was going to happen at some point. Is it truly that accumulated damage is just aging the roof really quickly? And so is it fair for them to put in a hail claim and have the roof replaced because it's just lots and lots of small damage versus a singular large event? In addition, just adding more information on the machine learning side, the model learns better, and being able to interpret the model becomes a clearer picture. Why is the model making this prediction? What is it telling us? Is there something to learn from what the model's learning as well? It'd be nice to have a clearer picture on that as well.
So I'm actually going to elaborate on the self-organizing map part of my research now, because I think the biggest issue that we've been facing is we want to kind of dissect all of the thousands of different hail events into different kind of forecast regimes or like different setups or like different combinations of ingredients. And we're able to do that now, but our sample sizes are just small. So if we're trying to kind of cluster these data into like about like 9 or like a dozen different most common clusters, if you will, of the ingredients that led to these hailstones, we just don't have a big enough sample size within each of those clusters. Like we'd love to see, like hundreds of hailstones created by this regime and then another couple hundred by that regime. And we just don't have that.
Yeah, for me, if we can get better data on hail site distribution or like the number of smaller hails, I think it will kind of help us to vet the different microphysics scheme you can use in hail model. For example, full speed, that's apparently that's going to be a big component on your final hail results for model. And they have a lot of different methods to calculate full speed, be it empirically, or be it just assume it as spherical or something like that. If we can actually have better data for a size distribution or something more nuanced like that, I think it will help us to vet these different schemes just to see which one is more realistic, I guess, for a model. Yeah.
Andy.
Now, how much does horizontal wind speed influence damage?
That's come up a lot. Trying to get wind direction data in a hailstorm has been tricky. Maybe you can speak to it. I know that IBHS has played around with that.
When we do our impact testing, it is pretty much straight on to the shingle, although we are working to create different angles to kind of capture that. We're not there yet, but hopefully in the future.
I know in terms of, we're looking at it as we look at top-down approach for our models. So we're looking at roofs. We use aerial imagery for that. And so just the directionality could play a huge role, but then it would depend on the roof shape and the roof and the building orientation itself. And our gable roofs more susceptible to damage than flat roof, depending on the hails are coming in at the angle or they're coming straight down. It becomes messy pretty quickly. Does directionality of wind matter in a storm? Yes. Have we gotten it?
Ted. And then next.
I'm going to ask this because I'm just ignorant. There's a lot of focus on structural damage, which of course is huge, but I wonder about agricultural damage and what interest is there. Is that something that's normally insured, or is that just an assumed risk on the agriculture industry part? And is it just well understood how hail damages, young plants and older plants?
I personally don't know too much about that. I know we've done some agricultural work, but that's more on the wildfire side than hail.
So I know when looking into data sources, one of the things that came up is FEMA has a pretty cool map online of all kinds of risks and risk index and all kinds of environmental factors. It's all CAT model stuff. And their data set includes agricultural damage. So that might be more covered on the FEMA side than private insurance, but I know nothing about agriculture. I do know that they use threshold of 2 inch rather than 1 inch. I've seen that number lobbed around a lot, but that is the extent of my knowledge.
Yeah. Okay.
Please use the mic.
Hi, everybody. It's good to see everyone. Hi, Ted. Yes, there's a lot of ag insurance products, and to some extent, the agriculture claims data is actually much, much better. Post-World War II, they actually put together a data standard for agricultural claims, so the data set is far, far better than what we have on the property side. But that's probably why you see a good amount of it show up in some of the Fed stuff through the FEMA products. But yes, there is a private market for ag, and it's a very big one. And of course, ag damage starts at even much smaller sizes. The wind-driven element that you guys were just conversing about absolutely plays a role there. Good question.
And thank you, Ian. And I'll add just from Justin McMecken at UNL is getting into this a lot. Ted, if you wanted a contact, and no, it is not well understood as to what stage of plant, how the hail hits it. Yes, there's many unknown variables there. I can confirm that. I get his hand up and then.
I'm Anthony Bernal Ayala. I'm also at the University of Wisconsin doing some core hail research. 2 questions for you guys. Other than the hail sample size and of course surface validation, what other challenges are you encountering specifically in your research while doing either modeling or doing that type of insurance, insurance research? And also a secondary question is a little bit heavy though. Are you accounting for satellite products, more continuous and wide products such as, satellite products, specifically GO16, GO17, that type of product in either modeling or in your insurance research as well?
Short answer, not yet. It's up there. I know even less about satellite data than I do radar, but it's definitely worth looking into. As for data limitations, is that the first part of the question? I think we've covered a lot of them. The urban bias plays a huge role. I think that is one of the ones that it's really hard to get at. There's all kinds of techniques, but at a certain point, you've taken this raw data set and then you've kind of grouped them, you've gridded it, then you've smoothed it to try and cover all those gaps, and the numbers keep getting smaller and smaller and less realistic for certain areas. And there's no one right approach that I found to cover those gaps. You can interpolate, there's all kinds of ways to do it, but filling in the rural areas, well, that one's hard to say. Yeah, filling in the rural areas is probably top of my list, that and small hail, but we've covered that a lot.
Trying to get the coverage, environmental coverage along different areas. For our field deployments, we mainly go into the high plains region, but we're trying to get the suburban areas, the southeast regions, and try to understand the environmental differences in the hail characteristics. And then, if we talk about data issues, it's just when your program doesn't work and you have to contact the people that helped create it for you because you can't process your data. That's a challenge.
On the forecast side of things, I'd really love to see more like physical studies, such as like wind tunnel studies or like more studies on heat transfer coefficient, stuff like that, because a lot of the formulas we are using right now are from like 1960s, 1980s. So if there are more like actual studies on the microphysics or dynamics of hailstones, I think would help a lot in modeling and after that forecasting. As for satellite data, I've never used it. Yeah, I think that's my point on that.
Yeah, I actually, just to comment over that, I did research with Macamjit and Relámpago down in Argentina, so I was curious if you were using satellite data as well in your research.
I think along with like the size issue, I just think that like one of the biggest questions I ask myself whenever I'm doing my research is like, is this data representable? Like, should I believe it? Should I trust it? And like, I hate having to ask myself that. So I just think like, like the urban issue, the size issue, like if we're actually, like reporting like 2.5 inches as golf balls, like whatever, it's just, it's messy.
Great, thank you. And I now see the time, and we've used up all of our time. So let's thank our panelists. You're welcome to grab them later. So that's more. And our next, we'll move on to our next session.
All right, so our first session is going to be looking, building on some of these difficult problems in terms of climatology and climate change. So what does hail risk look like into the future? And our first speaker is Dr. Sarah Bang from NASA Marshall Space Flight Center.
Good morning, everyone. I guess we'll start off with a bang. I mean, with a name like that, you have to make every joke you can. But I'm Sarah Bang, as John mentioned. I'm from NASA Marshall, leading off talking about some work I'm doing with my colleague Dan Cecil on detecting severe hail from spaceborne platforms, how we use those detections to build climatologies, some of the work we're doing to validate those climatologies, and then some of the challenges and current work that we're going through right now. So I don't think I need to talk about the motivation of hail, being damaging. Did you guys know that hail can be incredibly destructive. But from the precipitation research side of things, a lot of satellite precipitation algorithms do not retrieve hail because it is so rare and because it is so extreme. However, if you don't account for it in your algorithms, you will get very unrealistic rain rates for something that is actually, large pieces of ice. So, hail, besides being in societally impactful, also in the precipitation research side of things, can cause a lot of errors if you don't account for it. So all of these things motivate all of us to be in this room and motivate my group in particular to try and understand the climatology of hail, its distribution, its frequency, severity, those kinds of things. You can build those climatologies using radar data, using human spotter reports. But as we know, and I'm sure we'll talk about a lot this week, that's not available necessarily everywhere. It's not globally consistent. And in a data sparse or remote or oceanic place, you're out of luck. So for the most globally consistent picture, we choose to use satellite data. I will be specifically talking about passive microwave radiometers in particular. We like to use them because there's excellent global coverage and they have a very long legacy in space. I'll be talking about 4 instruments. I'm not going to spell out these acronyms, but it's TRIM, TMI, GPM, GMI, Aqua, AMSURI, and GCOB, W1, AMSUR2. But what these passive microwave instruments are measuring is that there is upwelling microwave radiation from Earth's surface. If there is a cloud and there are ice particles within that cloud, they will scatter away that radiation so that the radiometer receives lower brightness temperatures, less microwave radiation above these places where the radiation has been scattered away, resulting in a lower brightness temperature relative to the scene around it. It's called a brightness temperature depression. You can see a very good example of that in the lower right. That is the TRIM 37 gigahertz passive microwave overpass of a severe hailstorm in Oklahoma in 2012. Some of you may have been there for this. The warmer colors, that is the lower brightness temperature. So those pockets of reds, oranges, and yellows, that is where that microwave radiation is being scattered away. This relationship between lower brightness temperature and likelihood of hail, instances of hail, that's been known for a long time. Lots of algorithms in the literature have leveraged it. Most of them are just a threshold, yes, no. If the temperature is below a certain number, we're going to call that hail. There are also lookup tables, that kind of thing. What Dan and I have done is to actually fit a curve. So what you're looking at on the left is a probability of hail on the y-axis with brightest temperature on the x-axis for 3 different frequencies, 85, 37, and 19 gigahertz in the different, black, red, and blue there. You can see to varying extents, there's a relationship between the probability of hail, increasing probability of hail, with decreasing brightness temperature. And all that we have done is to fit a curve to this function, parameterize this probability relationship. We use 2 frequencies. We also take into account the height of the troposphere and things like that. But we've made a probability function where you can estimate from 0 to 100% the probability of hail for any given suite of brightness temperatures. So that same overpass that you saw before, for each little, storm cell identified by the algorithm, we can now estimate the probability of hail within each. And that means that over the lifetime of the instrument and throughout its domain, you can tally up the probabilities of hail. And of course, you normalize for orbit and sampling and grid size and things like that, but then you can actually create what, a passive microwave ideas of the global climatology of hail. Now, this is the TRIM instrument, which is only between 35 degrees north and south latitude. And we will be looking at several of these maps to go forward. But then, oh, that's weird. What this also means that now that you have this methodology, you can apply this algorithm to any instrument that has the same or very similar passive microwave frequencies on board. Just a heads up, the different instruments have different footprint sizes. Passive microwave takes into account all of the scattering within the field of view. And if you have something like a hail core, right, and it's not going to occupy the entire footprint, it's called non-uniform beam filling. You have to adjust for the size of the footprint before you apply this to any other sensor, just so you know we crossed our T's and dotted our I's. So you've seen the TRIM climatology. You can apply this to the GPM satellite. That goes to 69 degrees north and south latitude, AMSURI and AMSUR2. And now the TRIM and GPM satellites, they are both TRIM was and GPM is in inclined orbits. They're very similar. And it was very easy for us to combine these data sets. So now this is the climatology of hail from 1998 to March of this year. Also being in an inclined orbit means that they don't sample preferentially at any given time of day. They are agnostic to the time of day, which means they're great for looking at the diurnal cycle of hail. And if you're interested in that, be sure to catch Dan Cecil's talk on Thursday. But so looking at this climatology, we see some of the usual suspects, right? Central United States, Northern Argentina, Bangladesh. But you also see some really interesting features like offshore of Eastern South Africa. The Mediterranean shows us light maximum. So this is just a really cool way to look at the distribution of hail around the globe and really drill down into these areas. Now, we're looking at a satellite product that is measuring scattering from a huge field of view. Okay, it's a bit of a proxy for hail. You're not actually directly retrieving hail itself. So there are a couple questions that come up from that. And a lot of folks, I would encourage you, if you know a region and you know it's hail, please come find me at the coffee and talk to me about it, because I love to drill down in these details. There's a lot of insight to be gleaned there. But for example, this maximum in sub-Saharan Africa, it's a region famous for thunderstorms, but not necessarily hailstorms. So is our algorithm is it responding to really deep, dense, I guess, small hail or very, deep concentrations of graupel, and that's scattering the brightness temperature, but it's not necessarily hail? Our colleagues in Argentina have noted that our maximum is slightly north and east of what they have observed. There is a very tiny hail maximum east of the Himalayas, right where the Kunlun Shan Mountains are. Is the algorithm really finding hailstorms, or did a couple of them sneak past our snow filter? Our colleagues in Switzerland have mentioned, they said, where's all the alpine hail? Well, so all of these questions, how is the algorithm performing in terrain? How is it performing over water? How is it performing, in the tropics? These are all great questions. And please come find me after the break. I would love to talk to you about it. You don't have to come to the microphone, but please do. So to that end, in 2021, we published a paper where we were actually looking at coincident spaceborne radar. Because unlike a passive microwave instrument, which just, it just receives the upwelling signal, a radar is an active sensor and it's emitting a pulse of radiation. And then receiving, what is scattered back can actually get you insight into the microphysics, things mapped to certain altitudes. And because there are relationships between hail and radar reflectivity, and I know we're going to talk about them this week, but we can kind of look at what do these storms that the microwave calls a hailstorm, what do they look like in the radar? And without going into too much dense detail, we really wanted to make sure that the algorithm was performing uniformly across the domain. You don't want to see that it's overestimating hail in the tropics, but then really underestimating hail in the subtropics or something like that. And so at the top, those are mean profiles of radar reflectivity with temperature. An algorithm that performed very poorly geographically, if it was saying that a storm that had 20 dBz at -20 in one location had the same probability of hail as something that had 55 dBz at -20 in another location, that algorithm's not doing a very good job, right? So you would want all of those lines, because each color is kind of a different region, you'd want them to be close together. And you want to have the palest colors in that map on the bottom right. So especially compared to other algorithms, literature, ones that use that yes/no threshold, the method that we have developed did show the best performance, but there's always room for improvement, as I mentioned. So one question that we ask ourselves is, the satellite is, it can only observe, what it is observing is the particles that are aloft up in the cloud. And, without taking in any information of what occurs to those particles before they reach the ground and impact all of us. So one question that we have, is looking at this possible disconnect between what's going on aloft where the satellite sees it and what goes on at the surface when the hail actually reaches the ground, or if it reaches it at all. Some currently funded work with several colleagues here in the room is looking at these hail properties, at their size distributions, at their trajectories, at their melting from a variety of perspectives, from space, from ground radar, from in situ aircraft, from numerical simulations, and just trying to get at these relationships between hail size distributions, what they undergo along their trajectories, and are any of those characteristics manifested in the satellite signature that we see. Some other work is to look at that non-uniform beam filling aspect that I talked about. So in the bottom left, that is what a 19 gigahertz footprint, that's the pink circle. That's how big it is relative to an overshooting top, kind of that bubbly convective core, right? So it is obviously not taking up the entire footprint. So you're getting just kind of this smoothed out, integrated idea of what the scattering is, but it's not necessarily specific to a given column of scatterers. It's not specific to a size. And so there's some work to use Aquamodus visible in IR, which has wonderful horizontal resolution, but can only see what's going on in cloud top. And Aqua-M3, which is the passive microwave, which is actually getting at some of the microphysical processes, but it has terrible spatial resolution. So the goal is to use the strengths of one to fill in the gaps with the other and hopefully improve detection in both fields. So with that, I will point out that the gridded climatologies that you saw, the TRIM, GPM, and TRIM and GPM combined, those are available to the public. You can download them and play with them to your heart's content from the NASA GHRC DAC. And also our colleagues at Langley have created this wonderful ArcGIS portal where you can go overlay these climatologies, and not just the passive microwave, but also some overshooting tops, some lightning climatologies, and really drill down into those details. I mentioned that there were two publications about constructing and validating this algorithm. They are both open access from the Journal of Applied Meteorology and Climatology. And there's our contact information. If you don't happen to find me this week and you want to say, no, your hail in Kansas is wrong, please do reach out. And with that, I have no idea how long I've taken. What is it, question? Okay, thank you.
So absolutely excellent on time, which means we start off on time, which is great. We have a question already up in the corner, so we've got plenty of time. You come up to the microphone if you're going to ask a question.
Hi, have you considered parallax when considering these spaceborne observations?
Yes, so a lot of the data are already parallax corrected before I even see them. When we go into starting to pair the MODIS overshooting tops and the passive microwave, we have to do a lot of correction because of the angles that these different instruments see. But yes, I mean, that is.
And just a follow up to that,
what keeps us up at night.
Are you accounting for uniform cloud top height, or are you accounting for variable cloud top heights when doing the parallax correction?
They're variable.
So varying cloud top heights?
Yes.
So for example, in the GO16, the lightning mapper, it applies for the highest cloud top height to all the uniform cloud. So you would parallax correct the entire cloud with only one maximum cloud top height. Is that something similar you're doing, or are you accounting a time series of multiple maximum cloud top heights to account for parallax?
I'm gonna look over at my Langley colleague for that question. Thank you.
All right, thank you.
Other questions? One from online.
Please.
I have probably a very naive question. I guess, how do you know with the brightness temperature that you're detecting hail producing storms versus very deep storms? Like, do we know about a relationship between hail production and brightness temperature?
So yeah, that's not a naive question at all. And that is one of the problems, is that, okay, so one thing that we try to do, okay, is that, so do you see the three different frequencies? Obviously, each of those has different wavelengths. And so the 85 gigahertz, which is that black line, that really tops out around 60% predictability, because it's very sensitive to scattering from small ice particles. And so it will be scattered through the floor by things that are not necessarily hail. But a hailstorm will certainly scatter it to very low temperatures, but it doesn't have to be hail. We're looking at something like a 19 gigahertz. That's a much longer wavelength. It's not going to be as sensitive to those really small cloud ice particles. So you have an idea that is being scattered by probably larger things, but not necessarily. And deep columns of Graupel, or that, I guess that high frequency small hail, this is our nightmare, all of us. But the brightness temperature can be very effectively scattered to very low temperatures by that. And so trying to work with the radar, trying to tease out, is there maybe a ratio of these brightness temperatures that is going to occur only in these high frequency, smaller hail particles, or just, the larger hail. But that is because brightness temperatures, they're not unique to a certain profile of scatterers. You have that non-uniform beam filling issue. They can be scattered to very low brightness temperatures by smaller particles. That is something that is a constant thing that we work on, for sure.
Does anyone online have a question that they'd like to ask Sarah?
Can you hear me?
Yes. Hello.
Awesome. So this is Matthias Gergely from the German Meteorological Service. I was wondering, great results there, Sarah. Do you have also any kind of analysis for trends over time? So do you see an increase in the frequency of hailstorms globally or in certain regions of the Earth? Or is your data maybe too scattered in the time series to actually look at those trends?
I don't know about too scattered, but right now we only go back to 1998. These instruments have been in space since the late 1980s, but going to the SSMIs, their footprints are like out of control big. So we're still working on those, and I don't know if it's feasible. But we don't have a data set long enough that I would feel comfortable trying to establish a trend. But I would say the first step in trying to figure out where the trend is going is to have confidence that you can say where it currently is. And so I guess that is the hope, but I would say my data set is not long enough for me to confidently make that assessment.
But the data that you presented is basically the average of all those years for however long the
they have it. Yes, it has been. It's been smoothed and also gridded, and then it is. Yes, it's like a yearly average is what you're looking for the whole lifetime of the instrument.
Okay, thank you.
I had a quick question as well if there's time.
Yeah, we can slip that in.
20 seconds, go.
Oh, amazing. No, I was just wondering, you mentioned before that these changes in brightness temperature were relative to some sort of background temperature. Is that accounted for in the algorithm, or is it just like raw? For context, I don't know much.
It is. So one thing that we look at is we compare the brightness temperature minimum to the storm's maximum, which there are some, there's some very feasible criticisms of that, but that was our attempt to actually get at a brightness temperature depression relative to the scene around it, and not just kind of give you an absolute minimum.
Awesome. Thank you so much, Sarah. Really cool stuff.
Thank you. Okay.
Okay, thank you very much. So moving to one of the areas that Sarah's highlighted there for Australia and looking at a radar-based climatology, we have Jordan Brook.
Hello, just looking for my slides on the screen there. I've been informed that I can't drive the slides, so you'll just have to deal with me saying next every so often to change the slide. But if I could go to the title slide, if that's okay. So I'm going to present a radar-based hail climatology of Australia. And as John mentioned, hopefully I'll be able to attempt to either prove the results from Sarah's climatology or see if any of the radar-based data disagrees with that climatology. And I'd just like to acknowledge my co-authors, Alain Pratat, Josh Soderholm, Hamish McGowan, and Rob Fortune. Next slide, please. And then, so getting on to the Australian Radar Archive, we have 54 radars in our study, and they are broken up between S and C band on this plot. If you just flick through the next two animations, please. And the blue radars on this plot are S bands and the red ones are C bands. Next slide, please. One more. And what we also have in this plot is the dual pole coverage of our network. And so in this archive of 54 radars, we have 8 that are dual pole. And so the limited extent of that coverage means that we have to rely on single polarized radar for our hail retrievals. Next slide. And so the single polarized hail retrieval that we're using for this archive is the maximum estimated size of hail, or MESH parameter. And very simply, it's just a weighted reflectivity, empirically weighted reflectivity integration between the 0 and -20 temperature heights within the storm. Next, please. And what this is, how this has been empirically fitted. It's been fitted with S-band radars, and it's been fitted to hail reports in the United States. And so this naturally presents some problems for our hail climatology in Australia, which we'll get to. Next slide. And so first, the processing we use. So on the left-hand side here is mesh hail size, with darker colors being bigger hail sizes. And it's accumulated, for an example storm here, over time on the left panel. And because the radars only sample every so often, we have the hailstorm moving along and creating a spotchy swath here through time. And what we do is we apply an advection correction to that swath to make it nice and smooth in the middle. And then we also only take 4 hail sizes in our archive. So mesh isn't great at 1-to-1 hail sizes. There's almost no skill at identifying 1-to-1 hail size. So we take it at 4 different hail sizes. And there is some skill at above a certain threshold, you can tell whether a hailstorm existed. And so we do 20, 40, 60, and 80 millimeter mesh thresholds and create a polygon on the right-hand side there. Next slide. So problem 1 in this approach is that most of the Australian radars are C-bands, those red radars on the first slide. Now, the reflectivity response at C-bands is considerably less than at S-band. So what we expect in our archive is that if an S-band and a C-band radar were to observe the same storm, we're going to get a greater mesh value at S-band than we are compared to C-band. So we apply correction, and this is problem 1 that we're going to talk about. Next slide. Problem 2 is that mesh was calibrated in the United States. And this is a plot showing Australia and the United States on the same longitude. And it's just to show that Australia is closer to the equator than the US. And so we have a significant portion of the country that's in the tropics. And it's not a given that we expect that mesh is going to work perfectly for identifying mesh in the tropical regions of the country. In the subtropics and the temperate regions, we expect it to do a pretty good job. Next slide. And so we're addressing problem 1 here, and that's the C-bands. And what we did is we looked at 9 overlapping S and C-band radars. Next slide. And we're going to show a subset of overlapping storms for this region in the center of the East Coast. Next slide. And so this is just an example of some different events. Each panel shows a different storm, and we have gridded mesh. And on the dotted line down the middle splits C-band mesh with S-band mesh on the right and C-band mesh on the left. And what you can see for the first panel, it's pretty hard to see actually. The S-band is picking up a storm where the C-band isn't at all. And then for some of these larger cases, you can see darker red colors on the right-hand side of the dotted line, indicating that, as we expect, C-band mesh is less than S-band mesh. Next slide. So if you plot a scatter plot comparing S and C-band mesh, what you can see with S-band mesh on the x-axis and on the y-axis we have C-band mesh. We can see that the pixel-wise comparisons fall below the y=x line on these scatter plots, indicating that for all of the 9 overlapping regions, the mesh that we're getting is larger at S-band than it is at C-band. And so if we have a look at these yellow dots, which is showing the largest mesh identifications at S-band, then we're seeing that the S-band mesh is picking up around 70, 80 millimeters mesh in some cases, but that's only registering as 40 or 50 millimeters mesh at C-band. So what we've done is for our 4 hail sizes, fitted an offset that we expect between S and C-band. Next slide. And these are showing the slides here where, the offsets here. And so at S-band, we have 20, 40, 60 millimeters. And then at our offsets, you can see here we have 6, 8, 15, 25. And so the actual values that we're thresholding out at C-band are 14, 32, 45, and 55 millimeters. So it's quite a significant offset we see. Next slide, please. Now, these will not work for individual events, and that's because the reflectivity response to larger hail sizes at C-band simply isn't there. So another way of saying that is that a storm that contains 50 millimeter mesh will look the same as a storm that contains 100 millimeters mesh. And so the information content at C-band simply isn't there. Next slide. But what we're trying to do is see if these offsets make sense in a climatological sense. So if we apply these offsets, are we going to achieve the same frequency over a long period of time as between C-bands and S-bands? Next slide. And this plot is getting at that. So what we've done for all of the polygons in our archive, what we're doing here is we're showing a PDF of the area at all different hail sizes. So 20 in the first panel, 40, 60, and 80. Now, these empirical PDFs show C-band area in blue and S-band area in green. And what we can see is that the S-bands are detecting more area for the same hail threshold. So the storms look larger at S-band. And applying our C-band correction, those offsets, the red bars look much similar. So the areas of the same storms look much similar to S-band when we apply the correction. So let's go to the next slide, please. Once we apply those offsets, this is the type of climatological distribution we're getting across the country for all of our radars. And they're all the polygons are plotted on top of each other here. Now, this is a pretty plot to look at, but what we need to do is grid this back to a grid. So we're analyzing the annual frequency of hailstorms. Next slide, please. And there is a lot of details to cover on how we go from polygons to grids here, and ask a question at the end. I've got some slides on it if you're interested. But basically, this doesn't have a color bar because we're just showing the relative frequency across the country. What we can see here is quite noisy, and this is because it's only a limited archive. So there's about 20 years of data for some radars, and some radars are newer than that. So we see a hail maximum along the East Coast, and we also see a secondary maximum up in the Kimberleys in the top left northwest area of the country. But what we want to do here is we want to interpolate not only where we have radar data, but we want to use that to interpolate and create a grid across the whole country. Next slide. And so the interpolation that we use is called a variational interpolation method. And the cost function we use, it minimizes terms that have to do with the fidelity to the observations, a smoothing term, and that's because this is only a 20-year archive. And so we expected if this was to go on for 1,000 years, this data would look much smoother than what it looks. And then we also have a background constraint, which just means that far away from the country, we ensure that the frequency drops off to 0 over the oceans. And so next slide, some results from the interpolation. We have 20 in the top left panel, 40, 60, and 80 annual frequency of hail. And we have a bimodal distribution with a maximum on the East Coast and also a maximum in the northwest of the country as well. Now, the distribution looks similar for all these 4 hail sizes, apart from the fact that we have larger frequencies for the larger sizes, so in the 80 millimeter panel in the east of the country compared to the west. And also note here that storms, the color bar indicates that storms with 20 millimeters hail are 12 times more frequent than storms with 80 millimeters mesh. Next slide, please. So breaking this up by month, what we see is the same bimodal distribution kicking in around September, and that continuing through the austral summer to around February. I won't go into this plot too much, but just to show that the hail frequency kicks off on both sides of the country at about the same time. Next slide. Now, this is, if anyone knows Australia and the storms around the country, you're probably thinking this already, but if you look at the Severe Storm Archive of hail reports, what you'll find is that you have a large concentration of hail reports on the East Coast, which is what we know anecdotally to get the most hailstorms. And you don't really find this secondary maximum on the northwest of the country. And that's partly to do with the fact that nobody really lives there. It's a very sparsely populated area of the country. But in places like Darwin, right up the top of the country, you would expect that if this was a true hail frequency maximum, you would have more reports than what you expect. And the only way we can really validate this at the moment, because there's no ground observations, is by talking to forecasters and whatnot. And speaking to a forecaster recently, he sort of agrees with the fact that this northwest area hail frequency maximum, which was also in the plot that Sarah presented, is likely spurious. So we have a lot of thunderstorms in the region, but not necessarily hailstorms. And so next plot. Next slide, sorry. Yeah, this is our problem number 2. It's that mesh was developed in a different climate. And so it's not necessarily true that we're going to have mesh working in the tropics, which is so different to where it was developed in the continental United States. So how can we deal with this? Next slide. Or a better question, what's going on there? Some explanation would be that maybe hail's melting before it reaches the ground. And this is some hail melting modeling work that we've done. And what we've done is we've taken, on a hailstorm day, we've taken 3 different temperature profiles from soundings. Brisbane in the middle of the country in black, on the right-hand side temperature profile, Darwin, which is right up the top, and Hobart, which is right down the bottom of the country. And so what we've done, we've modeled 4 different hail sizes. And with height, you can see how hailstones melt once they get below the freezing, once they get below the melting layer in the atmosphere. And what we see is that hailstones only completely melt in this model if they're 1 centimeter in diameter to begin with. If they're 2, 3, or 4 centimeters aloft, they will reach the ground. They will experience some melting, but they will still reach the ground. So while melting likely does have a significant role in why we don't see hail in the tropics, we don't think it's a complete story. Next slide, please. And what we're starting to think the explanation to this is, and these are plots from both maximums, Broome's up the northwest of the country, Brisbane's on the east coast. And this is the whole hail archive plotted on top of each other. It's very difficult to show 12 years of data on top of each other, but this is what you see. And I think what you see here is that Brisbane and the East Coast do have these long-lived high mesh supercell-like tracks, whereas in Broome, what you'll find is that you'll get these storms popping up and there's a large amount of instability in that region, but you don't have the wind shear characteristics for those storms to become organized and live for a significant amount of time. And so we're thinking that this sort of difference in storm structure will explain why on the East Coast, we're seeing large hail form because hail takes a significant amount of time to form. Whereas the short-lived storms on the West Coast, we might not get the hail formation that, that is required for hail to then fall on the ground. Next slide. And this is just empirical validation of the fact that the storms in Brisbane, the probability distribution has a longer tail. The storms are longer in Brisbane than compared to Broome. Next slide. So is there any way that we can correct that hail maximum in the tropics? And this is a method that we've been using in the modeling work that we've been using, where we take a melting level deviation from the mean. So where you have a really high melting level, you impose a melting level constraint within the interpolation method. So there's just an extra term in that equation down the bottom for temperature. And this penalizes hail frequencies in the tropics, and it penalizes it according to those red colors on the plot there. So what does that look like in the final grids? Next slide. The hail frequency across the country, once you apply this correction for the tropics, looks like this. And I think this looks fairly good. If you were to intersect the hail frequency with the population density, you would come out with something that looks broadly like the hail report since 1900 there, where you have a significant maximum on the East Coast. You also have another secondary maximum just west of Perth, just east of Perth, sorry, in Western Australia. But this is, we're pretty happy with how this looks. Next slide. But the question is there a more physically realistic way to account for these tropical storms? Is there some method that we can actually maybe change the mesh formulation that we're using to account for these storms instead of just ad hoc applying a melting correction to the interpolation at the end? And then last slide is next slide, please, is one for the insurance or catastrophe modelers out there. Using this genesis frequency, what we've done is we've built a stochastic hail model based on the radar archive. So we generate events based on the genesis frequencies that we have, and then we bootstrap from historical events to create this stochastic model. And this is a 20-year synthetic event set that hopefully in the future, we're going to be able to base annual exceedance probabilities for hail, and also base pricing in the insurance industry based on these types of outputs. So to my summaries, next slide, please. The first one is that corrections must be made when comparing mesh between S and C-band radars. Next. Hail retrievals appear to overestimate hail in the tropics, so there's some feedback for you, Sarah. And then possible future changes to radar-based hail retrievals like mesh could account for this, but it's still very much an open question. And then future work that we're also aiming to do is to improve the climatology using melting and trajectory modeling. And that model is called HailTrack, and you should check it out. And a new radar gridding technique will also help with the data quality as well. So thanks for listening, and I'll take any questions.
So we've got time for a very quick question, and I'm going to take the opportunity to ask it because one of the interesting things that you show is an annual frequency, yet knowing the radar distribution, particularly the S-band deployments, for example, Nimoy, which you talked about, those are relatively short compared to some of these other archive lengths. How did you normalize for the temporal differences in the detections from the radars?
Yeah, great question. So if you flick forward past the references, past, yeah, keep going. And so this is some plots I've done to explain how we generate a frequency. And so this is an example where we've got the Mount Stapleton radar, we've got the Marburg radar, and they're roughly 20 versus 12 years in duration. And so next slide. What we do is that we look at the coverage for each of these radars. Next slide. We see where they overlap. So here, 3 radars overlap in the red and 2 radars overlap in the blue. And so we know from this overlap regions, the duration that each radar has observed that region. Next slide. We count the storms within those overlapping regions. And then next slide, we normalize by the duration to obtain our final frequency.
All right. Thank you very much, Jordan. We'll move on to our next presentation by Tim Ropach, looking at a continental analysis again of Australia using environmental methods and looking at trends.
So many Australians, what's going on? This is my first in-person conference presentation since the pandemic. It feels familiar and also really weird. So my name's Tim Ropak. I'm going to talk about Continental analysis of trends for hail, and this follows on really nicely from Jordan's talk, so thanks, Jordan. I'd like to acknowledge my co-authors, Joshua Soderholm, Rob Warren, and Steve Sherwood. Now. Right, so hail causes a lot of damages in Australia. This is an image from 1999 in April over Sydney, and all these roofs at the bottom of the screen here are damaged, and the blue tarpaulins are there to cover hail damage. So this particular event had normalised losses of 5.6 billion Australian dollars. It was the most expensive event in Australia. It remains so, but the floods last year might knock it off. But from 1966 to 2017, hail actually caused greater insured losses than bushfire and floods combined. And you might know that Australia gets its fair share of both bushfires and floods. So it's really interesting that hail is really leading the damages, and it's so badly understood, really. And my interest here is to look at hail and how it might change with global warming. And so we wrote a paper last year which summarized the current state of knowledge on this topic. And what we found was that there are three changes that you might expect with global warming that could affect hail. The first is that a warmer atmosphere can take more moisture, and that can lead to more instability, so more propensity for the hailstorms to form, and perhaps larger hailstones in those storms because of larger updraft winds. The vertical wind shear is likely to reduce a little bit, but the story there is more complicated when it comes to hailstorms, because at the time the hailstorm might happen, the vertical wind shear might actually increase. And melting level height in a warmer atmosphere is going to be higher, so you're going to have more melting of hailstones as they fall out of the storm. And therefore, this could mean that sometimes all the hail melts to rain and you get no hail on the surface, or sometimes you might get a shift to larger hailstones because all the small ones melt. When we look at existing studies in Australia, we know roughly where hail occurs. So Jordan was just showing that it mostly occurs on the east coast of Australia. But there is this high uncertainty in northern Australia, and particularly the northwest, where satellite products like the one Sarah was showing, and also proxy products tend to get really excited and show that there should be a lot of hail occurring there. But because of the sparse population in that area, we're just really uncertain about how much of that hail is actually reaching the ground, or whether there's hail in those storms at all. And hail trends are really highly uncertain as well. They've really only been studied at a few locations in the southeast, and generally at point locations. So when we're looking at a continent of the size of Australia, we really have very high uncertainty about those existing, the trends that exist. So in this work, I'm using an updated hail proxy. What we did was we took a method that's commonly used where you use discriminators in instability shear space. So the way you generally do things is you make a plot, you put wind shear on one axis, you put instability that might be measured by something like CAPE on the other axis, and then you take your environment and you stick it on the plot, and you might say on one side of a discriminator line, the atmosphere is prone to hail, and on the other side, it's not prone, it's binary. What we did was we looked at proxies that have been developed specifically for Australia, and there's really only been ones by John. And we tried to make an updated proxy that deals somewhat with the overestimation of hail that can occur in the north of Australia. And what we found was environmental conditions naturally have a latitude dependence in Australia. You have these high tropical regions where you have very high instability, for example, and also a high melting layer. So we tried to build into our proxy that change based on latitude. And as a proxy for latitude, we took the melting level height. So we trained this proxy using ERA 5 reanalysis data and hail reports from the Bureau of Meteorology. And we allowed our discriminator line to change based on the melting level height, basically as a proxy for latitude. And then we added extra conditions to try to reduce false positives in the north in particular. So these are extra conditions on lapse rate, melting level height, and lifted index. And we took an approach where we tried to define those thresholds so that we were removing as many false positives as possible without removing the true positives. and comparing them to other proxies in the literature, as you see here on the bottom right, our new proxy does pretty well, at least in terms of the high-Q skill score. And we also get a reduction of the false alarms in the tropics, and therefore an improved performance there. Now, in this work, I've applied our new proxy to reanalysis data. So this is ERA5 data from the ECMWF. It's hourly data at 0.25 degrees grid spacing, and I'm using the pressure level data, and I've subset it to the Australian region. And what I did was I took that data at 06 UTC, so that's mid-afternoon on the east coast of Australia, a bit earlier on the west coast, daily for 1979 to 2022, and I applied the proxy so we could see whether we got hail-prone atmospheres in the reanalysis data at those times. And then I'm comparing to radar data. So as Jordan did a great job of explaining, there are 76 radars in Australia. I've done a much more simple approach than Jordan's work in the last talk. What I did was I just took mesh. I used a very simple threshold of 21 millimeters. There's obviously room for improvement here. But what I did is I took the hours between 3 and 9 UTC, regridded those data to 0.25 degrees so that it matched with the ERA5 data, and looked for mesh exceeding that threshold. And here are the results from the ERA5 hail climatology, showing from 1979 to 2022, and the map of Australia at 0.25 degrees resolution. So you see the east coast there is lighting up as you would expect. This is where we know we get hailstorms. In the north of the country, there's not a lot. That's partly because of our thresholds on the proxy that we've added. And now comparing to the radar data is more spotty, of course, because we have less coverage, but we see that we agree roughly with the East Coast. And one interesting spot that I'd like to point out here is this Gulf hotspot, which seems to appear in both the proxy and the radar analyses. Now, whether this is real hail that falls on the ground is yet to be seen. There's very small population up there, so we need to look more into this. But I think it's interesting that it comes out in both the radar data and the proxy data, where the proxy takes into account the northern overestimation. When I look at the radar detections versus the proxy detections to try to work out how often a hail-prone atmosphere actually turns into hail, this is the map that I get. And we see that on land, radars detect hail roughly 10% of the time that the proxy indicates that there's a hail-prone environment. So someone called this a conversion factor. I like that term. So it's roughly 10% over the land and less over the ocean. This is the main result. This is the trend analysis for the continent using linear trends on monthly anomalies over that entire range in the reanalysis data from 79 to 2022. And here I've put a dot where there's a significant trend that's looking at the p-value on the linear trend, and also using a Durbin-Watson test to test whether there's autocorrelation in the residuals. So it's interesting to see here that most of the northern part of the country, we're seeing negative trends, but there are some positive trends in hail probability or probability of hail-prone environments. And interestingly, they're over some of the major cities. So I'm going to show, zooming in now over some of the major cities that we see. So there's a map here to show you where these cities are, if you're not familiar with Australia in great detail. But what we're seeing is increases over Perth in the west, over Sydney on the east coast, Canberra inland on the east coast, Melbourne, not a lot of change. Hobart, we're seeing increases. That's on Tasmania, the island to the south, and in Adelaide, not a lot of change. One thing that's really interesting here is that Brisbane is showing really different trends between summer and winter. So Brisbane's on the northeast coast or the central east coast. We're seeing that there's a negative trend in summer. We're getting less hail-prone atmospheres in summer, but more in the winter months, both of which can show significant trends. And in Darwin, right in the north, we're seeing reducing hail probability over time. So this is the first time that we've had hail-specific hail-specific trends for the entire continent of Australia using a proxy. Now, what about what is actually driving these trends? Here are maps showing basically the ingredients that go into this proxy. We've got the proxy on the top left, then across the top row, indicators of instability, CAPE, SIN, which is the inhibition in the atmosphere before you get a hailstorm, the lifted index, the lapse rate, temperature at 500 hectopascals, and the melting level height. And in the bottom right, the shear, which is just the difference in wind speed between the surface and 6 kilometers aloft. And just looking at these plots, you can see that the areas that tend to line up with where the proxy is showing trends are the ones that also show trends in the instability factors. So the CAPE field, the lifted index, which is also a measure of instability. The other ingredients that go into this proxy are showing much more uniform trends, so that the temperature is increasing as you would expect. The wind shear is generally increasing, but when I look at the proportion of the proxy trends that are actually explained by these different ingredient trends, which are shown in the top right here, what we see is that the wind shear is actually playing a very small role in those trends, and what is really driving them are the instability factors. I've compared these trends to radar data using this much more simple radar data set than what Jordan showed. So what I've done is I've taken the radar data, I've aggregated it over the radar domains for land points only, and then I've subset those to the 33 radars which have at least 10 years of data, because all of these radars have different data lengths. And to try to compare apples to apples, I've taken the same points from the proxy data set, aggregated them in the same way, and tried to find the trends using exactly the same points. And you can see that there are some matches here on the East Coast. We see positive trends in some of the similar places. We see negative trends on the West Coast in similar places. It's not showing very well on the screen. But there are some differences. You might be saying, well, what's happening up in Queensland on the northeast coast, where the radar data is showing negative trends, and using the same points, we're seeing positive trends out of the proxy data. And I think partly it's because I'm using this simple method to look at radar data, so I could substitute in Jordan's radar data set here to see how they match. And also partly I'm using ERA5 at one particular time only, and I'm looking at radar data over the whole day. So I'm still not comparing apples to apples when I'm doing these comparisons. And one of the next steps that I want to do is to really compare exactly the same things, to have a backup for the proxy trends to see that we're seeing the same thing in the radar data. So to conclude, the hail hazard does seem to be changing over time in parts of Australia, and I think it's driven mostly by changes in instability and not so much by wind shear. In future work, obviously, I want to look more at the radar data, and I trust the radar data more than the reports in Australia. The reports tend to be biased towards population centres, and people are not super good at estimating hail size. And I'm really interested also in using machine learning to try to get into some of these predictors. At the moment, I'm only using instability and shear. It would be really interesting to use machine learning to pick the predictors that have more predictive power. And then, of course, I'd like to look at model projections to really look into the future as well. So with that, I'll conclude. Thanks very much. If you have any questions, I'd be happy to take them.
So apologies to the folks we've had online. We're going to try a slightly different variation to make sure your questions are actually getting through the presenters. We were getting questions in the chat that weren't getting conveyed forward. So if your question gets preempted by someone online, don't feel offended. We just want to make sure that they're getting a chance to participate as well. So Ian, do we have any questions from the online? No. Okay. So we'll start off with. That's you. Yes.
I'll try and be brief. I grew up in Mossman, go Wales. It's great to have all these Aussies here. I'm curious if there's an inverse relation, especially along the Sydney-Canberra corridor in the subtropical region, between increasing global temperatures, particularly in that area, and precipitation, either inversely correlated to hail or positively correlated to hail. Frequency and intensity based on precip and rising temperatures. Thank you.
I haven't looked at correlations between trends in rain and hail. So I'm not sure I can answer that question about whether there's an inverse relationship. But this study is showing that there seem to be increasing hail frequency. I haven't actually looked at hail size. So I'm looking at hail frequency, and in that corridor, it does seem like we're seeing increasing hail frequency. And we're also seeing, in terms of rain, the extreme events are increasing in that area as well.
Matt?
And really nice work. And actually, this is probably a question for all three speakers and maybe something that can be continued into the coffee break. Jordan, if you want to stay up even later, maybe we can have you zoomed in as well. So it seems like whether it's satellite-based proxies, radar-based proxies like MESH, or these environmental proxies, you're looking at things that are basically proxies for storm depth and sort of how tall the storms are. We know that doesn't really correlate well with hail. So are we going about this in the wrong approach? If we're comparing radar imperfect proxies to environment imperfect proxies, for example, they may agree, but it may not be the right way to go. So should we rethink the way we're doing this?
Yeah, I think that's a really good point. We might get more to this in the panel discussion, but there is this disconnect between the proxy and what we actually see on the ground in terms of we can easily see whether an environment seems hail prone, but whether it actually produces hail is a really different thing. And I think when we're looking at these, so this proxy, for example, is only looking at 2 variables. And my last point there where I said machine learning, I think that's where that can step in and we can look at more variables that might have more predictive power in terms of actual hail on the ground. I agree. You mentioned storm mode the other day. I think that's a really important one we should be looking at as well.
Just a second, Eddie. Do we have anyone online, Ian, or?
Not right. Oh, got a question from Conrad Ziegler online, but got to the response right there. So we're all good, John.
Okay. So I think Eddie was next.
You could look at sounding data over time to see if there's been a change in the melting layer height.
Yeah, agreed. The points where soundings are taken in Australia are not super close together, so there's a representativity problem there, but yes, that's something we should look at.
Also doesn't help, they sample at 00Z, which is 11 in the morning, daylight savings time. Kelly.
Kind of related, I was going to ask about, have you considered looking at storm mode, but then also things like, CI, because if we can't initiate the storms, and there's obviously going to be a change, or even just low level shear, because we know a lot of that actually gets infected, the momentum gets infected up into the storm and where, the core region of where the hail is growing. So I didn't know if maybe, the proxies take us so far and maybe kind of looking at some of the smaller mesoscale and storm scale processes might kind of make the connection a little bit more clear.
Yeah, I think that goes back to we should be using more variables. I think that's right. Yeah.
Andreas?
Was wondering if you see any indication that urban climates also impact the hail climatology. Like you have pretty big urban centers here that get hailed on. I know from the observation, it is a really pretty critical, like very difficult to answer question, but also a critical question to look at.
Yeah, absolutely. I mean, there's a huge heat island effect around Sydney. In Western Sydney, we get a massive heat island. It would not surprise me at all if that had an effect. But for example, in this proxy, I'm using 30-kilometer resolution data. It becomes difficult to quantify that effect, but it wouldn't surprise me at all.
Hey, John, we've got one question from the chat function from our virtual attendees. Tim, the question is on the ERA 5 data used as a proxy. Are those mean values? And the question was, worried about not seeing much going on in Central Australia. Is it due to fewer population there or just really not that much activity in general from a physical standpoint?
So when we're looking at the ERA 5 data, no, they're not mean values, they're hourly values. So I'm applying this at hourly time steps, so they're the values each hour. In terms of Central Australia, when we're looking at this map where there's trends, that's not affected by population density because the ERA 5 data covers Australia evenly. So I think it's more that there is less storm activity there than in the other parts of Australia.
All right, we will wrap up the session, this part of the session there. We're going to have the morning break now for the next 20 minutes. So we'll resume at 10 Mountain Daylight Time or 20 minutes from now. Okay, so good morning. My name is John Allen. I'm an associate professor at Central Michigan University. I'm going to be moderating today's panel. The panel is entitled From Climatology to Climate Change, the Changing Picture of Hail and Hailstorms. So it's in tying with our theme. We have 5 panelists. We have Dr. Susanna Moore, who's a deputy group leader at the Institute for Meteorology and Climate Research at Karlsruhe Institute of Technology in Germany. We have Dr. Tim Propach, who is a lecturer in Climate Change Research Centre at University of New South Wales, who you've heard from it just earlier. We have Dr. Victor Gensini, who is Associate Professor at Northern Illinois University. We have Dr. Andreas Preen, who is a project scientist at the National Center for Atmospheric Research. And we have Dr. Sarah Bang. So today's panel is going to try and touch on some of these talks from the session. We're going to try not to steal Victor's thunder too much and ask him too many questions about that. So let's try and avoid giving him a chance to talk about it. And we're going to start off with some individual questions and then move to some questions from the audience and from online. So we're going to jump straight into it. And I'm going to throw this one to Tim, given he's recently done a review on this topic. In a nutshell, where are we on the understanding of climatology and climate change for hail and hailstorms globally? What is driving these changes?
So we have broad indications of how things might change and how they might affect hail, but we have really high uncertainty across the world, and most of that's due to geographical differences. So what's driving the changes? There's 2 main things that I think are driving the changes in instability. So that's driven by the atmosphere being warmer and holding more moisture. And changes in the melting level height. So that's driving more melting of hail as it falls, a reduction in the small hailstones, and possibly a shift to larger hailstones. So the really broad indication that we have is that we might get less frequent hail on the ground because of this greater melting, but that when it actually happens, it's going to be more severe. That's the really broad indication. But there's really large uncertainty. And if you look across the world, first of all, there's many regions of the world where we have no idea what's happening because there's no data. Other things are, if you look across the world, you can get different trends, even from stations that are very close together. If you do trend analysis and your time series is short, then you can actually get opposite trends, even from stations that are a few kilometers away from each other. So we do kind of have a very broad indication that perhaps there's a reduction in hail frequency in East Asia and perhaps in the States or in North America, and an increase in hail frequency in Australia and in Europe, and a generalized increase in severity. But there's a really high uncertainty, and that's why the IPCC, for example, is not putting down predictions for this. It's because of that high uncertainty.
Thank you, Tim. Susanna, taking a step back, and something that Cameron alluded to earlier, many of the processes we're hearing about for hail are very focused on the storm or the actual hail growth processes themselves at this workshop. But we really don't look as much at large-scale processes, at least in the United States. To what extent do you see large-scale processes being important for hail in the current climate or under a changing climate?
Large-scale process or dynamical process, respectively, are really important. And I think we are currently at the beginning to understand these processes in relation to the thunderstorm and hail frequency. And with dynamical process, I mean all the aspects which are related to mid-troposphere flow situation, weather pattern, weather regimes, or also the location of the jet. And for example, in Europe, we observed that in Europe we have a specific weather regime. It's called Scandinavic blocking. And the Scandinavian blocking is a persistent and quasi-stationary flow situation in the mid-troposphere, and it's also correlated with jet dynamic. And when we have these weather situation or this weather regime, we observe that there is a perfect synoptic setting for the thunderstorm and hail development. And especially in combination with the location of the jet, we observed that in this situation, a higher or a deeper vertical wind shear, and this help or just generates more, or it enable more severe thunderstorms, which producing bigger hailstones. And when we're thinking about climate change, this aspect is not really taken into account. Mostly we have a more grid point thinking, and all these weather situations are not really taken into account. And so I would say, or finally, I would say that it's really important that we not only consider as a thermodynamic processes such as instability or moisture content, and it's really important that we should investigate, especially in the context of trends and the future climate. We must better understand the correlation between this dynamical process and the thunderstorm and hail frequency, and how are the changes in these dynamical situation, and what is the influence in each country. And yeah, it's for me, it's a really important question at the moment in Europe. And I'm already discussed with Tim some minutes before that we must share. It's important also to investigate in the other countries. And I think this aspect is not good enough addressed at the moment.
So to Victor, we've heard a lot about discussion of trends, and we're thinking also in climate change context. We've heard a lot less about climate variability in relation to hail. So where we take those trends, particularly if we're looking at short records, could have adverse effects if we have large climate variability within it. Could you share your thoughts about what we know about variability as it relates to hail, and what research is needed to address these intra to interannual scales, both in the present and future?
Yeah, whoa, hello. The variability is obviously really important for the insurance sector, right? Variability equals volatility. Just more broadly first, Sarah's excellent talk globally, and then we had two great talks on Australia. If we can't get historical right, or we have a lot of uncertainty about historical, that obviously creates big challenges for future projections. Tim's comments about instability and wind shear are critically important, but what if you don't have a storm? And so another missing piece in the environment is convective inhibition, right? Where are the temperatures warming in the profile? Is it elevated mixed layer temperature, which is obviously going to increase convective inhibition? And so Matt Cumgen's comment about, are we approaching this the wrong way, really resonated with me. And I think another possible avenue here is to use modeling. And so if you have some money, you can run some high resolution drive ERA5 reanalysis, provide initial and lateral boundary conditions, and just create a synthetic 20, 30-year climatology of hail. I know people are working on this, right? And yes, it's not observations, but at least it's a model proxy of explicit, for example, hail scheme, AFO hailcast or something like that, right? That can, of course, then help verify or perhaps disagree with your environmental perspective. The thing about variability, though, is this year and last year, a great example. We're in 2 years in a row of record low hail counts and frequency across the United States, and yet the insurance companies are still knocking at the door saying, "Hey, losses were really bad." So what is that saying about exposure and other things, other factors outside of climate change? But for example, we're going to have a double La Nina year. How many of those do we have in the data set? What kind of climate variability and jet stream patterns are that going to drive? They're then going to alter the convective profile. These are all questions that we're going to need basically GCM style modeling to understand the tropical forcing specifically. So in hail, when we're looking ahead, it's typically tropical convective forcing that's driving that variability. But we still have a lot of work to do.
Okay, so Andreas, having you up here is great because we can ask the question about melting, given you've done some recent work on this topic. So there's been a lot of discussion about the role of melting and frequency, and I think that Tim sort of alluded to what this problem is, right? Small hail melts more. How does it change for overall frequency? What are your sort of thoughts on this problem?
Yeah, I think the first thing is that the increase in the melting level height is one of the most certain things we know about how climate change will impact hailstorms, because we really have observational evidence. We theoretically know or understand why this is changing, and we see this in models as well. So we have multiple lines of evidence. Andy Heimsfield and I, we looked at this globally using radio soundings and also reanalysis data sets. And what we saw in the past 40 years is that you had approximately 30 meters per decade increase in the melting level height over land globally. This relates approximately to 200 meters per degree Celsius warming. So that's quite a bit. So if you think about maybe we get 3-4 degrees warming in the future, that's quite a large change. And this definitely has impacts on thunderstorms and hail. Where we see hotspots is North America, like tropics specifically, but also North America, Eastern North America, and Europe had very high increases in melting level heights. And this might very well be related to climate internal variability. So this is also what we don't really understand, what is our hotspots that we see and how those trends will continue into the future. I think like we heard a lot of discussions about this tropical and subtropical environments, but this is really important because our environmental proxies or radar proxies that we use are not really working well in these environments. I think there's, as we heard before, there's definitely something missing, some knowledge gaps that we don't understand how an increase in melting level is changing hail risk at the surface. My personal opinion, like we really change the clouds themselves. We have more liquid in the cloud, less frozen. The frozen piece is shifted upwards, and like this is not only changing the area where the hail is growing, but also wind speeds are higher up there. So there's really complex interactions, and these clouds are changing in very complex manners that we don't understand yet. So more research is really necessary from multiple lines to understand how this will impact future risks on hail.
So Sarah, pulling on one of the threads you talked about in relation to the length of satellite climatology, how long do you think it's going to be before we can sort of get maybe some trend information out of that? Are there new data sets that we can perhaps leverage to actually use satellite data to get maybe a more global picture of the trend, or maybe even just validate for periods some of these other approaches?
That's really tough. I mean, I think it just depends on what you are comfortable with publishing. Right. So the climatologies that you saw, they only go back to 1998. Is that long enough to establish a trend? The similar sensors have been in space since 1987, but once you go before the TRIM era, the resolution is, very severely degraded, and even some of the channels that we leverage are missing. So to the point where, I would want to get to a place where you would feel very confident in the robustness of your climatology, right? You're not having people coming up to you and saying, what's going on in Northwest Australia? So, to the point of where what you would call a trend, maybe in an era, if, you had a very confident geostationary parameter for these things, where you're not working with satellites in low orbit that are just getting snapshot. I keep my fingers crossed every day for geostationary microwave, but it remains a carrot off in the distance. But that, I guess I would say, as long as you would feel comfortable with assessing, I think that's going to depend on your industry, your reviewers, and your funding source. And then I guess the confidence in the instruments that you were using to build it, along as a trend.
I think it's a very good question. According to the literature, it's anywhere from about 12 years to about 40 years, depending on what's reliable and whether it's a climate reviewer or a weather reviewer. So moving to a question maybe that Andreas and Victor can talk about. Both of you are involved in projects looking at dynamic downscaling and using this for current and future expectations of severe thunderstorm processes. To what extent do you see these playing a role in improving our understanding of hail?
What assumptions should we be challenging? And what opportunities exist for us to improve projections of change using these?
Sorry, want me to? Okay. So yeah, in the literature, when you're trying to answer this question, right, and you'll see this in my slide at 11 o'clock, you have the environments, right, which are all GCM driven, 1 degree by 1 degree. And then you have this dynamical downscaling, which is basically, numerical weather prediction, where you're providing initial and lateral boundary conditions to your regional model, perhaps a convection allowing model, right? They're computationally expensive. And so typically, if you look at the literature, you're looking at relatively small geographic regions, you're looking at relatively small time slices, you're looking at only one emissions pathway, and you're looking at one GCM input. And so they're all kind of one answer. And so I think the biggest challenge our community needs to address if we're going to move forward with dynamical downscaling for future projections is creating really a global convection permitting ensemble with explicit Hail microphysics if we're going to try to address some of these questions. But we're still pretty far off from that. And unfortunately, the groups that are kind of working on it are working on it in silos. And so there hasn't been, I guess, great collaboration in terms of model design, model experiments. There are groups that are collaborating and doing stuff, I promise. But it is a challenging problem, and definitely not one person can tackle it alone, given where we're at right now with computational expense.
Yeah, fully agree with what you said, Peter. I want to emphasize, for me, this is a really big deal to be able to run these kilometer scale models, because it really allows us to get away from this 100 times 100 kilometer grid cells and looking at environments, but we really can look into thunderstorms. Like they're still not perfectly resolved, but you see like there are large, deep updrafts, you have overshoots, you see how they propagate, and you can actually provide or get data at a scale which is meaningful to impact researchers or insurance. Like you have cities in there and you can see like, does this thunderstorm or this hail swath hit the city or not? So I think generally, I think this is a big step forward. I fully agree with Victor, like we need bigger ensembles. We really need larger domains and actually really coordination, because like we are guilty of this as well. I know that you are running these models over North America and we don't coordinate very well. We should do this more in the future. But I think this is really a very interesting research area that will allow us to better understand how hail is changing under climate change conditions, and also how climate internal variability is affecting those things.
Okay, to Susanna, Tim, and Sarah. A problem we often see with research, and this actually speaks to a point that Victor raised about silos. Different regions progress at different rates, and whether that's a result of the data available, the personnel, the resources and equities, or even parallel approaches to inquiry. Thinking globally about the state of knowledge, where do we need to improve our understanding? Where do we need to better share our insights? And how can the attendees of this workshop contribute to broaden the global hail community, whether researchers or stakeholders, to tackle these problems? And pie in the sky is fine.
Yeah, first of all, I think it's perfect that we have these workshops here and also in Europe. That's mainly focusing only on hail, the topic of hail, and it's really cool that we come all together and we can share our thoughts, can share our questions that we have for our specific country, and we can come back home with new ideas, and that's really cool. And so first of all, I would like to thank all the coordinators of this workshop here. But another point, what I think it's also important, that we should better understand the difference of the processes that drives the trend direction in the different countries. We know that there are differences between Europe and the US. We have in the Europe more the mid-mountain range, and in the US we have the Gulf of Mexico, the Rockies and the Great Plains. Yeah, we have different driver for the trends in the different region, and we have already we have already heard that some regions the melting level is more important, but in other regions I think it's instability. So I think it's really important that we better understand the difference between the different continents.
So I think I'm going to break my answer into two parts. You said, where are we missing knowledge on trends? So physically, where are we missing it? I think you only need to look at maps produced by people like Andreas or by Sarah to see that there are areas of the world with really where we expect to see a lot of hail, but we have no trend information at all. So I'm thinking of places like South America, Africa as a continent is very underrepresented in terms of trends. India, Bangladesh, these kinds of places, and the northwest of Australia that people have talked about as well. So physically, we're missing data in those regions. So to fix that, we need more data, more field campaigns, better proxies, better ways of getting hail information from satellite and radar, and so on. But then in terms of knowledge, what are we missing? And I think, and I got to this as well, talking about processes. Microphysically, there are still gaps in our knowledge, and we tend to look at different processes in isolation. I'm guilty of this as well. You know, I was looking at my trends and saying, well, is it related to CAPE? Is it related to melting level? But these things have an offsetting effect on each other, and you need to look at the whole picture to get a process level understanding of how one process affects all the others and how hail is going to be affected. So I think if we can look more on a process-based understanding level, that would really help in terms of our trend understanding as well.
So just these insights from panels, amazing. Out of the break, I was talking to a colleague who was saying that they weren't from an atmospheric science background, and that, you know, the way that I kind of skated over the really dense stuff was actually appreciated. And I said, you know, yeah, I mean, I could talk about backscatter coefficients all day, but at the end of the day, like we all deal in a very high impact, very human phenomenon, right? Severe weather. This is something that human beings on the planet that, you know, we have to live with and deal with every day. And, you know, so I try to tread carefully, because there are a lot of, you know, there are places in the world we don't have data, but I'm not necessarily an expert. And I would never want to purport to say that I know more about African hail than someone who lives there. So you know, the insight that I have gotten from colleagues and shareholders in other countries who, you know, they live this reality every day. You know, so when the colleagues in Argentina say, well, actually, you know, in our observations, they're much more. Not much more, but they're south and west of what you're seeing. I don't take that as an insult against my algorithm. I see that as a place that I think, okay, why is the passive microwave responding to hail further east? Is there terrain? Is there, you know, a diurnal cycle that it's responding to, something like that? So I absolutely agree, you know, with these knowledge gaps, but I also try to tread very carefully and not try to make any assumptions that, you know, my algorithm knows more than someone in situ from that place, because there is this, you know, there's a very human aspect of it to what we do.
John, can I make one comment? How many people are here from the insurance or reinsurance sector? Raise your hand. So you care about hail impacts on society, right? There'd be a few nerds of us, including me in the room, that would be here if hail didn't impact society because we want to study hail, but you're here because hail impacts society. We get these questions all the time: hail, climate change, hail, climate change, hail, climate change. It's a really cool question. There's a lot of uncertainty, but there's very little uncertainty that the population is going to continue to sprawl, right? And so the question of climate impacts is pretty clear. And that's something that I think we need to continue to, when you get these questions internal in your organization, insurance, reinsurance, whatever it is, and they ask you, it's easy to blame climate change, right? Because that's something far away, tangential, that nobody has to talk about. But what about your exposure? What about your footprint, right? And where are you taking on more business? Where are you not? And then you can put in the context of a changing climate. I don't want you to ignore the climate change component, because it's real, it's important. But I think there's plenty of literature out there that shows that, you know, the exposure piece is super important, and we can't forget about that.
Okay, so I see a whole bunch of questions from online, and I'm sure we've got questions in the room.
That's a lot of hands we can see.
And I'm going to throw the floor open to some questions, and then I'm going to pin down the panel right before the end with what they like the best. So let's start off. Ian, who we got first up?
For those virtual attendees, please put your questions in the chat. John, we actually don't have a couple right now in the chat function.
I do see a couple of raised hands. Caitlin, McBride, I think it is. Sorry, I can't see because of the angle. Both of them are on an angle. Would you like to unmute and just give us your question? Unless that's
Sure,
an old
can you
hand.
hear me?
Yeah, we can.
So back to the kind of climate change piece, you're saying use it as more of a tool in the toolbox, right? Not as a tell-all. Okay. That's kind of what I was alluding to too, but looking at where your exposure lies and where most of your premium lies and that type of thing to help drive decisions, but also take in climate change as a piece of that.
Yeah, if you're looking about, this from a loss perspective, there's certainly the physical risk piece. And if you're, for example, if your SCS models, your catastrophe models for severe convective are based on the last 30 years of data, that's going to be pretty obsolete pretty quickly, especially if you're not considering the current trends and future projections. But again, don't ignore the exposure piece. And it's really, again, it's pretty easy to blame climate change on that kind of stuff, but your footprint may be just as important, especially on a year like this year when we had relatively few. I would say this is a pretty poor year if you liked hail. If you were a storm chaser and all you cared about was hail, actually it was a pretty record low year for hail. And yet you could have had, depending on where your exposure was, significant losses.
Yeah, it's interesting that it was a lower year for large hailstorms, but I feel like, and we touched on this morning, that there were quite a few little or small hail-sized storms that are less trackable or traceable than the larger events. So we've seen a lot in places like Illinois, even that you maybe wouldn't expect, because it's not the central US where I'm from. And that was a little bit surprising to see more of that trend in those types of states that are not in the central US.
Fun fact, that might be an expectation of things like La Nina, but that's sort of beside the point. Let's open up to someone in the audience if anyone's got a question. Come on, the online people are doing all the work for us today. And do we have another online question?
Not in the chat. I thought we had another hand up. So if you're out there in the virtual space, if you want to unmute and ask your question, please feel free.
It seems that with respect to trends, we looked at trends in cape, trends in shear, and all the related parameters. But what I wonder is what the impact might be of changes in triggering mechanisms. So it is often fronts that triggers a cape, so that something can really happen. Did anyone look into that?
I'm going to throw this one to Susanna because I know that they've looked at it. I don't think that's really been done for the US to the same extent.
Yeah, in Germany we have the same question, but we have not the perfect idea to handle this problem. We didn't currently look at this, but maybe the high resolved models can help context. But we have the same, we have the same question, but we have no idea for good
and I think
for a solution.
I think there's really an issue there in this disconnect between the GCM and even these convective allowing spaces. For frontal resolution for that type of structure, you're probably going to have to be around about ERA5 resolution. Frontal detection algorithms work quite well at about 0.25 degree. So there's kind of this interesting gap that we really need the convective allowing models, but I think there's also a gap where maybe within the RCM space, bringing those RCMs just a little bit further down might allow us to resolve some of those large scale processes, which would allow us to start thinking of maybe a little bit more about those convective triggering mechanisms, at least in the context of fronts or other circulation features. So a question on the far side.
One problem is that not only the frontal systems are relevant. We have the frontal system, we have sometimes a cutoff, sometimes it's a local orography. So yeah, it's different, especially in Europe where we have the mid-mountain range and the flow converging zones are really important. I think it's in US, it's a more other trigger mechanisms relevant, but in Europe you have a really problem with local scale initiation process.
And those relationships change in retrograde regime that you're in as well, yeah.
What we looked like at the high resolution modeling that we do, we looked at dry lines in the US, which can also trigger convection, and we saw that those get more stronger in the future. So I think the high resolution models can definitely help a little bit to understand this.
Yeah, maybe it's not a question or maybe a comment or suggestion. I think having this workshop, one purpose for those workshops to connect the different sectors, so as the academia, research industry, and for the social impact and reinsurance insurance industry. I think we want to have some kind of a knowledge leverage at the very beginning, saying what's the level of details that you want to know from the industry side and what level of knowledge we can provide from our research side, and then identifying gaps that how do we actually get around or passing through to reach that level of information we needed, or maybe we cannot provide the details that ever wanted from the industry. So I might, because we kind of seeing the conversation going on sporadically, that's saying what capability we're able to provide now and what kind of requirements are needed that on the other side, but there's not a framework or at least a plan to try to make this happen or make this more kind of going forward smoothly. So just using this opportunity, trying to make that connection and forming some of those platforms and opportunities. So just probably a comment.
I think that's a great comment. Having spent a lot of time working with some of the folks from ASE and NIST in recent years and speaking to a lot of engineers as well as folks in the insurance sector, I think there's a little bit of an issue in the academic sector that we tend to silo ourselves off and we look at our problem. And I think Victor's point sort of spoke to this. There is a need to almost have a counterpoint to, say, Tim's review on climate change and hail, to actually say, well, what do we actually need to know if we're going to use this information? We really don't have anything like that. And I think it would be great if from this group, from this workshop, if we could come across and sort of say, well, these are where our needs are. This is the level of specificity we expect, because that may be what is needed to drive groups, funding groups, other groups involved to say, get more of these dynamic downscale models to resolutions that are actually relevant, that we can look at hail processes or microphysics or otherwise. I think that the more input we can have from the insurance sector, from the engineering sector, from anyone who is an interested stakeholder is a good thing, because it might help motivate and apply some of that research beyond just the interest.
I'm going to follow up on that just by saying, in the academic world, right, we live and die by funding. And so the private sector has funding, right? But if I go work for one reinsurance company or insurance company, I may be locked down with that insurance company. And so maybe revisiting the idea of a consortium, I think that came up in the 2018 meeting of, a pool of a team of researchers, a team of insurance companies or reinsurance companies that are trying to investigate these issues on their portfolio rather than siloing everybody off, if you really want to make progress.
We've got a question coming in on the chat side from our virtual attendees. This is from Isabel Greco. Given there's so much uncertainty and complexity, as we've all talked about here, how do we go about the science communication element? And this is actually one that is near and dear to me as well, especially to the policymakers as well as the general public who may not understand how the two things, whether it's exposure, the climate element, how they're all playing together.
The great thing about being a moderator is you have a panel to deflect questions to, because I could answer that one, but I'm actually going to throw that one first up at Victor.
Worse. Look, science communication is a big deal, and we like to sit in our labs and run our models and et cetera, but not a lot of us are trained in media interviewing. Ian actually does a really great job of this. I should let you answer this question. But yeah, communicating the basics in a fundamental way that, at the level of dinner table conversation is certainly helpful to non-experts. And then getting into the weeds when necessary. And when you have to get in the weeds, you need to get in the weeds, but you need to also communicate at a level that everybody else can understand, especially when you're talking to, know your audience, right? That's rule number, Ian's back there. Know your audience is rule number one.
Susanna, I know that in Europe, you guys have actually done, I think, a better job in some of that communication with stakeholders. Do you see, what are your sort of thoughts on this question?
Do we have contact? Yeah. we have contact more with stakeholders from the other side, but of course we have contact with the insurance company, and it's a really good cooperation, and they let us in our own research world, and we can do our own question, and we have very good data to our model calibration. Can I skip? I must thinking about this. It's a bit, yeah. It's a little. It's a tricky. Maybe it's a chat. Like, I'm not sure.
I think we can.
Yeah, of course we have a lot of contact, but yeah. No, sorry. I will skip.
That's okay. So I think I'm going to just throw this to a general panel question and give you each a chance to respond. If you could address one issue about our understanding for climatology, climate change, and hail science, what would it be and why? We'll start off with Andreas.
I'm trained as a physicist, so I think better understanding the basic physics, how hail is forming in clouds, would be really helpful. It's shocking that we're in 2022 and we don't know really how hail is growing in these clouds and why they get that big. So that would be very helpful also for the modeling downstream.
Susanna?
Most of the things are already said. The large-scale driver, but of this aspect that you mentioned, Jürgen, with how we can better include the trigger mechanisms in our statistical models. I think that here we should do some work.
Tim?
Yeah. I'm going to say initiation as well, because there's always this gap between a hail-prone atmosphere and whether you actually get hail on the ground, and it comes up again and again and again. We see it in the models, we see it in satellite data, we see it in radar, we see it in proxies, and then we have reports where there are actually people seeing hail on the ground, but they're few and far between, and they've got these problems. So if we could, and I'm not even sure it's possible, if we could actually pin down initiation and know whether hail was actually falling on the ground when it looks hail prone, that would be a massive help. That's my, if I had a magic wand, that's what I would do.
Sarah?
I would say I would like to get away from as much kind of geographic dependency as possible. A lot of times, we have jobs, we have to get products out, you can't just, you have to do your job, but there are so many things where you're introducing a scaling coefficient, whether something is over land or over ocean, or if it's in this regime or that regime, and that's not very physical, right? The thunderstorm does not know that it's on a different continent. All that matters is the instability and the moisture, the physics that are made available to it. It doesn't have a brain. It's going, oh, I'm an oceanic storm now. I guess I have to do this. So I really I like to get to an understanding of these physical processes and training of our algorithms that is as independent of its regime as possible and just gets to the available physics. That's my pie in the sky.
Victor?
So I dabble in modeling, but I'm an observationalist at heart. So I'll keep it simple. We need more observations. And we've had a lot of field campaigns dedicated to tornadoes. If there's any NSF reviewers listening out there, it's time for a field campaign dedicated to hail. We need more observations, period.
Yeah, I've got to agree on Victor's point there with observations. We rely on maximum size data. That in and of itself is seriously problematic, from everything from impacts through to anything we do. We need more information about the swath. We still don't have an idea of the swath. Hail and wind was a great point brought up this morning. We have no idea, right? There are a bunch of fundamental questions that we need those observations to get at. So let's thank our panelists. What do we think about that panel? And you're still stuck with me for the remainder of this session. Sorry. So a couple of general announcements. In the program, there has been a slight change. The icebreaker and formal dinner will be this evening. That is a change to the program. That you will see that on the online program. It has been updated, but that wasn't necessarily communicated through. And the Wi-Fi information, if you haven't found it, there is Wi-Fi available. You do need to go through a connection portal that UCAR provides. The information is in the back of your the program that is available online in the PDF. So let's now move into the last three talks of this session. The next talk is by Jiwan Fan, Dr. Jiwan Fan from Pacific Northwest National Laboratory, looking at the contrasting response of hailstorms to anthropogenic climate change in different synoptic weather systems.
Hi. Oh, this is loud. Okay, so I'm going to talk about the contrasting response of hailstones to anthropogenic climate change in different synoptic weather systems. This is a collaborative work I would like to acknowledge my co-authors as listed here, and particularly Yuwei Zhang, Jinyu Wang, Junhao Zheng, who were postdocs worked in my group. Severe convective storms, SCSs, produces hail, tornadoes, damaged winds, and torrential rainfall, which causes as much property damage and also even more deaths than hurricanes in the United States. The economic, is there a pointer here? Oh, okay. I was trying to, okay, good, can use. So the economic losses due to SCSs exhibit an increased trend in the past 2 decades. The level of understanding and our confidence in how SCSs will be affected by anthropogenic climate change, ACC, is the lowest among all of the extreme categories based on the National Academy of Science. This is particularly true for the southern hailstones type. For example, hail and tornadoes. Hail environment varies a lot, which poses great challenges for modeling and predicting them. So both in the literature, both decreased and increased hail increase was reported. So for the, in the central United States, hailstones occurs very frequently and also peaks in spring. And they are often associated with 2 different types of synoptic scale environments. Front systems, they are featured with the low pressure system and the middle level trough. So they're featured with strong wind shear and large storm relative velocity. The other type is Great Plains low-level jet. They, associated with the high-pressure system and a strong, extensive low-level moisture report. Sorry, I think yeah, my PPT doesn't project well in probably Windows. I made it in Mac, so there's some messed up here. So our science question is that how do the hailstones over the central United States respond to ACC? And do the hailstones associated with these 2 types of synoptic environments respond to ACC differently? So we selected 8 hailstone cases with 4 for each systems from the springs of 2015, 2017. Those covers different storm modes, score line, such as case 1.5 and supercell, case 6.8, and multi-cells 3 and 7. So we simulated those storms with wolf coupled with NSSL at 2.5 kilometer grid spacing and driven by RAP. The future simulations is performed by the pseudo global warming approach, PGW. I want to emphasize that climate perturbation is singular, was obtained every 6 hours, which means the change in the dialogue cycle was considered. So we also track the convective cells of the storm, use the rate of activity so that we can count this hail associated with the particular storms more accurately. So here is a little bit about the synoptic environment change. This is just the synoptic scale environment for the present day case. So for case 1, the synoptic for all 4 cases in the front system, we can see they are associated with the low pressure system. It's just the system, the position of the system is different. And then for all GPLG systems, they are associated with the high pressure system and a strong moisture transport into the North United States. So here we did extensive evaluation of the cases. Here I just show the hail evaluation with SPC report, which is in triangle, and then also the mesh report from Commoners group. So as you can see, the current climate simulations get the health was very well. This is actually one of the criteria we used to select the cases. We did not include those who we cannot simulate today. And here you also can see from current to future climate for the GPLG system, for the frontal system, we do see increased hail frequency and the size. Well, for the GPLG system, it's difficult to see the clear trend. So here is the overall differences, which you can, on the left is the difference, relative differences in percentage. So we see that the front type, for the front type, for all 3 types of systems, 3 types of hails, long severe, severe, and significant severe, we see very significant increase, particularly, sorry, this is very sensitive, probably should not use. So for the severe hail, we have over 110% increase. For the significant severe hail, we have over 140% increase in the front systems. While for the GPLG, you can see the increase is less than 30%. So the in contrast difference in differences. We look at the precipitation and the frequency, both in frequency and total precipitation. And you can see for different types of precipitation, weak, moderate, and heavy, the response between the 2 types of system are pretty similar, particularly for the heavy rain. So here I want to show a little bit in change in the synoptic scale features, because we're trying to explain why these 2 types of systems have different response. So for the front system, we use this single case to show the point. We see the overall, the geopotential height in the future climate become larger everywhere. But we do see the trough become stronger because the horizontal gradient on the trough become larger. On average, the increase by 5.2 for all average of all 4 cases. Well, for GPLJ case, we also see the geopotential height is increased as well, but the horizontal gradient on the ridge is not changed that much. And we do see the high pressure system push more northwardly. This makes the stronger low-level jet and the stronger transport of moisture into the central northern United States. Now, the pre-storm environment, this is showing here is the 2-meter temperature precipitated water, and cape, thin, wind shear, and storm relative velocity for front system and GPLJ. The major message here is that if we look at the surface temperature and the cap change, you can see the GPLJ system has much larger increase. This may infer that GPLJ storms would become stronger in the future climate. However, if we look at the thin and wind shear, we actually see the front system get stronger. So this may infer front storms may become more severe. So it's very difficult to get a clear picture why those two systems will respond to ICC differently based on pre-storm meteorological conditions. Well, when we look at the cloud dynamics, we see very different responses. Showing here is the updraft velocity and updraft width. You can see on average, there's a significant increase in the frontal system, while there's minimal increase in the GPLJ system. So the stronger updrafts would lead to stronger condensation and a stronger vertical transport of the cloud water, which will lead to more supercooled liquid, enhanced ramming, and leads to the larger increase in global and hail mass. This is what we see as well. And then the large updraft width would allow the hail embryos stay in the updraft longer time and experience more growth. This also explains we see much larger increase in the hail bulk size. Well, let's look at the supercooled liquid. So this is the supercooled liquid. You can see the increases is larger compared to GPLJ system. I forgot to say the dashed line is the relative change in percentage with the second x-axis. So this also contributed by a stronger transport across the melting level of the cloud water, which makes more supercooled liquid. However, we know that besides the stronger updrafts, another factor affected vertical transport of the cloud water across melting level is warm cloud depths. So the deep warm cloud depths, the more droplets will form and then fall out, less will be transported across the melting level to become supercooled water. This is what we see. Indeed, we see in the GPLJ system, the warm cloud depths increased much larger. And this explains, this contributed to less supercooled liquid. And the reason for the larger warm cloud depths is that we have much larger increase in the multi-level height in the GPLJ system, and then also slight decrease in the cloud base height. Then while the convection becomes stronger in the front system compared with the GPLJ system. So I didn't show the slides for the mesoscale change, which is convective initiation. In general, the convective initiation because the environment becomes more favorable for the front system. And here we show from the vertical velocity component, we show that the vertical pressure perturbation gradient PPG, which is the major reason leads to the stronger convection in the front system, while we only see very limited changes in all of the vertical components in the GPLJ system. So this stronger vertical pressure perturbation corresponding well with the stronger trough, the enhanced trough in the GPLJ system. So in summary, we see the responses of hail to climate warming depends on the synoptic scale systems. And the front system have much larger increase in the large hail, while the GPLG system, the increase is pretty minimal. And the two reasons is more significant enhanced convection and also updraft width. And the multi-level increase is also minimal in the front system, much larger for the GPLG. We do see the precipitation response is similar. This is because the precipitation mechanism is very different. The hail response, the hail production, initiation production, and the growth is more sensitive to the multi-level height, pressure gradient change, those kind of things which are more sensitive to a synoptic scale. So I want to also mention that by linking the ACC impact on hailstones to synoptic scale features that are easier to predict, this study can advance our knowledge of the hailstone predictability, which also can increase our confidence in the future projection of hail. That said, we can start from region by region because for each region, we have a much better understanding about the synoptic features and to gain more a better understanding. But many of you know, I come from a cloud microphysics or small scale. It does not mean that the small scale future doesn't matter. It's just the predictability can start from there from synoptic scale. We can gain better understanding. I stop here. Thank you very much.
Got time for a question or two?
Very interesting talk. I had one quick question about the Great Plains low-level jet impacts on the storms. Typically in the US, the Great Plains low-level jet occurs at night. And I was wondering if you looked into any diurnal cycles related to the hail growth potential associated with that.
Yes, that's a good suggestion. And from here, we actually, indeed, we look at the diurnal cycle change, which well, we don't see there's a significant diurnal cycle pattern change. So also we actually emphasized that because the climate change, future climate change singular is like obtained every 6 hours. We actually, I feel maybe still because we are not used the climate change singular for particular environment for that hailstone, because we still use 10 years mean, so that's why this is the uncertainty in there. But that's very good suggestion. Thank you.
Okay. In the interest of time, we'll move on. So thank you, Jiwan. Our next talk is going to be given by Vic Jensini, looking at how do severe hail occurrences change under future predicted climate regimes.
Great, thanks, John. I want to thank my collaborators. This really represents about 3.5 years of a modeling effort. The simulations that I'm just going to show today are based on a publication in Climate Dynamics. So if you have maybe specific modeling questions, I would point you to that paper. Be happy to chat with you after this session. One other request, there are some figures in here that have not gone through peer review yet and are literally only seen by probably 4 eyeballs. So if you do take any pictures or post them on social media, just ask you to be respectful about the fact that it's not in press yet. So, but we have some really cool new simulations, and it's based on the whole idea of dynamical downscaling. A lot of the stuff for GCM future projections have been things like analyzing significant hail parameter, large hail parameter from pretty coarse degree, 1 degree by 1 degree, say GCM output. The nice thing is there, you can grab a whole bunch of GCMs, you can do a nice big ensemble of environment. The issue there is you're not guaranteed to actually get the storm. right? The convective initiation issue that we were just talking about. Literature has been pretty clear that dynamical downscaling is relatively useful. Unfortunately, as we mentioned in the panel discussion, it's typically very computationally expensive. And as you'll see with our study, you're really only getting one GCM sort of RCM combination. So the whole idea here is you basically take coarse scale global climate model data, you feed it into a regional climate model. We're using WRF here, as I'll show you in a second, and then we can simulate, instead of GCM precipitation, we can get these realistic features like this mesoscale convective system that's propagating through our regional climate model. Just a quick primer on the simulations. We have a historical slice, which represents 1990 to 2005. These are continuous integrations over the water year, so October 1st to September 30th. And then we restart the simulation. So this allows us to send several jobs to the queue at once. And of course, these are, again, very computationally expensive and take a long time to process because our horizontal grid spacing is about 3.75 kilometers. We have two future slices. One we're going to call mid for mid-century. You can see the dates there, and also end of century. And for both of those mid and end of century epochs, we simulate using RCP 8.5, which of course is a pretty aggressive emissions scenario. And I would caution your interpretation of some of the maps that are coming up with 8.5, as there's been a lot of literature that suggests that may be a pretty unrealistic pathway. And the results that I'm really excited about are the RCP 4.5, which I'll show you today, kind of giving an idea of sensitivity to emissions and how explicit hail classification some of these CAMs. So again, there's a paper if you're more interested there, but the setup is over the entire continental United States. We have 51 vertical levels. We tried to set this up as close as possible to like the high resolution rapid refresh model. If you're familiar with operational numerical weather prediction, this is basically what we would call a convection allowing or convection permitting model setup. Here's your obligatory WRF configuration slide, but again, I'll point to you to the paper. One thing I will point out here for the microphysics people is that we are using Thompson Microphysics, and some of the hail stuff that I'll show you in a minute is using the hail max 2D parameter. So we're just looking at basically the hail microphysics classification. Other than that, spectral nudging, that's kind of important. You don't want your regional climate model to drift away from the GCM. So we nudge at a pretty large spatial scale based on some sensitivity tests and previous literature, the state variables. And we do that every 6 hours as well. So what do the simulations look like? They're kind of eye candy. This is an example of most unstable CAPE in the color fill. We're also relaying composite reflectivity. This is from the historical epoch, just a time slice. To give you an example of just kind of what these simulations look like at the convective scale, we're zoomed in here on what apparently is convection initiating on or near the dry line, and then you can actually see the westward surge of the dry line back in the evening once the sun sets. So it just kind of give you a scale that we are kind of looking at, basically operational numerical weather prediction data here. Not sure what's going to go on here. Hopefully this runs. This is just an animation. Oh. The output we have is every 15 minutes. So instead of looking at every hour, the delta T in the model is actually 20 seconds, but we're saving output every 15 minutes. This is an example of composite reflectivity with updraft helicity, sort of getting synthetic swaths, if you will, from the climate model data. This is just every hour, but you can get an idea of, your mind starts running crazy. We can run some tracking algorithms, right? We can do all kinds of really neat things inside of these simulations once we get this type of data. So I just want to present pretty quickly here 3 variables from the simulation. Here's sort of what we saved every 15 minutes. So we have kind of a candy store of data. First thing I'm going to show you is RefDCom, which is the derived composite radar reflectivity factor. So just the highest reflectivity value in the model column. Then I'll show you the results of updraft helicity max. This is kind of a proxy for rotating thunderstorms, so supercells perhaps, and also hail max 2D, which is kind of the new one. So the first here, composite reflectivity. If I had to sum up this paper, which is cited there in the bottom left, and this is a relatively new paper, really looking at cross RCP, so cross emissions pathways and cross DBZ combinations, what happens to thunderstorm days in the future? So using just derived radar reflectivity factor in the model as a proxy for convection. So sort of taking a really modeling-based approach, detecting these. The top row there are 40 DBZ days. So let me get you oriented. This is essentially the historical period average number of annual 40 DBZ days gridded at 80 kilometers. We have 50 DBZ and 60 DBZ. This is all from the historical slice. And then the middle column will be RCP. This is all for end of century, RCP 4.5 and then RCP 8.5. And so the maps on the right are basically just showing you the deltas, where blue is fewer days in the future and red would be more days in the future. So the sum up here is sort of, there's definitely a varying response to RCP. If you hit the emissions pathways pretty hard, you get this big delta signal of increase in thunderstorm days, mid-south, Midwest, portions of the Northeast. And if you don't hit it as hard, you kind of still see that same spatial signal. You do see a lot of decrease in DBZ activity across the Great Plains, which is actually something we've also been very interested in over the last 3 to 5 years. So that's radar reflectivity results. Again, that's published in GRL if you want to take a look at that. We have some new stuff that's in review at BAMS. I'm really excited about this. This is basically using machine learning to track the storms and what type of storms they are. So looking at whether or not the storm is producing rotation. So if you wanted to get an idea of the future of potential supercells inside of this CAM simulation, we can do some nice object-oriented tracking, look for thresholds of DBZ and updraft helicity. Updraft helicity is just a measure, vertical integral of vertical vorticity. So we're just looking for storm rotation. And the specifics are there on the right. Again, I don't want to bore you with time here of how we're doing this, but essentially I love this image. I love these cumulative frequency diagrams because they really say a lot about the annual cycle and what to expect. The historical line there is a little bit difficult to see, but it's in that light green color. This is just average annual UH track counts. So we're basically just saying how many of these supercell tracks do we have inside of the model in the historical period on average, in the future 4.5 scenario. This is all for that end of century. This is not mid-century right now. I'm not showing you any mid-century. The range, and then also the future 8.5. So you can see sort of this aggregate response of increase with increasing RCP in the cumulative annual UH track count. So it's basically just looking at the number of those UH swaths that we basically see and then summing them up over the CONUS. Seasonally, you actually see pretty small changes in the boreal fall and decreases in the boreal summer in total UH, consistent with some of our thoughts about how things will change seasonally, perhaps drying out in the central Great Plains in the summertime. Your biggest increases, though, are seen early on in the cool season, basically DJF, early on in the cool season, specifically February driving a lot of this, and big increases in March, April, and May as you go from historical to RCP 4.5 to 8.5. And then looking at the most intense UH values, let me orient you on this panel. This is also updraft helicity. This is just looking at the frequency, the number of times a grid cell hits UH greater than a value on the x-axis. And so if you look at those counts historically in the black, RCP 4.5 in the yellow, and 8.5 in the red, you see big increases in the cool season frequency of those extreme UH values. You actually don't see much change at all in the boreal fall, and maybe a slight increase in boreal summer in terms of this would basically be looking at like the intensity of the rotation inside of the model. All right, now to the new stuff. All right, so this is our mid-century looking at hail max 2D. I will caution you, this is not hail at the surface. This is maximum hail diameter from the Thompson microphysics scheme in the vertical column anywhere. This is greater than or equal to 2.5 centimeters, looking at the average number of days in the historical period in the top. How does that change as you go to RCP 4.5 in panel A? And how does that change to RCP 8.5 in panel B? So some pretty big spatial decreases across the Great Plains in that particular parameter, and some increases noted, kind of very similar to what you're seeing in sort of the DBZ framework. This is not gridded to the 80-kilometer values. You also see some increases in places where you typically don't get, right, severe hail at the surface. And so I think there's some, some microphysics issues again there that we can maybe argue over a beer about, but the decreases to me in the central Great Plains and the increases of what we're seeing in portions of the Midwest, Northeast, and Mid-South are pretty telling of a story that we're starting to see emerge in terms of the spatial shift in hail and tornado frequency. When you really hit the button hard, RCP 8.5, this is now for end of century slice, so 2085 to 2100. Same historical period on top. Same historical period on top. Now we have the RCP 4.5 in the bottom left, panel C, and then panel D would be like the worst case scenario by the end of the century, where we're looking at RCP 8.5 from 2085 to 2100. Again, these maps are just showing the delta in days. So the number of days, either more or less, blue less, red more, that we're seeing that condition in the model met. What about big hail? 4 centimeter or greater? Here's what our historical model climatology looks like. Average number of days with hail greater than 4 centimeter from our WRF historical period. Looks pretty similar to what Sarah had, only we're on a much finer scale. We're at 3.75 kilometers. This is basically like a WRF climatology of just this hail max 2D parameter. And again, there's some issues with hail max 2D that we can talk about, but for the most part, it gives us a first order look at our historical period of significant hail. And now I guarantee you want to see this map, right? How does sig hail change based on these panels? So top left is the delta in number of days 4 centimeter, mid-century 4.5. We also have mid-century 8.5. Bottom left would be end of century 4.5. Again, delta in days, fewer days here, obviously, because we have fewer events. And the bottom right is, again, kind of the worst case scenario, end of century RCP 8.5, looking at, again, number of days at the model grid box level, so not even aggregated, just looking at the number of days with that exceedance of 4 centimeter. So if you're in the insurance sector, you probably don't want panel D. Before I end, I want to give you some GCM context, because the GCM is the driving model for this WRF, right? And so it might be pertinent to ask, how does the model environment change as a, you're showing me these cool downscaling maps, but what does the actual GCM that you're using kind of show? And I'm going to start with tornadoes, because this is a really interesting study. I get this question all the time from the media after big tornado events. Mayfield, the derecho that went through last December. What is the future of tornadoes? What is the future of hail? And again, I echo Tim's comments of uncertainty, but here's a time series from the GCM looking at the number of days on average in the CONUS where you exceed a significant tornado parameter value of 1. Basically what we're saying is there somewhere in the CONUS that's favorable for a tornado occurrence? The blue line is history, and then we can, since we have the GCM data, it's very coarse, this is really easy to look at. We can look at all the way out to 2100 every single year. For tornadoes, the 4.5 response is an increase, but it's not certainly anything. I think the variability issue might be bigger than the mean increase. Look at what happens when you go to 6.0, 8.5. So some pretty significant increases by the end of century in RCP 8.5 for tornado environments. Remember, we can't do anything explicitly in the GCM. We can only look at environments there. How about for hail, though? Oh, let me show you that spatially, by the way. So top panel is your history. How many days do you get favorable on average for tornado conditions? And then the deltas for, I can do RCP 6.02 because I have, again, just the GCM data. This is pretty easy to manipulate. So at least in terms of tornado environments, kind of across the board increase, and a lot of that increase is directed in the Mid-South and in kind of east of your traditional kind of tornado frequency regime. That agrees with some of the recent trends we've seen in severe convective storms, specifically tornadoes. Those of you who were on the Great Plains roaming around last year kind of realize that not a lot of tornadoes, not a lot of hailstorms in the Great Plains over the last couple of years. Is this climate variability? is this, are we in some sort of new normal? But I want to show you quickly, look what happens in the GCM with hail. You saw that nice tail upward with tornado environments by the time we got to 8.5. This is a different parameter. This is the significant hail parameter now instead of the significant tornado parameter. Look at the time series for 4.5, 6.0, and 8.5. That looks pretty flat to me and actually a little bit muted in terms of the variability by the time you get to 8.5. But remember, this is the CONUS average. So could it just be that one area is getting really hot and another area is getting really cold in terms of our spatial locations of favorable environments? And the answer is yes. You're seeing a big decrease in this particular GCM in the number of favorable hail environment days in the high plains, specifically in the summertime, and an increase in the number of, again, favorable environment days in really portions of the Mid-South, Arklatex region, where we've had several damaging hail events in recent memory. But that big decrease it was very interesting across the summer. It is kind of consistent with a lot of other GCMs that do have a pretty, I would say stark drying trend across, the high plains become a more arid desert-like climate where, the historical environments here, ship days, again, this is just the significant hail parameter, look pretty realistic. But again, we talked about this area, if you are, let's go to 8.5 across Texas, ship is getting more favorable in the GCM, but there's no storms there in the RCM, right? So I caution always, when you're using these environments, it's very, very tricky. I think across Texas specifically, there's a big issue of convective inhibition where the model is just getting hotter and hotter and hotter in the mid-levels and you're not getting convective initiation. To be continued. And finally, I want to end my presentation. This is looking at strictly at RCP 8.5. I want to underscore the variability theme. John asked that question in the panel discussion about variability. Even in the worst case future scenario, it is not a linear increase through time. There is a significant amount of year-to-year variability. You're looking at basically the departure from normal of hail days, hail environment days, all the way through 2100. I just took a slice of every year and I just wanted to visualize sort of what does it look like. There are some really low-end hail years on the plains in terms of environments, and there's also some pretty high-end years in the plains in the future as well. This whole variability thing fascinates me. I think we could talk a lot about Ji-Wen's talk on regimes and what causes favorable versus unfavorable and how can we anticipate that. These are all questions that we just don't know the answers to. But I wanted to highlight here before the end of the talk this idea of variability, because that I hear from my colleagues in the insurance sector that is often one of the most important things that you're worried about is this year-to-year volatility, which of course just makes things kind of a pricing nightmare. So I'm going to summarize just by saying increases in aggregate SCS. We kind of looked at each of these individual hazards. We're just now getting at the hail kind of stuff. The variability is kind of concerning. The spatial changes are very interesting, especially depending on where your exposure is located. Right, an eastward, I don't want to call it a shift, but an eastward trend increases, in these types of events happening along and east of the Mississippi River obviously has huge issues for population density and losses. And there has been some work, but I think a lot of us at a community effort here. I'd like to hear your thoughts also maybe, again, over a beer about attribution science. I get a lot of questions from the media about attribution. Hurricanes, other hazards are way ahead of us in terms of attribution work, and I think we might be able to make some advances with attribution in the future. So I'm going to end there. Please shoot me an email if you're interested in collaborating, looking at the data. Again, it's kind of a candy store right now, and too much sugar is a bad thing. So we're happy to spread the wealth around. Again, this is resembles kind of a 3.5-year modeling effort. So thank you all for your time.
So definitely contact Victor via email or catch him around the workshop, or if you're online, feel free to reach out to him. Unfortunately, we don't have time for questions despite a very interesting talk. We're going to move on to the next talk, which is Dylan Reif talking about comparing US hail risk estimates using publicly available hail data to forensic hail data. While we're waiting, did anyone have a really pressing question for Victor they'd like to throw out there? Tim? Mm-hmm.
Great talk. It's really, the mind boggles at how many compute hours you must have thrown at those WRF simulations. My question is about drivers and whether you looked at the drivers for the changes in hail that was there, and maybe you could break down the drivers in terms of dynamic changes and the thermodynamic changes.
Yeah, good question. I've only really done that from the GCM perspective. CAPE is driving a lot of those increases that you're seeing, and then decrease in wind shear is kind of the other thing. We haven't looked at like melting level and all the things that go into storm relative wind profile for a portion of the ship. The downscaling stuff right now is we're kind of getting into that. The issue is this is just as big as big data problem as it is kind of a computational issue. One WRF out file from our simulations was 2.5 gigabytes. So you multiply that, right? We're 15-minute output for 15 years. You know, we're talking petabyte total. By the time you condense everything, we can get it down to about 300 terabytes. We need help. So I don't have a good answer for you in terms of the dynamics of what's driving some of those changes. You know, there's a lot of stuff that you could do. I just don't have a great answer, unfortunately. Uncertainty.
Ian, I see a question from online.
We do. We've got two if we can get to it while we're working out the tech difficulties. First from Isabel again. In the larger hail size maps from the RCM, there was a lot of fine scale spatial variability. Her question is, are these differences, Victor, do you think significant or just artifacts from the simulations themselves?
They're noise. Yeah. Anytime I presented you the raw model deltas, when this goes to review eventually, I mean, we want to, it's kind of weird, right? You downscale to get the benefit of convection permitting, and then you have to upscale to look at the spatial changes. You know, typically that's done in the literature at about 80-kilometer grid size. That's probably what we'll end up doing. That's what we did for the thunderstorm day activity. But if you're looking at the difference between Chicago and Rockford or Boulder and Denver, you know, that's where you need to bring bootstrapping in, stochastic, generate these longer synthetic samples to get it. That grid cell level is pretty much noise. I'm more interested in those 30,000 foot sort of big spatial changes that you're seeing, which is kind of that, again, higher frequency east, lower frequency central plains, high plains.
I think we got this last one on the how computationally extensive are the model simulations, and I think you covered that. But that's Michael out there in the virtual space. If he has another one that wanted a little more detail about how computationally expensive these are, please throw that in the chat, Michael.
Yeah, so it depends on your methodology. If you want to take sort of a numerical weather prediction framework, you could use a daily reinitialization technique and then just throw 1,000 days at the job queue. But that's not good for climate modeling, where we want to hold on to soil moisture memory and we want to look at GCM level changes. We want to retain that information as long as possible. And so the continuous integrations require somebody to sit there, and when you run out of wall clock, you got to do a restart, right? And so it's just, it takes a lot longer. It's not necessarily that we couldn't generate these simulations in the matter of, you know, a couple months. It's just more of an issue that the way that we do it from a climate perspective takes a long time, and you know, we're still limited in the number of nodes, et cetera, that we have. So yeah, good question.
All right, thank you, Victor. Yeah, we're all good to go back to Stellan.
Hi, thanks everyone. Sorry about the technical difficulties. My name is Dylan Reif. I'm a meteorologist at CoreLogic, and today we're going to be comparing U.S. hail risk estimates using publicly available hail data, our radar-based estimates, and forensic hail data. So I'm speaking directly to the insurance in this presentation. So why is accurate hail size so important? One, we need it in order to understand the proper and potential impacts of an event, pre, during, and post that event. It leads to more efficient adjuster deployment based on storm severity and adjuster experience. And we all know that the response of a carrier can be drastically different for drastically different hail sizes. It also impacts your date of loss estimates. And so this study is motivated by the continual use of mesh or mesh-related products in the insurance industry, and to a lesser extent, publicly available reports. And so in this talk, we're going to examine some common sources of this information in terms of evaluating the hail risk directly at a property level. And so what are these three common sources of hail information? The first one's public reports, and this includes reports from the Storm Prediction Center, NCDC storm data reports, and those are commonly used, and we've heard about some of those earlier today. IMPing reports, and reports from social media and TV. Other ones are radar-based algorithms, such as the maximum estimated size of hail, or MESH, and the hail size discrimination algorithm, which is not as widely used as MESH in the insurance space. And then lastly is a forensic output, which basically combines both to create one final product. And CoreLogic's hail verification technology is an example of that. So some pros and cons of each are listed on the bottom. Public reports, they're very easily available. The problem is they don't have any, if at all, any form of quality control. The locations of the hail size and the hail size itself can be highly suspect at times, and it's not a gridded output. For radar-based algorithms, you're not dependent upon the public reports. So nocturnal biases due to people sleeping at night or sparsely populated areas is less of an impact. This is easy to automate. You don't really need people in real time to work on this. However, as we all know, accurate determination of hail size from radar data alone is extremely difficult, if not impossible. So that's where forensic output comes into play. Again, it combines the best of both. You have quality controlled public reports that you can use in conjunction with radar data to get the best overall path that you can possibly at the time. One of the problems, though, is you need a team of people in real time in order to actually get these paths to be accurate enough for insurance purposes. So let's just do a quick visual example of some of these problems with public reports. Let's hypothetically say that you want to estimate the hail risk at this dot, and these are the public reports that you have. I jumped the gun, but this is one of the hail paths that you might actually contour for this case. But let's take that exact same dot, and let's take that exact same public report field, and let's draw another path. And so one of the issues with the fact that public reports are not a gridded output is you can draw literally an infinite number of paths of the hail around these reports. And that's a problem when you're trying to estimate the hail risk at a location. That's where radar-based estimates come into play. And so MESH is popularly used, and it can help fill in the gaps for that. As we've talked about before in some of the earlier talks, MESH is an integrated value. It uses reflectivity from all tilts and knowledge of the freezing level on the -20°C level in order to calculate this. And there's some issues with this. One, it doesn't see areas where the height is below the freezing level, where you could have substantial reflectivity and actual hail falling. It also projects the data down towards the surface. So storm advections and storm tilts is also a problem, and that can cause path displacements. The original use of MESH was as a cell-based value. You'd have one value per that storm, but high-resolution data has turned that into a grid-based estimate. MESH tends to create underestimates when the freezing level is too low, when it's below 3 kilometers. And again, as we've talked about before, MESH was designed to use with most of the data from Oklahoma and some from Florida. And while that might not necessarily seem like an issue, and some of the climatologies that we just saw from Australia, it turns out to be a fairly substantial issue due to climate regions. So the outline of this talk, we'll do a quick overall of the climatology of hail. Again, since it's been widely discussed, I'm not going to spend too much time on that. And then we'll get into the analysis of the events. We'll discuss what we call potential events, and that's where property could be impacted by hail. Then we'll evaluate the risk at the property using the publicly available reports, MESH, and our forensic output from HVT. We'll illustrate the differences using these three methods, and then we'll summarize everything at the end. So here's some slides that we all know and love. The panel on the left is a radar-based climatology using MESH. And we can see that there's two areas of interest. We typically see our highest risk in the Great Plains, and we have a very notable hotspot in Southwest Texas. And while this is probably true, this does bring into the potential issues with MESH when you have the radar beam that's very far away from the radar. Your beam tends to broaden out, it tends to look higher in the storm, and you can overestimate the hail size of the surface just based on that alone. Radar beam blockage is another potential issue. If the radar is not seeing the storm, it's not going to show hail. And then when we shift to a reports-based criteria, and these are reports using NOAA storm data, we can see that the overall impact of the hail tends to be reduced in these regions. And this is due to predominantly population density. And sometimes when the hail occurs at night, it goes unreported because people are sleeping. Also, depending on where the National Weather Service office is, they will treat the public reports differently, trying to verify potentially more marginal risks. Weather Service office in Boulder may act differently than the Weather Service office in Orlando. And that does show up in the public reports. So for our hail verification technology, it's a forensic product designed to show the maximum hail size at a given location. We combine both low-level radar data and quality-controlled public reports in order to generate these paths in near real time. And we have a team of forensic meteorologists that reviews all public reports for accuracy in size and location, and the hail paths in order to ensure that we have accurate hail paths. So the objective of this talk is to show the differences between these three types of hail estimates, especially at the property level. And so for our methodology, we obtain SPC storm reports and storm data reports for a 10-year period starting in January 1st of 2012. We define any potential event as any day with an SPC hail report within a 50-kilometer radius from the location that we chose. We calculate mesh following the original formulation for every single potential event that we have. And then we generate what we call hail history reports. And that basically shows the maximum hail size within 1 mile, within 3 miles, and within 10 miles of a given location. And events with hail that was less than 3/4 of an inch within 3 miles are removed. And that's something that we've talked about is the impact of really small hail with high frequency, but we're not showing that in this one. And we've done the analysis on these properties since January 1st, 2017. So let's take a look at our potential events. We examined 6 cities in these 6 states. And not surprisingly, the states with the most potential events are going to be Colorado and Texas out of what we chose. And the other ones are Florida, Georgia, Pennsylvania, and Minnesota. So now let's dive down quicker and take a look at the risk at the property level itself. And so first, we again need to define the radius that we use to define the impact at a specific property. And so we're going to be using the 1, 3, and 10 mile radius. And we really want to focus in on the 1 and 3 mile radius. If the closest hail was outside the 3 mile radius, then we've removed it from the report. For the public reports themselves, we've doubled this radius from 1, 3, and 10 to 2, 6, and 20 because there are simply too few events that are captured by that original radius. And we want to make sure that we capture a fair number for a fair comparison. And due to the proximity of these properties that we've chosen to highly populated regions, and there's a large number of reports, we do consider our forensic analysis as the best estimate. So let's jump to Texas real quick. We picked a property near Dallas, Texas, and the 3 different types of estimates for our forensic analysis, we have 8 potential events within 3 miles of the property. Mesh had 7, and the storm data events had 11, and that was within 6 miles. But as we can see from here, there's really not a significant overlap among the events using all these methods. HVT did not have 4 that were included in Mesh, and Mesh did not have 3 that were included with HVT. And so this begs the question, what's the best way to go about this? Here's an example of one of the events from storm data that was not included in the other 2. We took the latitude and longitude that was listed in the public report, and we plotted it on Google Maps with a pin that you can see there, and it's just north of downtown Dallas. However, when we look at the intersection that's listed in the comments, that location is over 10 kilometers away from the actual report. So if you do not actually take the time to quality control the reports for size and location, you're going to end up either missing a bunch of events or getting a bunch of events that you don't actually want to impact that property. So which location is trustworthy? Now, let's hypothetically say that we want to have the SPC reports or the storm data reports capture every single event that's listed in the forensic analysis. Well, when we do that, we actually end up with twice as many events as actually occurred. And these extra events that we can see are the ones that are listed in red. And so if you were to try to estimate your date of loss to capture every single event, you end up with almost 1 false event per every real event. And this is summarized very nicely in this slide. So for the 6 cities that we have listed the 3x, 5x, 2x represents the radius that you'd have to use aside from the 1, 3, and 10 in order to capture all of the events that are listed in the forensic analysis. And then for every one of these real events, you get basically one false event. So public reports should be taken with a lot of caution. So now let's look at radar-based algorithms. We're going to specifically talk about mesh on this one. And so we've picked a property near Colorado Springs where our forensic analysis and our public reports indicate more than 10 events impacting this property. However, mesh only had 6 within a 3-mile radius. So that's a very interesting issue number 1. And this could be because mesh was not designed for Colorado. But when we take a look at exactly what happens around this location, so on the panel on the left, we have mesh that's outputted and plotted from level 2 radar data. And on the right, we have our forensic output from HVT. I've contoured the 60 dBz radar reflectivity factor in the black contour on the left and then the white contour on the right, roughly about the time it was impacting the property so we can easily see it. There's a couple of things to note. Mesh seems really toned down compared to the forensic output. And why is this? In fact, there are actually several public reports of greater than 2.5-inch hail across this entire region, and mesh only has about 1 to 1.25 of an inch of hail. And even in this void of LSRs, we were able to scour social media and find several reports that are between 2.5 inches and 4 inches in this entire region. And so mesh is clearly missing something here. And so if you were to try to use this to estimate risk at a property level, depending on where you are, you can have drastically different results. And so the forensic output basically combines a sophisticated radar-based algorithm with these public reports to try to get closer to the truth. And these last couple of slides that I'm going to show, really going to show and highlight the differences between mesh when you start to go down to finer resolutions. And so in this case, I've taken the forensic output and I've taken the mesh output and I've taken the common events within 3 miles. And this plot examines the maximum hail size within 1 mile. So the common events are going to be within the yellow circle, and we're examining the hail size within the blue circle. And when you get down to these fine scales, we can see mesh tends to underestimate several events, in part due to the problems with mesh, potentially path displacements. Mesh also tends to miss several events that actually happened, and we can verify these from public reports. And some of the more egregious examples are some that we've already shown in this example. When we start to look at the maximum hail size within 3 miles, so again, I've taken the common events between mesh and HVT, looking within the 3-mile radius. And now I'm examining the maximum size within that 3-mile radius. We start to see more of the traditional mesh overestimate that we know in operational meteorology. Some events still have a drastic underestimate, and that's related to storm information. But overall, when you're trying to look at the fine scale resolution, mesh is potentially problematic as well. And so our 3 main takeaways from this: if you just use public reports, your risk analysis is going to be misleading. Every hailstorm is different. Trying to translate large-scale risk into risk level down at the property is really difficult. Radar-based algorithms help. You can start filling in the paths to get more accurate information. But if you really want the best, you really need to try to use both. To have an accurate radar-based algorithm that properly combines quality-controlled public reports is going to be your best bet to estimate hail risk at the property level. And with that, I will stop and take any questions.
So in the interests of time and
that's one really quick.
Yeah.
Why is the insurance sector still stuck on using individual values, whether it's mesh or HVT, given the uncertainty in mesh and reports? And that's just one example of reports, by the way. There's so many other issues with reports. Why not move to a probabilistic framework, probability 1 inch greater, 2 inch greater, et cetera? That just makes a lot more sense when you have so much uncertainty in your data set rather than just using numeric categorical values, right?
Yeah, that's a great question. And the best answer that I can give is probably ease of use and ease of interpretation. It's easier to say this hail impact was 4 inches and people have set standards for that versus there was a 75% chance of greater than 2 inch hail. It's just, I think interpretation is probably the biggest part of that.
Okay, so we'll wrap up this session. Let's thank all our speakers once again.
And so we're now into the lunch break, and that lunch break will go until 1 MDT, or an hour and 18 minutes for those of you online and in different time zones. And so we'll see you all back then.
Now it's on. Woo, thanks, Kelvin. All right, just a couple announcements before we start our afternoon session. Couple things. After dinner, we do have a shuttle running between here and the Hyatt. So if you need that, that'll be leaving here this evening, 7:30 p.m., but also in the morning. So 7:30 a.m. for those at the Hyatt coming over here. We do have the shuttle running. That's one of our announcements. For all of our speakers, especially for tomorrow and Thursday, please get your slides uploaded. That's how we make this work for our virtual attendees, which has worked very well so far. So please get those slides uploaded to our Google Drive account so we can get those set up for folks. So that's our orders of business, and we will start with a really cool talk that I'm excited about. Andy and Jerry Heimsfeld, their careers spanning together as brothers in our field of interest. And I will turn it over to Andy and Jerry. And I'm just really interested to hear you guys talk. I've had the opportunity to work with Andy for about the last 8-9 years, and it's been wonderful. And he is our fearless leader of this workshop too. So glad to have these two to talk to you today.
Thanks, Ian. Jerry and I had, come on up, John. We had nothing to do with organizing this talk. We prepared it, but we did not put it on the agenda. Someone else did, anyway. So just a little information. Jerry and I are in the same field, and our older brother, that's pretty interesting too. Anyway, we all went to the same high school. And I guess my thought is to really provide sort of a message at the end of this that might help people in the future. I wanted to be an accountant. I did all my math grading for my father, who was a math teacher, and I was accepted at one of the New York City colleges. And Jerry wanted to be an engineer and was accepted at Brooklyn Polytech. And here's just a picture of us, and we were interested in snow. I'm going to talk a little bit and then I'll turn it over to Jerry. So whenever there was a forecast of snow in New York City where we grew up, I was mesmerized by the thought it'd be snowing. And I always used to look at the New York Times weather map. This one's from December 12th, 1960. And just a little bit of detail. And so whenever there was a forecast of snow, here's an example of snow in our backyard. I always, in the middle of the night, would get up and watch the snow fall past the streetlights. I mean, I literally got up every half an hour looking for it. And so I was just really mesmerized by it. Now, I'll go back. So that kind of highlights my early interest. Even though I wanted to be an accountant, I was always interested in snow and always read the New York Times weather maps. Jerry, you want to? So Jerry wanted to be an engineer.
Yeah. So anyway, when I was a teenager,
you were 13.
13 or 14, I was interested in cars, and we actually built a car, my oldest brother and I, and so I wanted to be an engineer. And just to show you how involved, this is when I was about 13.
It was a totaled car,
and
you bought the car from the junkyard.
It was a sports car, Triumph, and we took it all apart and salvaged the parts, and then put together this car on the right, which was, it was a kit, but I was doing that when I was like 13 or 14, and this is what the car ended up looking like. And my oldest brother, who's now a doctor, he became a doctor, medical doctor. And but he did all the painting, and but we worked together. We built this together, and so I was basically interested in engineering and mechanical engineering, and that changed. And what's the next slide?
Well, before you turn it, you want to say that Jerry did the welding, and he welded a gas tank, and it blew up.
That was my brother.
Yeah.
So he survived, and
the house survived.
And I mean, the other thing, I was driving when I was 12 years old, the stick shift, and there's another story, but anyway.
So I was always interested in snow. This is an example. We built a snow cave, and I slept in that overnight, but I was truly interested in snow. Well, what happened between the senior year of high school and the first year of college? And this is the point we're going to make at the end. And so I received this letter. I don't know if you can see it. And there was through our high school, there was a letter passed around. Anyone who might be interested in meteorology or doing something like that. This was in April of my senior year, and June was the graduation. And so I applied. It was a position for doing basic research at a university in New York State, upstate New York. And so this is the letter I received confirming it. And that's from Vincent Schaefer. He was one of the discoverers of cloud seeding weather modification. And so this started me, I decided in May I would go to upstate New York to the State University College. And so just some of the detail of Vince Schaefer. What he did was he started this thing called the Natural Sciences Institute. And it was funded by State New York as well as Kettering Foundation. And so the idea was to get high school students kind of interested in meteorology. And there are many names of people who were in this program. So I decided to go. And so I liked it so much that in the middle of the summer, I decided I'm going to change the school I'm going to. And the important thing was that the person who was handling it, professor at Fredonia, really embraced the students and did terrific mentoring, which we never had. And so I participated in NSI for 3 years, and I liked it so much that I encouraged Jerry to apply. Jerry?
Right. So I was in it for 3 years as well. I went to different places, well, some similar to Andy. I think the unique thing was that they paid for everything, didn't have to pay a penny, and they took us to places that were really fantastic. Like Andy went to Durango, Colorado. I went to Whiteface Mountain, New York. Basically spent 8 weeks at these places, and what we did there was we basically did a science project. I think one of the goals of NSI was to have, young students like high school, junior year, senior year, put together some kind of instrumentation and then make measurements and then write a report. And it was a really good research exercise. I think it taught both Andy and I about doing research. So anyway, it also took us to places we hadn't been before, and like beautiful places. Flagstaff and Whiteface Mountain had cap clouds or mountain clouds, and their Flagstaff had rain every afternoon. They were kind of like natural laboratories, particularly Whiteface Mountain. And that was part of Vince Schaefer. By the way, he was co-discoverer of dry ice cloud seeding with Irving Langmuir, who was a Nobel laureate. And then he went on with Bernie Vonnegut to do cloud iodide seeding. Is that right?
Silver iodide. Yeah.
Silver iodide. Silver iodide, I mean. So, yeah, anyway.
Okay, so here's one of the reports that I did. So this just shows a little bit of detail. This was the Fredonia unit, and Gary was the professor there. And so it was actually expanded quite a bit outside of New York to many places. And so just a little bit of detail. And so we did receive a stipend, which was really nice, $100 plus room and board, and $200 if you were a high school graduate. So the reason why we're showing this is how we got interested in it, even though we were going off in a different direction. And this should be something that perhaps is done in the future. So this is Jerry's.
Yeah, so I did different project. This one was electric currents carried by rain. I did do some atmospheric electricity work very early. It's just a report I had, and ended up building this thing on the right to measure the currents in falling rain. And so next one.
And this is an example. Jerry and I were at Fredonia for 2 years together. And so this is a paper which I did, snow crystal types observed in snow squalls. And so we developed some instruments. Actually, Schaefer invented the process where ice crystals fall in a liquid plastic, solvent evaporates, keeps perfect examples of the snow crystals. So what we did was look at snow crystal types falling, and these were actually some of the lake effect storms that time were seeded. So we were interested in that too. And so this is an example lower. I won one of the Father McElwain Awards, the second place, and I'm on the lower left. And the reason I show this is because Peter Hildebrandt is in the top right. He was Jerry's boss and NASA for supervisor for a while.
And he was at NCAR.
Yeah, and at NCAR too. And so then I developed a automated process for replicating snow crystals. And that was, so it was an instrument we put out, and then it would capture entire period of snow. And so I went on to University of Chicago, Roscoe Braham on cirrus clouds. And then I went on to NCAR afterwards, Jer.
Yeah, so I went also to University of Chicago, and I worked for Dave Atlas for about a year until he left for the ENRI project, National Hail
at NCAR.
At NCAR. And then I went to the University of Oklahoma for a PhD. John McCarthy also worked at NCAR for a number of years, talked me into going there and work on severe storms and Doppler radar. And then I went back to University of Chicago, Srivastava, for a postdoc, and then I went to Goddard Space Flight Center.
And so I got into the hail business. I worked at a private company for a couple of years and then joined NCAR. And my responsibility was to try to figure out whether hail pad reports at the ground during ENRI, National Hail Research Experiment, were valid using radar data. And it was very interesting. It led to this, led to improved estimates of hail pad data from during the experiment. What we found, and I spent 2 years doing this, was that on weekends, the reports of hail contradicted the radar data. And it turned out that it was the students who were actually doing the hail pad collections. And it turned out that they were parting on weekends, and we could identify which students were parting and fabricating. It was fabricating. They were fabricating, and this is a randomized hail experiment, seeding experiment. So they were fabricating the data. And so I had all these hail pads and radar data, and I had to figure out, and I figured out pretty much which students were doing it. And it was always on the weekend in the evenings. And so after that, shortly after that, I did this paper on hail growth mechanisms in the Colorado storm. And I was working with Art Jameson. We did some dual Doppler radar work on hail detection. Schematic here using National Hail Research Experiment data, showing a feeder cloud, transporting embryos from the feeder cloud into a main updraft region, and pretty much tracing it out. And Jerry, you want to talk about that?
So this was when I first started graduate school in Chicago, and we had a field trip. Dave Atlas took his students to see the new chill radar. Looks old there, but that's what it looked like around 1971. CHILL is acronym is Chicago and Illinois Water Survey, and this was taken in Illinois when I was at the Water Survey.
It hasn't CHILL. CHILL is operating at CSU.
It's you're right. It's CSU undergone
State University.
Probably about 10 upgrades, but so this was amazing. Well, this was X and S band. This is about again 1971, and the reason they went to dual wavelength was that Dave Atlas and Ludlam around 1960 did hail calculations and said found a really good dual wavelength difference signature between X and S band, and so they took that idea. They received NSF funding between the two groups and built this radar. Well, the radar was way ahead of its time. The processor for the radar took an entire trailer. It was built by CDC, which is a predecessor of Cray, I think, and so it's like a mainframe in the trailer. Well, I don't think it worked that well, but they were able to get time series data. In fact, Art Jameson, who was one of my co-students at Chicago, wrote a number of papers on dual wavelength X and S band, and using those two wavelengths, you can get information on the size of hailstones, something we don't always have with polarimetric data. And so anyway, this was at a time when we didn't have computers, basically. We didn't have hand calculators. Barely. I think they came in right after this time here. And so everything we did was like 10 times harder than it is today, everything we take for granted.
Yeah. So then you did that.
So then when I went to Oklahoma, then I worked on severe storms. And I came at a time to OU when dual Doppler was really in its infancy. I see Howie there. Howie came right at the end of my PhD work. I mean, you probably would have been on my committee, if you came another year earlier or something. But and so I did dual Doppler analysis of the hailstorm, and there really were only two other people at NSSL working on dual Doppler, and so I did a lot of work on this era storm, and I did dual Doppler 3D wind fields, vertical velocities, and things like precipitation trajectories, and try to come up with a schematic or conceptual model of the airflow in the storm, and calculated things like tilting, into intensified tilting of horizontal vorticity to intensify the mesocyclone. But at that time, it was still early in terms of looking at tornadoes themselves. We were looking at the mesocyclone at Howie Shing. I think that's right, Howie? And so anyway, that's kind of what I did. And I was looking at hail, but in a more general sense. I really focused in graduate school and even at Chicago more on the wind fields versus the actual microphysics like Andy did. So we did kind of split apart in that sense, but we both overlapped a lot. One more. And then when I went to NASA, I kind of had to switch to.
Got to move the journal.
Oh, okay, Spaceborne. Okay.
And then, Robert Wright, who instigated this talk, got me back into the field of grapple and hail physics. And for many years between my first few years at NCAR and this period, I was working on other aspects of snow. And then Ian, who was shown here, gave a seminar at NCAR about a year later, and that really pushed my interest forward. So I guess the message we wanted to leave was that it's really important if one can get more high school students interested in atmospheric sciences. High school was a really important place for nurturing our interest in atmospheric sciences, and summer programs were extremely important for both of us. And these types of programs are not currently available. And then professors then mentored us were extremely important in our careers. That's it.
Guys. So we really wanted to, this was Robert's idea, but we wouldn't be sitting here with our second workshop without Andy. So we want to recognize Andy, and this was a way we thought it'd be really neat to bring Jerry in and do this. And I want to tell my Andy story just for a second. I was here on a job interview. I came, gave that talk on some of the hail work we had done at IBHS. And then Andy comes running up at the end of the talk, says, "Hey, we got to do something." And I'm like, "Well, what?" I knew his name from all this literature, and I see Andy. I'm like, "Okay, what do you want to do?" And he's like, "Well, I've been doing all this grapple kinetic energy work, and we had made all these hail measurements in the field." So I came out a couple of months later. We spent 3 days in the conference room over at Foothills, wrote the 2014 GRL paper, the coolest thing I've ever done, just sitting with him doing that. So without this guy, I wouldn't have gotten to interact with all of you over the years and get into this hail business. So thank you, Andy. So let's give Andy and Jerry a big round of applause, but also Andy for making this all possible. So thank you. And with that, I'll turn it over to our next session chair, Kelly Lombardo from Penn State, who will start us off and get through our next set of talks. So thank you.
So hello, everyone. Welcome to Microphysics and the Dynamics of Hailstones. And so our first speaker is Becky Adams-Seelan, and she'll be talking about the stochastic yet I can't talk after lunch, opportunistic nature of hail growth. I need coffee. All right, thank you, Kelly. Okay, make sure I understand this. Okay, all right. So I wanted to start this talk off with a question: why is large hail forecasting so hard? And it really is. I'm gonna poke at Victor here for just a little bit. This is a figure from a
paper of his that was published earlier this year, and it was attempting to use a whole mess of different environmental parameters to attempt to detect 50 millimeter hail, and it was using public hail reports over about a 14-year period. And so the bottom two are the SHIP, the severe hail parameter, and the large hail parameter. These are reliability diagrams, which are kind of a bit tricky to explain, but essentially if you're below this dotted line, you are not showing any skill. And so no, neither the SHIP nor the large hail parameter shows any skill. Even more interesting is up here on the top two, that's a logistic regression and a random forest. So that upper left is take all the potential environmental parameters you can come up with, put them into a fancy random forest AI, and see if you can predict or detect even 2-inch hail, and it is not possible. And okay, so moving away from picking on Victor, this is environmental information. You know, this is kind of a larger scale. This is synoptic, meso-alpha. All right, what if we move down to the convective allowing model scale? Maybe this will make a difference, right? No, and this is where I'll start picking on myself. Here on the left is, these are 50 millimeter hail forecasts from the 2015 hazardous weather testbed, and skill level hasn't changed a ton in the intervening 7 years. But these are using a number of different machine learning techniques that incorporate convective scale features from the convective allowing model, thing like updraft helicity, et cetera. On the right, that's the orange there is Hailcast. The blue is the Max 2D, the Greg Thompson's explicit microphysics parameterization prediction, and then there's an FV3 Hailcast in blue. This is for 1.5-inch hail, so that's a little bit easier to do than 2-inch hail. That's why the skill levels look a little bit higher, but yeah, they're still not great. This is, convection allowing model where we're pulling in microphysics information and we still can't forecast large hail. Why? So the thing that I was most interested in and that I could do something about, since I'm one of the CAM Hailcast designers, I thought, okay, let's focus on CAM Hailcast. Let's figure that out. So to explain how Hailcast is set up, it essentially uses a one-dimensional grid column, pulls it out of a convection allowing model, and that 1D grid column acts like a convective updraft. Then we have this sort of quasi-parameterization that attempts to parameterize a hailstone's motion across the updraft. So it changes, modifies the updraft speed there to make it seem more like what the hailstone would be experiencing. If it starts on the outside of the updraft, it is affected across out to the other side. Like, okay, that's pretty simplistic. Surely there are more advanced ways that we can do this updraft parameterization, and maybe that'll improve some of our large hail forecasting issues. Yes, is there a better way to parameterize an updraft as experienced by a hailstone? So the way I went about doing this was saying, okay, let's go out, simulate a nice hailstorm, and simulate all these hail trajectories through it. Let's see what kind of common features emerge. And I'll get in a little bit later into how I actually did the hail trajectory simulations, but this is just an example of what they look like. This is just one time step, and you see a giant mishmash of different hail trajectories moving through a storm. It doesn't make a whole ton of sense. What are some good ways to try to condense this information? Well, AI has all sorts of cool things for clustering. So I turned to a combination of, it's a trajectory clustering technique for 2 dimensions done by Lee et al. And density-based dbScan clustering. Combined those two, adapted them for 3 dimensions. And I'm just going to glance through this here real quick, but if you are interested, come see me and I'll talk your ear off about it. But so roughly, first you partition the trajectories into kind of sub-trajectories based on information theory, minimum descriptive length. You find the distance between all partitions using a 3D distance calculation. Then you do a density-based clustering, roughly based on dbScan. That clusters your trajectories that have similar orientation and are similarly located. And then you go back to looking at your parent trajectories and say, okay, which parent trajectories have at least 2 of these guys in common? And you get something that looks like that. You have to do a little final human QC at the end, but roughly you can say, okay, in this giant mishmash of hail trajectories, you could come up with about 4 different pathways that the hail takes through the storm. Oh, but wait, this was for just a single time period. We all know storms don't stay still, so you have to look at this as it evolves in time. The way that I accounted for that was simply making everything storm relative or updraft relative, if you will. So that way, say if a hail trajectory early in the storm life cycle and late in the storm's life cycle are still structurally similar, those can still be clustered. The time-space distance isn't going to prevent that. All right, so you do all that. Now, as I promised, I'll tell you about the trajectories themselves, how I generated them. So I used a CM1 simulation of a supercell using the NSSL observed soundings from the DC3 field campaign prior to the Kingfisher, Oklahoma storm. Conrad Ziegler helped me out with this, and they're also reported in the Davenport et al. Paper, Casey Davenport's paper. So what I did was actually embed the Hailcast hail trajectory model that's discussed in Adam, Seelan, and Ziegler 2016. Actually embedded it in CM1, so it's fully four-dimensional. And then I inserted embryos every 5 minutes from 90 to 180 minutes into the simulation and let those run entirely out. They do not interact with each other. And the boxes that follow are where I initialized the embryos, only where there was some sort of hydrometeor in the model. All right, so our left mover produced hail that looked roughly like this here on the left, and our right mover produced hail that looked something roughly like this. Each one of these dots represents a hail report of at least either 15 millimeters in the left mover or 19 millimeters in the right mover. Gosh, the gray doesn't show up real well, but there is some light gray on there that represents roughly, it's a smooth updraft field, so you can see where the updraft was moving, and I'm noting the storm motion on there as well. All right, so each different color corresponds to one cluster of trajectories or a hail point produced by one trajectory cluster. So for example, on the left side, you'll notice cluster A is in purple, and all hail points produced by the trajectories that make up cluster A are each of these purple dots. Interestingly, so there's 13 different trajectory pathways that this method identified in the left mover and 10 in the right mover. Oh, that's a lot of different ways hail can move through a storm. Seems a little concerning. Let's keep looking. All right, I'm going to start with the left mover. You'll notice that it seems like there's some maybe additional storm splitting going on here. This looks pretty complicated. Let's just focus on maybe early on in that before things start to split and we see kind of it's a lot cleaner and simpler updraft. We can probably see some common updraft hail behavior here. So interestingly, there does seem to be some sort of periodic type of hailfall. You see sort of 3 rounds of this periodic quote unquote hailfall. And again, I really wish that you could see the updraft, but it is preceded by a increase in what appears to be updraft area. So that's intriguing. There are 4 different clusters that appeared during this time, so we'll take a look at those. Here I am showing you, oh, you can't see, okay. Here I'm showing you plan view. This is an XY looking down. Here is XZ looking vertically, and then here is YZ looking vertically cross-section in the other direction. Each line represents the median position of all trajectories in that cluster, and the shading is the 25th and 75th percentiles. So this gives you a rough idea of what these trajectories look like in the storm. The black lines represent the center of the updraft, because remember, these have all been made updraft relative. They could be happening at different times, but they're all updraft relative. All right, so cluster D was one of the first ones that showed up. You'll notice that it starts, okay, there should be a note here saying that it starts about 2 kilometers below the others. And interestingly, it appears to be anticyclonic rotation about the updraft. If we move forward to cluster G, it is next. It starts about 2 kilometers higher. And this is a little bit harder to see. They start anticyclonic before switching halfway through to becoming a cyclonic rotation. Clusters E and A are the last to fall out. They are entirely cyclonic, but they are advected much more to the south, or this is upshear, on the upshear side of the updraft. All right, it's roughly, and A does happen to do 2 extra cycles in the updraft, which E does not. The source regions themselves, they're pretty kind of tough to see in this figure based on how I put it together. So here's actually the trajectories in each cluster themselves. The dot shows where they're starting from, and I just happen to circle them to help. There's cluster D, cluster E, farther aloft, there's G and A. And yes, you can still see each of those circles. That's a total of anywhere from 4 kilometers up to 12, where the embryos were sourced from, and up shear and down shear equally. So yeah, embryos were sourced from multiple sides of the updraft and different updraft levels. That was just in this first hour of this left-moving hailstorm. We weren't even getting to splitting yet. And trajectory paths were both anticyclonic and cyclonic about the updraft. Not looking great for our nice common theme, easy to find trajectory paths. Right here, these are again, the median and 25th, 75th percentile plots, but these are now with respect to time, where time is increasing, and on the right side, that's when the hail reaches the surface. And they're for a whole variety of different features, different characteristics, but the top right is diameter, and the right middle is mass. Looking over here to the right, you'll notice the median mass of each cluster ends up being almost identical. But the updraft speed, that's the top left, is incredibly different. The residence time aloft is quite different, and the attempting to parameterize that updraft speed as experienced by the hailstone would give you 4 different updraft parameterizations for just this one storm. All right, not looking good. Okay, switching now to the right mover. Left movers are notoriously fickle. A right mover, dang it, that's going to have our nice steady updraft. We're going to have common hail trajectory paths here, surely. Interestingly, we do see this sort of periodic behavior almost again. It's not quite as tied to increases in the updraft width, but that there's a lot of additional analysis that could be done here, I'm sure. But yes, you do see this periodic behavior, and there's interestingly towards the end, more hail appearing on the upshear side, a couple of different clusters appearing up there. So just for right now, let's compare clusters C and F. They both fall right in this space. They're both showing up at the same time. It's both the same type of storm. What do they look like? All right, well, they of course look quite different. Cluster F and C, they are both cyclonic, but whether they actually move or rotate around the updraft or stay entirely to the northeast side of it, fully up for grabs. Whether they tend to be advected southward or, advected southward or eastward, up for grabs. And interestingly, despite falling in the same exact location, they do have a significant difference in size. Their final mass ends up being median mass, does end up reaching outside the 25th and 75th percentiles there. Yes. All right. Then just to maybe compare these things, the left mover and right mover, as a whole here. So looking at just the peak hail size produced by both storms, the peak hail sizes produced by the right mover, there were about 60 millimeter or so hail produced by that. The left mover, the hail trajectory is maxed out around 30-ish. However, look at those different residence times aloft. That's a much shorter residence time in the right mover than in the left mover. That almost half the time spent aloft in the right mover, despite being ending up approximately twice as much mass than some of the clusters in the left mover. Updraft speeds, while they are stronger in the right mover, they're not egregiously so. And that's the same case with the cloud water. So it's not a lot of these relationships that we understand on a statistical sense for large numbers of trajectories across many storms, things like residence time and cloud water and updraft speed. Those are not going to hold true even on a single storm level, and definitely are not going to hold true on an individual trajectory level. All right, so in conclusion, hail trajectories within a single storm are highly variable. I might even say stochastic, and cannot be understood outside of big data mining type efforts. Be very, very suspicious of studies that say present just 10 trajectories and say, oh, this is what the trajectories look like in the storm. No, I do not think they do. Also, a single hailstone updraft parameterization is not possible, and it is not possible even if you attempt to link it to the environment, because those trajectories are going to vary so much, even within a single right-moving single supercell. All right, moving back to that question I asked way back at the very beginning, why is large hail forecasting so hard? Oh, and it didn't, well, I have these nice animations that aren't showing up. All right, well, so the point being that the dice can be loaded, you can have a favorable environment, you can have a favorable convective mode, you can have all those things, but that's no guarantee that you're going to get hail. Remember our hail trajectories from the right-moving supercell? Depending on how those looked, you could get severe hail or not severe hail. There's a lot that we don't know at these smaller scales, and it has a really big impact. Now, I'm even going to say it has a larger impact than the meso alpha and synoptic scale environment. I think there's kind of been this idea floating around out there that if we could, just get the right environmental parameter, and put it into the right equation, we could estimate large hail from environmental parameters or proximity settings. And I'm going to propose that that will never be true because these storm scale and smaller features have a larger impact than some of these larger environmental features. All right, I'm off my soapbox with that. Thank you, and I'll take your questions.
Do you have questions for Becky? Okay.
Yes.
Absolutely fascinating talk. I agree with you in the stochasticness. Is there an opportunity, though, to do maybe many ensembles of this type of stuff in different CM1 profiles and environments that may allow you to constrain that stochasticness to say this particular vertical wind shear profile does favor trajectory X, Y, and Z at this time in the storm's life scale that can poke at that at all? What are your thoughts on that?
Many. Yeah, and I think so that there's two pieces here, right? There's the how does the environment translate to what the updraft structure looks like, and we don't understand that. And then there's the how does the updraft structure and the hail trajectory interact, and we don't understand that either. And I'm just poking at that second piece. So in order to do what you're suggesting, we have to understand both of them, and we don't understand either. Matt, yes.
Yeah, I echo what Victor said, really fascinating stuff here. So I guess I'm trying to think physically about the trajectories and like what you just said in terms of the updraft. So would this also imply that because the trajectories are guided by the airflow patterns, so would this imply that the airflow patterns in the supercell updraft are also changing that? Like, have you looked into the details of what is going on with those? Are those total chaos as well, or is there some structures like the mesocyclone that are kind of quasi-steady there?
Oh, that is a very interesting idea. And no, I haven't done that yet. But yes, that'd be excellent. Yeah, I admit I've focused almost solely from a hailstone perspective, but yeah, that'd be interesting. Thank you. Sorry, Jerry. Oh. I don't know what that was first. Okay. Yeah, that way.
I think there's probably another complication, and that is neighboring storm interaction.
Oh, absolutely. Yes.
Isolated supercells are often not isolated. There's something nearby. And you can have cirrus from a neighboring anvil come and drop ice crystals over a storm downstream and so on and so forth. So that's something that's even more complicated.
Absolutely. I admit I was being a little messy and I was including that in my smaller scales, but yes. Jerry.
You say anything about the size of the updrafts and the magnitudes? And also the other question I had was when you talk about residence times, is that an updraft or is it just a loft? Or
good question.
Because I'm interested in how long they spend in updrafts, whether that's
okay. Good question.
Matt gave a talk a few weeks ago where you talked about the trajectories going growth of hailstones going across the updraft, I think. So yeah, I'm just curious, all those questions. Yeah.
Sure. Let's see. So what I have here, these guys are on the fourth one down is the updraft speed as experienced by the hailstone.
Right.
So if you draw, say, a line at maybe 10, you define your updraft as, you can see they spend all about the last 6 or 7 minutes of that time is spent aloft. Whereas, yeah, here it's still also 6 and 7, but they fall out a lot faster. Let's see, what was your first question?
Yeah, that helps.
Okay.
Yeah. So from the Doppler observations, I think, yeah, some of these supercells are at least 40, maybe 50 meters per second. That's probably okay.
Sure. And yeah, I guess that maybe brings up a good point, is that I'm looking at this almost entirely from a hailstone perspective and not trying to look at it from a, oh, what is the storm itself doing perspective.
Right.
Yeah, which is another piece of the puzzle.
Do you have anyone online? So we don't.
Yes, I have a question. So this is Charles Jackson. So at the beginning you showed kind of a, the hail prediction was a failure if it fell below a certain threshold. I think that was whatever, 25% or something like that. To me, it seems like even if it was 10%, it would be successful. I don't quite know why you say it has no skill.
Oh, sure. So yeah, the no skill line is actually this diagonal line right here. And that just simply means that your forecast is no better than climatology. So what your climatological forecast is going to vary based on, you know, where you are and what type of hail amount was observed over that time period. But no, we're still evaluating even at, say, a 10% forecast here. Here's your 10% forecast and your 10% reliability. Perfectly reliable would be following this dotted line. This just showed that a 10% hail forecast occurred less than 5% of the time in real life. So yeah.
Okay, thank you.
Sure. Due to the interest of time, maybe we'll save questions for Becky at the.
Yeah, I'll be out here. So yeah, we can talk. Yeah, thank you.
Our next speaker is Yuju Lin, and she's going to be talking about physical assumptions about non-spherical hailstones.
Hi everyone, I'm Yuju, and today I'm going to talk about physical assumptions about non-spherical hailstone shapes. How to use this? Oh, here we go. So we know that right now most models and microphysics schemes assume hailstone to be smooth and spherical. But obviously in reality, hailstones are rough and non-spherical. You can see in the figures below. So here, there's a question, what will happen if we instead model our hailstones as those rough non-spherical stones instead? How would that influence our model results? So immediately I'm going to show a flowchart. This is what happens when we model spherical hailstone. Like definitely this is like grossly simplified, but basically, you will have a hailstone mass and you will calculate your spherical diameter based on this hailstone mass, based on density, be it average density or Raman density. And then from the spherical diameter and hailstone mass, you can calculate your flow speed based on force balance. The hailstone diameter and flow speed, they go together. You can calculate your collection kernel, which will influence how much hydrometers you collect in the air, which will feed back to your hailstone mass, and then this loop continues. However, if we don't model spherical hailstones, instead model non-spherical hailstones, the flowchart will become way more complicated. So we no longer have a spherical diameter, instead we have a maximum dimension. And from this maximum dimension, we will have your aspect ratio and intermediate ratio, which will give us the hailstone shape. And then with this non-spherical hailstone, we need to calculate tumbling to get our collection kernel, which will then feed back to our hailstone mass. The aspect ratio will also influence our heat transfer coefficient. because right now the hailstone surface area will interact with our outer environment in a different way. Heat transfer coefficient is going to influence our hailstone temperature, which will in turn influence the dry and wet growth of the hailstones, which will then feed back to hailstone mass. We can see that this is becoming like a big flow chart. Luckily, most of these new processes have some literature backup that we can actually use them to model our non-spherical hailstones. So in this study, we are going to investigate what will happen if we actually apply these different physical assumptions using CEL1 and the detailed 3D hail growth trajectory model by Comje and Lombardo 2020. First, my PowerPoint is a bit different, just bear with me. First is a brief description of the trajectory model. So basically, this is a model using a composite storm produced by CEL1, which means it's steady state. And we are putting a seeding cube in the middle of the domain. The embryo size for this experiment is 7.5 millimeters in diameter. We will let these embryos grow in the storm and we'll look at the results. The base model itself is using Morrison Microphysics thing, which is assuming smooth spherical hailstone, but this is what we are going to change in this study. So first, let's talk about hailstone shape. So originally we are assuming, originally we are assuming spherical hailstone, so we have a diameter d, which will be a function of your hailstone mass and your density, be it ramming density or your average density. If it's spherical, then obviously your intermediate ratio and aspect ratio are both going to be 1. If we're going to modify it to make it non-spherical, then we no longer have this diameter. Instead, we have your maximum dimension, which will be an empirical function of your hail mass m. The reason why it has to be empirical is because we are trying to simulate real-life hailstones. So this function should somewhat come from real life. And then we can have your intermediate ratio and aspect ratio, which make up the shape of the hailstone, to be a function of your maximum dimension a. This will give us our new hailstone shape. So to get this first function, we have the Hayfield et al. Paper from 2018 and 2020, which they gave us a function between your maximum dimension and your hailstone mass, which can be directly used to calculate our hailstone maximum dimension in a model. So how do we get the next function here? We can use the Shed et al. 2021 data. This is the data from IBHS 3D hailstones. Following the example of Hayfield et al. Papers, even though there's a pretty large spread for hailstone aspect ratio in regard to hailstone maximum dimension, we can kind of bin them and calculate their percentiles and feed them into a coefficient here. For intermediate ratios, which is basically your B versus A in a hailstone shape, so the intermediate dimensions or maximum dimension, is a bit more messy. We don't really see a very clear trend here, but we can see that most of them are between 0.7 and 1. Just to avoid complication in this study, we are going to use 1 for these intermediate ratios, which means in this study, our hailstones are going to be oblate. So now, instead of our spherical hailstone, we are going to calculate the hailstone shape this way. We can derive your maximum dimension of a hailstone from your hailstone mass m, and then we can derive your ratios from this maximum dimension, and then we can calculate the non-spherical hailstone shape. So let's see some results. The plot on top is the statistics for number of hailstones larger than a certain hail size, and the plot below shows the hail size percentiles. We can see that once we have non-spherical hailstones, we have a lot more larger stones. But the question is this because of a physical process or is this something else? So let's answer this question. This plot, this is a very simple diameter, like maximum dimension mass plot. We can see that with the same hailstone mass, using non-spherical hailstones, like these dotted lines, will give us a way larger maximum dimension than spherical hailstones. So when you record your hailstone size, you're going to record a larger number just automatically. With these larger diameters, maximum dimensions. Since we're using oblate hailstones, they are also going to give us larger collection areas. So they're going to collect more hydrometeors in the air, which will feed back to our larger hailstone mass. And then you're going to have larger maximum diameters. So this is a loop here, which is not physical. Where does this happen? Oh, sad. The animation isn't showing. But this is our current model when the hailstone falls face down. However, in real life, hailstone, obviously, they do not fall face down. They actually tumble in the air. So with their tumble, there are going to be a lot of hydrometeors kind of slip through the crack. So they are not actually going to be collected by a non-spherical hailstone. So next, let's talk about tumbling. I'm gonna skip this part a little bit because it's just a lot of high school math. Basically, you can explicitly tumble a hailstone by tumbling in 3 dimensions. For example, here we have a hailstone, we rotate in your XY plane, and then similarly we can rotate in your XZ plane and the YZ plane, and in the end, you will have a rotated hailstone. So the orange plane I'm showing here is basically your new tumbled collection area. And this area is going to be smaller than your oblate maximum area. For example, here, the collection area part AT will be smaller than your maximum projection area part A, and the ratio between them is this. So we can actually use this ratio, I call it AR, to calculate our new collection area, which means we can calculate our maximum projection area of a hailstone in our model and simply times it with AR, and then we have our new collection area. Now I have a new problem. If we want to actually calculate hailstone tumbling, we need to explicitly tumble each hailstone at each time step. It's going to take up a lot of calculation time, and that's going to be bad. Luckily, we can kind of parameterize it. So here what I did is I just choose different randomly sized shaped hailstones. I tumble each hailstones 1,000 times, and I fit it. So we can see that this AR ratio is going to be related to your intermediate ratio and your aspect ratio, so your hailstone shape. And if we want to save calculation time, we can actually just use this formula to calculate our AR. So now we can actually have our maximum projection area in our Hail model and just directly use this formula. We have AR, and then we have our new collection area. So now this is our new hailstone statistics. We can see that this tumbling is bringing the number of larger hailstones, medium to large hailstones, way down, even though we still have like larger hailstones overall. So we have non-spherical hailstones, they are tumbling, but is this good enough? Is it realistic? So if you remember in the beginning on the flow chart, there's a very important component that's hailstone terminal velocity. So I think there is still a problem here, which is how we calculate our terminal velocity. So this is the most basic formula for your hailstone terminal velocity based on the definition of drag coefficient. Originally, we assumed hailstone to be spherical, which means a lot of things can be boiled down to your diameter and your density. Because it's spherical, so your M and your part AT can be kind of concentrated. Obviously, this isn't suitable for our non-spherical hailstones anymore because we no longer have a clear relationship between your M and your AT. They're not directly only related to your diameter anymore. One simple way to understand this is we can see the plot here with the same maximum dimension. Your differently shaped hailstones are going to have different mass. So they're going to have different gravitational force acting on them. So with the force balance, of course, they're going to have a different terminal velocity. So how do we tackle this problem? To modify this, we can use empirical relationships again. So here, also from the Hailstorm et al. 2018 and 2020 paper, we can see that they gave a relationship between your terminal velocity and your maximum dimension. So here we have different panels showing the comparison between Morrison drag, which is basically assuming hailstones to be spherical, and your non-spherical Hailstorm drag, which is the blue line and the red line here. One curious thing about it is that we can see that even though we are changing the aspect ratios in these panels, they are differently shaped hailstones. These panels are absolutely identical. This is because with this empirical relationship, your terminal velocity is only related to your maximum diameter. So what is the basis of using this kind of relationship? Let's go back again to the most basic form of calculating our particle terminal velocity. So with terminal velocity, we can have all these parameters related to the Hailstones, and then we have your drag coefficient. So how is drag coefficient calculated? It's going to be calculated based on your Reynolds number and your Best number. So once we have tumbling non-spherical hailstones, it's going to complicate things. So when your projection area AT is only related to your A or D, and everything else is also only related to your A or D, or when your drag coefficient is a constant, then your particle terminal velocity is going to be exclusively related to diameter. But this is not the case, as we can see here, if your hailstone is not spherical and tumbling. The lucky thing is that a lot of these controlling factors for our particle terminal velocity is actually documented in a detailed explicit Hale growth trajectory model. For example, your mass and maximum dimension, drag coefficient can be calculated, your projection area, these are not documented. So instead of using a bulk empirical relationship, we can actually calculate the terminal velocity of each hailstone at each time step separately. But is this good enough? So we still have a difference between our hailstone right now, which is the smooth hailstone, and the hailstones in real life, which is clearly not smooth. This is going to be a huge difference because it's going to affect your drag coefficient for one. So, I think I'm missing this. Oh, okay. Let's look at this slide first. This is the paper Julian Brimlow sent to me and Matt. I'm really grateful for that. This is not a meteorological paper. This is actually a paper from Boulder Technology. So they chose different stones from volcano stones, and then they used the roughness to calculate our new drag coefficient. We can see the parameter here, which is D equal to a third, and then LIS. This is going to be a parameter we're going to look at. How do I go back? That's what I know. Sorry, can someone help me? I'm really sorry. Back. Oh, got it. Yeah, thank you so much.
Wow,
yeah. Oh, okay. So this is the parameter we're going to look at. So here, I used a bunch of Slurholm and IBHS collection of 3D scan hailstone data to calculate this parameter VR. So VR is your V versus VCOG. So V here is your real volume of a hailstone, and the VCOG is going to be the hailstone volume that you calculate using your dimensions A, B, and C, assuming it's a smooth ellipsoid. So here we can see the range of VR. They are mostly between 0.9 and 1.4. Here I'm using 129 hailstones to calculate this. So this VR can be actually a pretty good parameter to characterize, I messed up that word, the hailstone roughness. So here I just showed two different examples of hailstones with different VR. So with that, and using this formula from the Boulder Technology paper, we can compare different terminal velocity schemes. So what we do for the individual calculation ones is basically we'll collect all the parameters needed for those ellipsoidal hailstones at each time step. We'll use these parameters to calculate our best number, and then we find Reynolds number and Reynolds number base drag, and then eventually we calculate our terminal velocity. You can see that for the hailstones that are really, really not spherical, there's a pretty big spread. But as the aspect ratio approaches 1, they are kind of getting closer together, which is encouraging because in that case, we are approaching a more spherical hailstone. So this is the result of using different like terminal velocity schemes. So here we can, the way we actually put this into model is we relate to our drag coefficient to our lobishness, so VR, and we relate this VR to our bed growth coefficient, or to our bed growth time. So basically, the more time you spend in bed growth, we say, oh, the hailstone is rougher, it's more lobish. We can see that here there's actually a pretty big difference between results produced by different terminal velocity schemes. Now, another thing the roughness of hailstone is going to influence is the surface area. Because the roughness, the lobes on a hailstone is not only going to influence its VR, we can also similarly make a parameter SR, which is the actual surface area versus your calculated surface area. So here we can relate to this SR to VR. So this will show what the actual surface area of a hailstone is, and that's going to impact our diffusion and our heat transfer. So the way we do this is we set the roughness of a hailstone in our model, which is VR, and we can calculate your SR based on VR. The different color is just showing the two different ways to calculate SR, whether we calculate this S-Calc as an ellipsoid or we calculate the S-Calc as a sphere. Another thing that's going to influence our heat transfer coefficient is actually our aspect ratio. This is from the early McLean papers. You can see that differently shaped hailstones have different heat transfer coefficient. And from the Laura paper, we can also see that our aspect ratio of hailstones is indeed pretty low. So it's going to be different from spherical hailstones. So this chi is also going to be taken into consideration when we are modeling those non-spherical hailstones. So let's see difference here. So the chi adjustment here means with this experiment, we're actually adjusting chi. It seems to us that just by adjusting chi, it doesn't seem to be a very big difference in our results. However, we can show something here. So for example, this is a randomly chosen pretty large hailstone in our hailstone trajectory model. The only difference between these two trajectories is when I'm having the chi heat transfer coefficient adjustment and your surface area adjustment, and the other one I don't. So just by this simple adjustment, they're having very different trajectories and they're having very different final sizes. The black lines here is the height, the altitude during their growth, and the colored lines here are their like mass. Okay, I don't know how much time do I have, so I'm just gonna put the discussion future work here. And if you have any questions, you can either email me or ask me after I finish talking, and then I finished.
We have time for maybe one quick question. Yeah.
So that was a great talk. Wow, I have 100 questions, but it really good to compare your estimates of fall speed that you're getting here with those in wind tunnels, or even dropping instrumented hailstones from a drone or something. Like, are we getting more accurate by doing all of that? Or do you have a feeling for getting more accurate estimates of fall speed using this approach?
I'm not sure, because I think the Hainsfield papers are actually, you are using like wind tunnel studies, if I remember correctly, right? And the Boulder technology paper is giving us very different fall speeds, like compared to other stuff. So right now, for now, I'm not saying which one is more accurate, but I can use this as a sensitivity test to see that terminal velocity really does matter in our hailstone modeling. But I really hope like there can be more abundant like wind tunnel data that we can actually use to verify this.
Thank you. Our next speaker, oh, sorry. Blocking her in. Our next speaker is Ted Mansell, talking about hail embryo trade. Tracking in both.
Good afternoon. It's a pleasure to be here. Well, afternoon here. I don't, where people online, it could be evening or some other time. So this topic is something I've been playing around with for the since last year. Okay, great start. And so since about last year, I've been working on this, and I'm still going to call it preliminary because the simulation results I'm going to show are done within the last couple of weeks. It just keep updating. Some people know how this works. You always make changes and fix bugs. And
apologies. If you can give us just 1 minute just to fix the projector issue.
Okay. But I can still say something about the motivation for this work. Is that I got involved with the ice chip proposed field program. Oh, there we go. Boy, making me look great there. I'm just hitting the button here. Yeah, so, and part of that planning and the proposing, I was looking back at some of the old papers, and the Nancy Knight paper from 1981 had this really interesting relationship between cloud-based temperature and the fraction of hailstones it had, either grapple or frozen drop embryos. Now, if a hailstone comes and breaks your window, you don't really care what kind of embryo it has. But there was a question raised this morning about, well, we still need more basic understanding of how hailstones form. And there's information that comes down to the surface about the embryos, and maybe we can use that to understand better what's going on in the production of the hail. But this pretty simple looking plot has perhaps a lot of physics behind it. There are a lot of things that, a number of things that affect the cloud-based temperature, cloud-based height. How do aerosols affect this? How does a hodograph affect this? There's an emphasis on average cloud-based temperature there. So that's, we look at this and think, oh, well, that's a nice, simple relationship, but maybe it's not really. So I'll say a few words that probably people in the audience not familiar with the microphysics scheme I'm using. The Nessel microphysics, it's a fully 2-moment scheme with mass and number. It has separate grapple and hail. I'll say more about that on the next slide. And there's a 3-moment option for rain, grapple, and hail, or any of the fast-moving species. And then there's a prediction of bulk density. All the cool kids are doing it these days. And this allows grapple to take on the characteristics of either the frozen drops or low-density grapple instead of having a fixed density. And then the hail species, instead of being defined by high density, it's defined by its source. And so it's produced in areas where grapple has wet growth, and then it picks off the larger diameter particles and puts them in the hail category. And then they go from there. And then there's also a predicted bulk CCN for aerosol sensitivity. And I've done a little bit of that with this work, but it's also very preliminary. And so I won't be showing any of that right now. But just quickly, the bulk density uses a formula that some people here will be pretty familiar with. And then there's a provision for soaking that can turn that on and off if I want. And then again, the hail, the only source is this conversion of large high density grapple or frozen drops. And there are a couple of ways that you can do that conversion. What I'm going to show here is saying, looking at the size where wet growth starts, and then basically integrating the tail of the distribution and putting that into the hail category. And just a quick example from a paper a few years ago, how the aerosol, the droplet concentration affects the density of the grapple. On the lower panel there, you just see the graupel getting lower density as we increase the CCN concentration, smaller droplets, just leads to lower density rime, and you get this variability. So once again, we have the 2 moment, which is predicting the mass and the number concentration, and we turn the 3 moment, we'll call that Z. That column is the 6 moment in diameter, or the reflectivity. And then we predict the volume for graupel and hail, and that provides the information about the average particle density. Okay, so for this study, I added a separate frozen drops category. So instead of graupel representing both species, then we have separate ones. And so graupel is exclusively particles that rime from ice and snow crystals. And then the frozen drops are, well, frozen raindrops. And again, the frozen raindrops are 3 moment with volume, so it also has a density prediction. In my other life, another column here would be electric charge, but I'm not going to talk about lightning today. And then we could also make an additional information in hail. So the idea is to track what fraction of embryos are coming into hail. So to do that, I just added an extra number concentration to hail for the number that came from frozen drops. And then that quasi-Lagrangian information is carried down to the ground, and we can see a map of and what fraction of hail comes from frozen drops versus graupel. Oh yeah, I'm not gonna skip this one. And then you might say, well, we get these frozen drops, where did the frozen drops come from, right? So I thought, well, okay, we can do that in the same way that we're adding a number concentration to the hail for the frozen drops. We'll add fractional mixing ratios to the rain for what the rain came from, whether it's auto conversion from warm rain process, melting of ice particles, graupel and frozen drops, or wet growth shedding. And then there's just an enforced total. So the QR and then each component are separately predicted, and then there's a enforcement that they equal each other. And then the gains and losses are just applied by fraction, proportionally to each fraction of the mass. All right, so given that this is kind of ice chip oriented in my case selection here, because the proposal is to spend the first year in the high plains, Colorado. Reached back into history to 1974, and it turns out NCAR still has the soundings from that program online, so you can download them. You have to clean them up a little bit though. So I pulled the sounding out of that. And then there's another well-documented case on the high plains from the Stereo A program, 96. And then for a Southern Plains case, I get into this century for an Oklahoma case that we've looked at in a couple other papers. And these simulations are done with commas, which is pretty similar in design to CM1. And these are done with a grid spacing of 500 meters, which is a little bit coarse for this still. I'd like to do higher resolution, but that'll take time, and 2 to 3 hour integration. And I have done CCN varying with this, but what I've done with these cases is try to get a similar droplet concentration at cloud base for each of the cases. And then initiation is done with a persistent low-level convergence forcing to simulate like a boundary that would get convection started. And these are our soundings. The famous Fleming case on the left, it had to modify a bit to get it to actually work because it was on the dry side of the boundary. And then the stereo case has been done by a number of studies. And then this one June case, 2008. And so we have two cases with the colder cloud-based temperature, 7 and 10 degrees, and then much warmer cloud-based in Oklahoma, and also much moister boundary layer. So we have this boundary layer moisture is a big factor in where the cloud base is. And I'm working on a set of analytic soundings to have more precise control over the shear and and everything to make use environments that are associated with real cases, so you get an idea of if your model is actually simulating something realistic. And that's what we'll see here, I hope. The animation is not wanting to go there. It's an MP4. Well, anyway, what you would see on the left is a movie of the low-level reflectivity of a storm and the hail swath coming out behind it. Apparently, those of us who use Macs are not having good luck with our animations today. And I would say you could judge for yourself if it looks realistic. I'm going to tell you, yes, it looks realistic. So this was not planned, that didn't work. But on the right, you see the hail swath in the blue contours is the hail accumulation. I think the lowest contour there is at 1 millimeter water equivalent. So there's you can see an episodic hail output. You have local maxima, and then the color fill indicates the fraction of those hail at the surface that come from frozen drop embryos. So at the top, at the northern end, is the beginning of the storm, and then it progresses southward. And so that initial maximum in the hail fallout is pretty much all graupel based, which is maybe not surprising because you're a high base environment. You haven't had time to recycle drops yet. But as that storm starts to mature and grow a little bit bigger, you do get more frozen drops coming in, but it still stays less than 60%, but it does vary over time and over space. So if you're out sampling and you park your van in one spot, you're going to get one answer that may not be representative of the whole storm. Stereo A, also very nice. Animated loop that you're not seeing. But on the right, we have a summary again of the hail swath. And again, episodic cycling behavior in the hail output. And again, initially a very low fraction of frozen drops, but as time goes on, we get higher output up to 70, 80% at some points. And then the next one is the Oklahoma case, the 1 June storm, which also makes a very nice, realistic loop of low-level reflectivity. This is only 3 animations, so I can show them on my laptop if you want it, if you're interested later. And as we are expecting with this warmer cloud base, we're getting a much higher fraction of frozen drops. But even here at the beginning, the fraction is 50% or less. All right. Let's see. Go forward. Okay. So this is a time series summary of what we just saw in the swath, just looking at the whole domain accumulations. The solid lines are the number of hailstones falling out per minute. And then the dashed lines are the accumulated totals. And so for the NHRE case, the Fleming storm, we can see pretty clearly the difference between the black, the total hail, and the blue, the hail with frozen drop embryos. It maintains, for the most part, a pretty high fraction of grapple, low fraction of frozen drops, except in this one time when it has a minimum output. And then where those frozen drops seem to come from. So this is a plot showing the total freezing rate of raindrops and what fractions the rain has. So at the very beginning there at 20 minutes, you're seeing this little bump with actually from auto-converted drops. But those are probably high up in the storm and they're just freezing and blowing out of the storm, not necessarily producing hail. That's a guess. I haven't looked at that specifically. But then as the storm matures and we have more complicated structure, then we're getting frozen drops from melting. So these would be drops that get pulled back into the updraft. And then some from shedding, some from auto conversion. And again, this is the entire storm. I have not broken this down into by height, although I do have time height information. So it doesn't necessarily tell us that these are the ones that are becoming hailstones. But it's a good first guess, I think. And then for the stereo case, we again see a relatively low fraction of frozen drops at the beginning, but then it picks up. It's not clear why in this case. It's a narrower storm, so we may need higher resolution to really separate the hail shaft from the updraft better. There may be a resolution issue there. So stay tuned for bigger simulations. And then it's, again, like the NHRE case, most of the frozen drops are coming from melted ice particles that are pulled back into the updraft or within the updraft and just getting carried back up. And there is a big difference in the shear between these two high plains cases. If you've ever looked at the Fleming storm shear, it has like 80 meter per second winds up aloft, much higher than the stereo case. And then what we're expecting from the Oklahoma warm season storm, getting mostly frozen drops. But again, at the very beginning, it's mostly it's a majority of grapple from these early hailstones, because there hasn't been time for these freezing drops to form. And then when you do have freezing drops, there's a much bigger difference here between this and the high plains cases, where we have a bigger mix of frozen drops coming from shed or melt or auto-converted rain. And again, this is the total, so I'm not going to say these are all equally going into hail production, because the auto-converted drops, again, might be forming higher up, and so they may be less involved in the hail production region, which might be a little bit lower down. That's another thing to look at more closely here. And so that's the basics of what I wanted to show today, that it seems to work, that we can carry this information down to the ground. And if we get more detailed observations of the hailstones at the ground, maybe that will tell us if the model is totally out to lunch, or if maybe we're on doing the right track here. And we generally follow the trend. I mean, basically 2 points make a line, right? So you can follow the trend of the night figure there. And a couple takeaways is not surprising, I guess, that raindrop entrainment becomes more prominent as the storm matures. So simulating out in a couple hours is good to do. And the rain auto conversion, as also not surprised, it becomes more prominent in we have the warmer cloud base, and also a higher adiabatic water content, moisture boundary layer. There's more vapor to condense. And that case also has a bit more CAPE. I think it's like 4,000 versus about 2,000 for the high plains cases. And of course, there are always going to be questions using bulk microphysics. Well, we might be overestimating wet growth. We might be overestimating shedding. We might overpredict the drop entrainment, maybe because of the resolution. That's something to look at. So there's still questions about how these things are happening, but that's what we do in research. Thanks for coming to my TED Talk.
Questions from Ted? Thanks, Ted. Great talk. It was really interesting that you mentioned seeing this kind of periodic production of hail as well. And you mentioned seeing it in, I think it was the accumulation field possibly. Did you see any other hail characteristics or embryo characteristics that appeared periodic as well?
It's hard to say offhand, but I was thinking during your talk that, oh yeah, you had those clusters of hail, and that's kind of what happens in the swath. I have a couple extra slides. I'm not sure if they show anything extra, but my talk has gone away. If you can pull that back up. There's so this is the mean diameter of hailstones reaching the surface. And so it's not I don't have yet a maximum possible size of hail. This is just the mean mass diameter of hailstones at the ground. And so we got like a centimeter or more in these. And I don't, there's obviously some variability there in the Fleming case. There's definitely some here in the stereo case. So this is not really about the embryos, but the hail at the surface. But I mean, we know hailstones do this, or hailstorms do this. The size varies as they go along. Yeah, thanks.
Is there anyone online that has a question? No? Okay, in the interest of time, we should probably move on, but thank you.
All right, that was for Matt.
Our next speaker is, are we clapping? Are we not clapping? Is Patrick Kuntz talking about the impact of microphysical uncertainty on the evolution of a severe hailstorm.
All right, can you hear me? I guess so. All right, hello everybody. My name is Patrick. I'm a PhD student from Mainz, Germany. My work is part of the Collaborative Research Center Waste to Weather. We're part of the project is led by Corinna Hose, Michael Kunz, and Lena Frey at the KIT in Karlsruhe. And Annette Mildenberger and myself are working at the Johannes Gutenberg University in Mainz. And we are interested in the microphysical uncertainty and also the initial condition uncertainty in severe hailstorms. So we are particularly interested in cloud, hail, and precipitation-related variables. But today I'm only focusing on the microphysical part of things. So that's why the title is. Okay, next slide, please. Oh, I can actually scroll. Okay. So just a short motivation. Here you can see a plot of Moyenasca et al. Showing where they used 8 different models to simulate the same synoptic situation. Deep convective precipitation, and you can see here accumulated precipitation over several hours. And clearly visible, there's a huge differences in the coverage and of the intensity of the precipitation. So where do these differences come from? The short answer would be from the initial conditions and the different formulations of microphysical processes in the different models. And we want to know then, can we quantify impact of those two sources. Next slide, please. Okay, so we also look at a specific synoptic event, which we call the Munich Hailstorm from 2019. On the right-hand side, you can see the storm track taken from Wilhelm et al. The green and blue colors indicate the storm track over southern Bavaria, several hundreds of kilometers in length and also several hours lasting supercell. We observed the red triangles near Munich indicate sightings of hailstones up to 6 centimeters. And we simulate this hailstorm with the ICAN model, version 2.622. And we use a two-moment microphysics scheme of Seifert and Beheng. We included the three main secondary ice formation processes, and we use cloud resolving grid resolution of 1 kilometer. We initialized the simulation at 300 UTC, so we have about 10 to 11 hours of lead time before the storm develops. Now, we don't have different models we use, but we are conducting an ensemble, so we change the microphysics in every ensemble member, so we essentially create variations of our model. Next slide, please. So here, the main feature of our ensemble, we are looking specifically at 8 different microphysical parameters related to hail formation. These are listed here together with the ranges where we vary those parameters. So we're looking at the CCN and IMP concentration, the collision efficiency of graupel and hail with cloud droplets, so essentially the rhyming efficiency. We introduced a density-dependent formulation for both graupel and hail particles. So by changing the density of the particles, we influence the fall velocity and also the mass diameter relation. And we are looking at the capacitance of ice and snow crystals. We use a Latin hypercube to homogeneously sample the 8-dimensional parameter space. So every one of the 8 parameters is changed in every ensemble member, of which we have 112 ensemble members. And the next slide, I just want to highlight the top 2 ones, those are CCN and the IMP concentration. So the first results show clearly that the most influential parameter which we perturb is the IMP concentration. It overshadows kind of all the other impacts of the other parameters. And the second most influential one is the CCN concentration. We are using the Hundred-Al activation scheme for both of the aerosol concentrations. So simply we use a scaling factor to scale the default value of the activated CCN concentration and IMP concentration. For the CCN concentration, we have 2 orders of magnitude, and for the IMP concentration, we vary in a range of 4 orders of magnitude. And this kind of comes from the literature, so it should cover an observation range on climatological base. All right, let's look at some results in the next slide. Okay, first, let's have a look at the effects of the IMP concentration on 4 different metrics. On the top, you have hail precipitation, total precipitation, and at the bottom left, we have the hail water path. And on the right, we have the sum of essentially the column integrated hail numbers, which is the number of hail particles in a vertical column. Okay, so the metrics here are calculated by averaging over 2 hours during the most intensive stage of the storm in the model and over the horizontal extent of the storm cells. Each blue dot represents one ensemble member, and the red line is a linear regression, and I calculated the Spearman's rank correlation coefficient and the respective p-value, which are shown in black inside the plots. So we can clearly see strong correlations of all the 4 metrics to the IMP concentration. And the x-axis always is represented the INP concentration. So what we see is that the higher the IMP concentration, the more hail particles are produced in our model. And likewise, more hail content is produced. But at the same time, we get less hail precipitation. So we have more hail in the atmosphere, but we have less hail at the ground. So why is that? It should come down eventually. So on the next slide, we can look at, next slide, please. We can look at some vertical profiles. Okay, so here are 4 time steps of vertical profiles. In our storm, again, the metric is calculated by averaging over the storm cell, horizontal extent of the storm cell. The red profiles include all the ensemble members with very high IMP concentration, and the blue profile represents the ensemble members with very low IMP concentration. And on the top right, we see the number concentration of hail particles. So again, here we can see high IMP concentration leads to high number of hail particles. And at the same time, those hail particles are very small. So on the bottom left, we see the effective radius, so kind of a mean radius of the hail particles. So red, again, many particles that are small. And on the bottom right, we can see the mass mixing ratio. And the middle dashed line represents the 0 degree line, so the melting level essentially. And below this 0 degree line, we have melting, and it's clear that the many small particles melt more efficiently, which then leads to a stronger reduction of hail content in this bottom layer, and eventually less hail precipitation at the ground. Okay, next slide, please. So here we can see now the effect of the CCN concentration. So again, all the same 4 metrics. And again, we can see some correlation. It's not as pronounced, but one thing that we can see is that the correlation has different sign, every one of the metrics. So this time, for high CCN concentrations, we have less hail particles, less hail mass, but at the same time, on average, we have more hail precipitation. And well, the picture in the hail precipitation, so in the upper left panel, is not that clear as before. But what we can do on the next slide is we can look at the simultaneous effect of IMP and CCN concentrations. So here now on the X concentration and on the Y-axis, it's a representation of the CCN concentration. The position of the dot essentially is the parameter space, and the size of the dots represents the hail precipitation rate. So the smallest dots are in the bottom right corner, where we have high IMP concentration and low CCN concentration. And the other corner, on the opposite side, also the upper left, we have on average the highest hail precipitation, where we have low IMP concentration and high CCN concentration. So there's kind of an effect happening that's enhancing or decreasing the precipitation we get. What else can we see? So on general, it's not that clear, but on general, we can say that the sensitivity of the hail precipitation on CCN is higher if we have high IMP concentration, so on the right half of the plot, compared to the left part where the CCN concentration may not be so important. And on the next slide, we can look again at some vertical profiles. And here we can see in the upper right corner, again, it's the number concentration. We can see this effect that the sensitivity is different. So the colors here represent the 4 extremes of our parameter space. For example, the yellow and the red profiles mean we have high INP concentration, and the blue and the purple one are low INP concentration. And if we compare the yellow and the red profile, we see that the CCN concentration leads to a reduction of hail particles. And for the blue and the purple profile, there's not so much of a difference. And this enhancement of the sensitivity can also be seen in the bottom left for the size of the particles. But however, not so much in the hail content picture on the right, bottom right. So it doesn't seem to be pronounced enhancement of the sensitivity of CCN concentration. And this may just be due to the fact that we have a lot of effects controlling the size distribution, essentially, of the particles. Okay, so I think I can conclude now on the next slide. So we found out that the results show very strong correlation, especially on hail content, of hail content and precipitation, especially on INP concentration, and to a lesser degree on CCN concentration. However, the correlations have different signs. We also have, we've seen slight correlations of graupel density to the total precipitation, but the INP concentration effect essentially overshadows all the weaker correlations. And therefore we want to do a more thorough sensitivity analysis. And since we also see that there's interaction effects happening, this will also be included in the sensitivity analysis. So we want to investigate this further. And then we, as I mentioned earlier, we also want to look at the initial condition uncertainty, and we already have done an initial condition ensemble. And we then want eventually combine those two ensemble types to get a larger ensemble, and then assess the relative contribution of both uncertainty sources. And with this, I'm finished. Thanks. And I'm open for questions.
We have time for questions in the audience online.
Hi, Patrick. This is Matt Cumgen in the audience. Nice talk. Just a couple of naive questions about the microphysics scheme. So your effective radii for the hail was quite small at a high altitudes, like 0.1 millimeters, something like that. So I guess, what is the hail like in this scheme? What are the sort of defining properties of it? And then I'm trying to understand the chain of physical processes that goes from INP to hail. So is there some sort of conversion that would make such a strong relationship there? Thank you.
Yeah, so so for the hail size, we essentially don't have really large hail in the model. I think the upper threshold is like 1.2 centimeters, which is like half an inch, which is maybe really small. So this is probably one of the reasons why we have these smaller hailstones here. But eventually it's just an average measure here. And then the second question was about the INP, the importance of INP concentration. So, I mean, there are two pathways essentially for the formation of hail, which is the freezing of large rain droplets, and then the freezing, the riming of graupel. And so I would assume that if we have a lot of high INP concentration, we get a lot of small ice crystals. which eventually rime and grow to snow and then crumple. But when those crumple then grow to hail, we still have just on the basis really many hail particles which all compete for the same water vapor or liquid water. So it's just yeah, either we have a lot of small particles or we have less but larger particles.
Other questions?
I don't.
Oh, can't hear me?
Yeah,
Hello?
yes,
I'll stand
yes, I
closer to
know.
the mic. You're far away. I don't want to seem overly critical, but I did want to make a comment on the tool that the microphysics scheme and looking at the effects of CCN concentration on convection, deep convection in general. As Ted alluded to in his talk, the size of droplets impacts the rime density, and which really affects the grapple fall speed. So I would sort of make the general sort of strong statement that any study that looks at CCN, the impact of CCN, really needs to have a grapple density as part of the scheme. Otherwise, you get the wrong impact. So sorry to sound so critical, but it's a point that I think that the community sort of underestimates.
Okay. Yeah, thanks.
Other?
I mean, the density we use is just a predefined value. We don't kind of track the density evolution. We don't have that, but yeah, good comment.
Any questions online? Nope. Becky. Do you look at the content or amount of super cooled liquid water, perhaps? That might help you get at some of these intervening steps?
No, I did not. So I was thinking about kind of looking at the process rates in the kind of related to the pathways of hail formation. So that would be a point where I could look at the liquid water, the supercooled water as well. Yeah, but I did not yet.
Any final questions? No? I have one, but we're kind of up on time, so I can save it. All right, so let's thank Patrick.
Yeah, sure.
Yeah. Our final speaker is Rory Coy, talking about exploring the hail and lightning associated convective events in kilometer resolution simulations over the Alpine-Adriatic region.
We cannot hear you. Make sure that you're selecting the right mic. We can hear you now, yes.
Okay, great. So thanks a lot for the nice talks. And for the last talk before the break, I will shift the topic a bit back to the climate change over the Alpine-Adriatic region, which is the hotspot over Europe because of the complex topography. Next slide, please. So the main objectives are twofold. The first is to see how well are severe convective events simulated by convection resolving models. And the secondly is to see how will severe convective events change under global warming conditions. So for the first objective, I will focus on case studies. And for the second one, I will focus on my decade-long climate simulations. And next. As you can see from this figure, I'm using Cosmo Climate version that is able to run on GPUs with Era 5 boundary conditions. I'm using two-step one-way nested domain. So the outermost is 12 kilometers with parameterized shallow convection. And for the innermost, I'm using 2.2 kilometer with explicit shallow and deep convection. To diagnose hail and lightning, I'm using Hailcast and lightning potential index that called every 5 minutes and also 15 minutes respectively. And those can predict the hail sizes on the ground and the potential of lightning. And I'm using single moment microphysics. So on the next slide, I will show you. Next slide, please. So I will firstly show you the analysis of 8 deep convective events over the Alpine region. And those events are selected based on different synoptic situations and the cost of the impact. So the first and third rows are the image observations, and on the right corner are the high-resolution ring gauge data, and the second and fourth rows are Cosmos simulated daily accumulated precipitation. So from this figure, we can see that Cosmos is able to reproduce the patterns of precipitation. So with this, I will show you the result of hail on the next slide. Here I show you the footprints of daily radar-based observations probability of hail that is larger than 0% with orange color, and also Cosmos simulated hail with larger than 0 millimeters in blue colors. So for, as you can see, for 8 different cases, Cosmos Hailcast is able to reproduce the hail swells, and even for the second case, which is the 1st of June, and it can also simulate no hail with heavy precipitation. So, and for lightning, I didn't show it here, but it produces similar patterns, meaning that Cosmos Hailcast and LPI are good candidates for decade-long climate simulations. So on the next slide, I will show you the climate simulations. I'm using Pseudo global warming approach. So as I said before, under current climate, I'm using Arrow 5 as boundary conditions, and then followed by this nesting approach to get 2-kilometer control simulations, which is from 2009 until 2018. And next, I get this PGW, next click, please. So for this PGW signals, and it's coming from 1 GCM, which is MPIESM, high resolution, and it's the difference between this SSP 585 with 30 years daily mean minus the historical 30 years. And then when I add these PGO signals over these Arrow 5 boundary conditions, next, I can get the future climate boundary conditions, and then followed by a similar simulation approach, I can get 2-kilometer PGW simulations, which is under future climate of 2089 until 2098. And next, because it's very expensive simulations, I'm mostly focused on this 10 extended summer seasons, which is from April until September of 2.2 kilometers. So for the 12 kilometers, I will run it for full year continuously. And for this 2.2 kilometers, I will initialize in February and run it until October. And I will focus on the analysis of April until October, meaning that from February until April will be the soil spin up. Next, I will show you the, firstly show you the result of changing precipitation. So here I show you the mean accumulated precipitation of observations, the first column, and the second is control simulations, and the third column is the relative change. So compared to observations, Cosmos is able to simulate mean daily precipitation, and mean daily precipitation tends to decrease in scenario simulations over land. However, when we look into the precipitation at high percentiles, next click, the precipitation at 99.9 percentiles already, it will increase at high percentiles in the scenario simulations. So meaning that the precipitation will be heavier and more intense in the future. Next, please. I will here I will show you the change in hail and lightning. So the hail observations are in of the first column, and then followed by control simulations and relative change. So compared to available observations over Switzerland, Cosmo tends to overestimate the hail days, so that you see the color bars are different, but the patterns are similar. But and Cosmo does a good job in simulating lighting days, as you can see on the second row. So in control simulations, the north of the Po Valley, the northern pre-alpine region, the Ural Mountains, and Eastern Europe are hotspots of hail and lightning. And if you look into the relative change in scenario simulations, the hail and lightning days over the southern alpine region and the coast of Adriatic Sea will increase. However, over Eastern Europe, the increase is less pronounced. Next, please. Here I show you the change in hail size and lighting potential. In scenario simulations, the frequency of larger hailstones and lighting potential will increase. And for this hail workshop, I looked much in detail for the hail. Please, next slide. I looked into the 5 embryos in Hailcast that initialize at 2 different temperature levels of different hail sizes, 5 and 8, 7.5 and 10 millimeters. Next, please. Here I show you the in control simulations, the x-axis showing the 5 different barrels and the y-axis showing the hail diameter. But I should note that it's not really the size distribution, but it's the hail size, number of grid points, and the hail size on the ground. And in control simulations, if we have larger initial hail in barrels, we tend to get larger hailstones on the ground, which is quite straightforward. And if we have smaller initial hail in barrels, we tend to get wider hail size distribution on the ground of different grid points that simulate hail. Next, please. Next, please. And another click. And another click. So here I show you the result from scenario simulations. Next click, please. Compared to control simulations, we tend to get larger mean hail diameter, which you can find in these red diamonds. And also we tend to get wider hail size distributions of these 5 until 95 percentiles. And to understand why this happened, I looked into the change in hail environment. Next slide. So the first row I'm showing here is the maximum vertical velocity from control simulations, scenario simulations, and also the absolute change from scenario minus the control simulations. The maximum vertical velocity is calculated at every model time steps, and we found increase in maximum vertical velocity, meaning that we have higher energy to overcome low-level stability, meaning that we tend to get larger hailstones and lightning. And for the second row I'm showing here is the updraft helicity that already introduced before, from 2 kilometers to 5 kilometers above ground level. And it's also calculated every 15 minutes. We found an increase in updraft helicity, meaning that we tend to get stronger rotating updrafts, and meaning that it will be more favorable for larger hailstones and higher lighting potential. Next slide, please. I'm also looking into the wind shear from 0 to 6 kilometers above ground level. Another click, please. Here I show you the mean change from scenario minus the control simulations. We tend to get increased deep layer shear, which can promote the sustainability of the storm, meaning that we also tend to get larger hailstones and lightning. And another click, please. But however, we also found increase in melting level height, meaning that we also found a significant increase over Western Europe and Northern Alpine region. This means that the melting process will increase and it will be detrimental to smaller hailstones. So both increase and melting and how they play a role in the final ground hail at the ground, I will show you in the next slide. The first figure showing the in-cloud growth is the difference between the initial hail embryos and the hailstones that leave the cloud. And for the second figure, I show you the below cloud melting, which is the difference when the hailstone leaves the cloud and the hail at the ground. And the last figure I already showed you before. So from control simulations, click please. One click, please. We tend to get smaller initial hail embryos, and for smaller hail embryos, we tend to get larger relative growth within the clouds. And when we look into the below cloud melting, click please. If we have a smaller initial hail embryos, we tend to get larger melting below the cloud. And this could explain that why we get wider size distribution of the smaller hailstones. And when we look into the scenario simulations, we get larger increase in hail size when hailstones leave the cloud in scenario simulations. And when we look into the below cloud melting, and we tend to get increase in melting also in scenario simulations. And overall, the increase in cloud process overcome the melting process, and so that we get larger hailstones at the ground under different hail categories. So in summary, next slide, please. The Cosmo Climate Convection Resolving Climate Model is able to realistically simulate observed severe weather events of hail and lightning. And hail and lightning days are projected to increase with further warming of the atmosphere. And from the detailed analysis, the mean hail diameter is getting larger with the warming of the atmosphere, and the spread of the hail size on the ground is getting wider. And that's it. Thanks a lot.
Do we have any questions for you? Yeah.
Thanks, Rui. That's incredibly interesting. I was a bit confused. I think it's maybe 1 or 2 slides ago. You talked about some of the below cloud melting versus in cloud growth. And how are you calculating that?
So it's calculated within Hailcast, and in the program, I just calculate the difference when the hailstone fall out of the cloud base.
Okay, so you're actually getting in the code and calculating the at cloud base, and then when it reaches the ground, kind of that extra melting. Okay, fair. Then my other question was, when you're talking about the size distribution at the ground, how are you relating the size distribution that you're seeing at the ground to the embryo aloft?
Actually,
over time, or
it's not really like size distribution, but
okay, good.
Yeah, it's not really size distribution. I already note in my talk that it's the size on the ground, number of grid points, and we tend to get on the future climate, we tend to get larger hailstones on the ground. It's not really like size distribution from the hail embryos. I should note that it's not really size distribution. Yeah.
So the distribution that you're showing, it's all hailstones produced by that embryo size?
Yes. Yeah.
At all time periods, all
time periods from 2 years. Yeah.
All right. Thank you.
Any questions online? No. Audience? I actually kind of have maybe a bit of an off-topic question, but there was a large relative change over the Adriatic Sea for a lot of the plots you showed. Why is there such a large change over the water body?
Thanks a lot for your question. I actually don't know, but I guess it might relate to the PGW approach, that the treatment over the ocean is kind of different from land. So I really don't know. I need to look into much detail.
Okay. Other questions? Are there online questions? No?
Nope.
no questions in the chat. Anyone out there in the virtual? Oh, we do.
It just came in. Did you observe hailstones each time you get lightning, i.e. during lightning days?
Yes, it's mostly like we tend to observe more lightning days than hail days. Is that answer your question?
All right, any final questions from the audience? Oh, yeah, sure. There actually is. All right, awesome. Yeah, so yes, I'm very excited about this talk, as you can tell. Yeah, so I'm also very curious, why do you think Cosmo Hailcast overproduced by a factor of, what was it, 3, the number of hail days per 6 months compared to control?
I just compared to available radar observations from Switzerland and also other papers like radar-based papers, and I just found that it's really like overestimate the hail days. But I should also be critical that radar-based observations from Switzerland, like mesh data, that only consider about the hail size that is above 20. So yeah. But hailcasts can produce smaller hailstones, but still, I should say that it's kind of.
Was there one more that just popped in online? Oh, sorry. You have more? No? Okay, thought I saw something pop up. Any final thoughts from the audience? No? Let's thank Roy and all our speakers again.
Start off. Oh, hello. There we go. All right, this will start off really quick. One slide for each poster presenter, a couple of minutes, and it's meant to kind of advertise the work. We're able to do this also with our virtual participants. And our very first one is Stephen Strader, who is virtual. Hi, Stephen. I see you on the screen over there. And it is all yours to start us off. Stephen will be followed by a couple by Matt Comgen. John Allen will be next, and then we will continue on through our list.
Yeah, can everybody hear me okay? Hopefully you can. I just wanted to start off to say, to have a little plug here for our poster that Walker Ashley will be presenting in person. I wasn't able to make it to the workshop this year. But overall, what we're really highlighting here is some stuff that was talked on the morning session, talked about relating to the other parts of why we care about hail, which is the exposure element. One of the things that we've worked on over the last about 5-6 years now is the tornado impact Monte Carlo model. But we've now started applying this to hail events and started this process that was kickstarted, I guess, by Russ Schumacher and Samuel Childs at Colorado State. And we're starting to build the model up and continue to improve it. The idea of the model is that we can simulate hail events repetitively over and over again in a Monte Carlo fashion for the user-defined region and come up with a probabilistic estimate of impacts of hail on the underlying cost surface. In this case, it could be housing units. It could be the number of building footprints. It could be agricultural acreage. It could be any user-defined surface. What is going to be shown on the poster is a sample simulation over the Eastern Colorado domain, and really it highlights some things that we're headed towards. It's not necessarily a perfect model, but it is something that we're working on, and one of the big things that we hope to do in the future is to improve our spatial representations of hail events going forward. So right now we're simulating long rectangles to represent hail events, but clearly that's not an ideal situation. So with that, I'll sort of pass it off to the next person, but please do send me an email, steven.strader@villanova.edu, or ask Walker Ashley at our poster. Thanks.
All right, thank you. So I'm Matt Comgen from Penn State. And so I've got 2 back-to-back here. I'll be quick. The first here is the revisiting thermal energy transfer coefficients for non-spherical hailstones, which I know is everybody's favorite topic. But really, this is important, right? So thermal energy or heat transfer, right? The physics of heat transfer are what are going to control how rapidly the hailstone can grow. That can control the regime wet growth versus dry growth. And all of our models are pretty much parameterized based on one single study from 1963. In 1968, actually, there's 2 studies. So this is showing there's some of the data. We digitized it. We did a little bit of a fit to it compared to what's been used in the literature. And we went through the math behind it. Are we able to click? Real quick. Let's try this. There we go. So went through the theory. So if you're really excited about the physics of heat transfer, come by the poster and you can see all the theory. But basically it comes down to a few assumptions that were made in that original study that they didn't have the technology at the time to sort of address. And now we do have that technology using some of the 3-dimensional digital hailstone models from the IBHS collection and from the Soderholm collection. And so we can look at the impact of these different assumptions and how they actually affect the physics of heat transfer. And so I'll just leave with a picture of some of these models, right? Accounting for the hailstone surface roughness is going to play a big role in that. And so I invite you to come and sort of compare some of these old hailstones, which is the photograph of an artificial hailstone from Bailey and Macklin 1968, to some of the real hailstones and see the natural variability and see if you think that surface roughness is captured from the original study is captured by the actual observations that we see. So thank you. Moving on. And then I said I'd be quick. What is the theoretical upper limit to hail size? A little bit of a fun project. I won't give it away. You'll just have to come find out. But basically, we looked at historical records and we looked at the digital models to quantitatively assess and characterize hailstone shapes in a way that we could try to do different possible renderings of that theoretical maximum size. And so here's one of them, one possible rendering of the theoretical maximum size hailstone, the upper limit of that. So if you want to find out more details and take a selfie with this, feel free to come by the poster at some point. Thank you.
Okay, so I've managed to have a PowerPoint fail straight off and looks like we're going to have all sorts of trouble, but that's okay. I'm going to be talking about in this poster some work that I've been doing looking at how does hail return interval scale from large scales to small scales. Previously, I've done some work that's looked at relatively large scales, 1 by 1 degree type areas, but it's kind of bothered me for a long time. How do you start extrapolating that information to increasingly small scales? And so, wow, this is really failing dismally. It didn't even show up, even better. So if you look at the big white box there, that's actually representative of what a 1 by 1 degree is. If you take an individual pixel, it's one fraction of that. It's like basically the end of that little red arrow that points out towards the 0.4 by 0.04 degree. So part of this has arisen from an interest in things like photovoltaic cells and those big plants that are being deployed out in places like Texas, but also just local risk. And so basically, I looked at a couple of different ways to get at this question. One is to use really, really well-observed locations. What we find is you can use a GV distribution with a relatively heavy tail, and that actually ends up approximating the return interval. And nearly all locations converge to a similar shape parameter, which tends to suggest we've actually found something fundamental there. The other way to approach it is to go empirical. And so on the bottom panels there, you can see examples of some empirical estimates of returns. Now, they're ugly. Clearly, they don't do well for longer returns, but you can certainly get an approximation if you're starting to worry about a given hail size. Maybe the biggest hail size isn't necessarily what you're worried about. It's some sort of critical threshold. So if you want to find out more, come check out the poster in the session.
Okay, hi. Thanks for sharing my slide. And since our understanding in the microphysics is still very limited, especially that in the rammed ice. So in this work, we are trying to find out how does the improved rammed ice treatment will influence the surface hail prediction, and will the improved microphysics influence the storm dynamic structures? And in order to do that, we choose 3 versions of Thompson scheme, including the newly revised MP38 scheme and the 2 existing 1 moment fixed density MP28 and MP8 scheme. Comparing to the previous one, MP38 added the prediction of the grapple number concentration and density, making it a 2 moment hail aware scheme for the grapple category. And our simulation is run with WOPS reservoir. So I will quickly show you the results. The bottom left is the result for the predicted mesh of a moderate hailstorm in Beijing. And we can see that all three schemes can well capture the hail walls, but MP28 and MP8 overestimate the surface hail size, and the hail walls headed more northeasterly, while the hail walls in observation and MP38 headed more southeasterly. And the macrophysical analysis is further conducted to further identify the smaller hail size in MP38. From the vertical cross-section, we find that because of the prognostic grapple number in MP38, the number concentration can adjust itself. So it produced a large, even more grapple number in the updraft region, which then leads to more smaller grapple and hail size here. And we further conducted the grapple mass tendency. We find that because of the smaller grapples and hail size in MP38, it leads to a stronger melting process here. The blue line, maybe it's not that clear. So the stronger grapple melting will then enhance the grapple mass decrease in MP38. And the differences in the grapple size will further influence the storm dynamics. Here we only show the conceptual model. By conducting the vertical momentum analysis, we found out that because of the smaller size in MP38, it will produce a stronger cold pull and stronger buoyancy forcing, which will then enhance the downdraft and cause the storm headed more southeasterly. So that's all. Thank you.
Or a little different, Sean. Well, we're killing this, by the way. This is a lot of fun. Yeah, so back in 2018, this is a video. We'll see if it actually will play. And I'm just going to let this play behind me. IBHS in 2018 did our very first record hail investigation using our 3D scanner system. We actually went out to Coleman, Alabama. Actually, Walter is the name of the town, and scanned what would become the Alabama record hailstone. So you see some visuals of what this looks like behind us. This is some social media video that we use at IBHS, but what the process actually looks like to go out and do this kind of work, along with some pretty pictures of how you 3D scan hailstones in the field. We've now done several investigations looking at the Texas record hailstone. We've 3D printed those. We've tested this just to see if we could fly these things in an iFly wind tunnel. And yes, I have a picture of Andy in the wind tunnel if anyone would like to see it, and Julian. They let us fly. But just to prove we could put some of these massive hailstones in a wind tunnel and look at some of the properties that they have. So if you want to come check out our poster next door on Thursday and talk a little bit more about these record hail investigations going out and trying to verify state record, U.S. record hailstones, even the Canadian national record as well. We were able to help out Julian and the Northern Hail Project through that. So there's just a little bit of what that looks like. I had a little bit more. Nope, that was it. Last video, and that is it. So come find us next door and come talk to myself. Brenna Meisensal and Lucas Faulkner from IBHS are also here, who have participated in our field work and are more than happy to talk to you about what we do with this. So Sean, are yours. Still not, Sean. Still now.
But you are the less, and the less is the best. Okay, yeah, I will present you an update of existing hail climatology in Central Europe. And for Germany, we have already several hail climatology which based on satellite data or radar data, but radar data are the most the powerful remote sensing tool for the indirect hail detection, and especially when you use 3D volumetric radar data. And my work built on the work from Manuel Schmidberger, who had done a lot of here in the last year. And the new hail climatology has 6 years more, and it's now based on a 70-year period. And the climatology built based on hail tracks, which are identified within cell detection and tracking algorithms. And in the past year, we have also modified these algorithms and filter and added some filters, for example, especially in the context of split and merge artifacts. And I will show you on my poster, of course, the spatial distribution of the hail days, but I'm also have some new detailed characteristic about track length, lifetime, cell speed, and cell motion direction. But additionally, we also applied on a sub-sample of these hail tracks the Bunker's supercell motion method. And here the question is, how well does the parameterization of the Bunker's method work for Germany, and should be it's good, or should we modify the parameterization? And here you see two pictures. From the original method and from the modified method, and shown is the difference between the results based on the parameterization, which based on high resolution model data, and on the other side we have the tracks, this information from the hail tracks. And the closer the kernel density function fits the center of this figure, the better is the presentation. But more on this on my poster on Thursday. And here I'll show you first overview, and I hope I see you on Thursday. Okay, and now I hope.
Hi, everyone. Thank you for having us here today. How many folks are familiar with CocoRoS? Oh, good. So I don't have to say it. No, actually. So our poster is going to be about CocoRoS and how we deal with hail data. We've got a 25-year data set of hail in Colorado and about 10 years in Canada. And then we have 25,000 folks across the country. So we've got a lot of people out there and a lot of possibilities. We don't just measure large hail, all different sizes, all different types of ice, clear, hard, so forth. And it's a rich data set. We use these hail pads. You guys are probably familiar with these. I'll have that one up there. We also do something called have our folks, if there's hail occurring, they can report it online. It's called a hail report, goes right to the National Weather Service here in the US, and Paul can attest to it, goes right to their AWIPS, it alarms their workstations and gives them possible criteria for issuing a severe thunderstorm warning. So a lot of stuff out there. You know, we were talking yesterday and of the international inquiries that we get from around the world for data, most of those are for hail. So it's interesting that it's not just rain and snow, but also the hail part. And so that's, as we talk to folks from different parts of the country, I'll tell you more about that. We're going to look at some other stuff on there. So anyway, come by. Are we tomorrow or next day? Anyway, come by and see the poster. Thanks.
Didn't want to preempt it if it wasn't my turn yet. Those of you guys that have been clamoring for more hail observations already, just today so far, if you're really interested in hail observations, I have a poster on Thursday. You should come by, and you should definitely come to Kyler Ortega's talk tomorrow morning at 8:30, because we're going to blow your mind with hail observations. Sorry, I keep touching that. Most of our hail observations, you guys know, are based post-impact, right? Somebody goes out, they see it, they collect it, they pick it up. It's broken, it's shattered, it's melted. It may not even be the same size that it was when it failed. So we set out with the intention of capturing observations in hailstones in free fall before they impact anything, which is really, really difficult to do, considering it has to survive, like your instrument has to survive, and it's got to be really fast. So some of the images that you see up there are actual pictures of real hailstones. Those are not, modeled hailstones. Those are real hailstones that fell in various parts of the United States this year when we set out to capture these. And we're actually using two different, very, very expensive cameras that are moving very quickly to position those hailstones in a three-dimensional space in the back of a moving pickup truck. It's not moving while we're collecting data, but we can move around and we can move under hailstones. So we can three-dimensionally position where those objects are and then use the frame size to actually figure out how big the object is and then track it over time so we can see movement, we can see rotation speeds, we can see velocity information information, not only in the vertical, but also in the horizontal. So we're getting tons of observations from real hailstones in complete free fall before it has a chance to impact anything. And you can see an example there in the bottom right corner. That's a very oddly shaped hailstone that's actually rotating quite rapidly around its central axis. Depending on whether you ask Kyle or I, it's either rotating at 60 hertz or 125 hertz, which is moving extremely fast for a hailstone that at that point is about 1.5, 1.2 inches in diameter. I will also point out right before I stop talking that some of the larger hailstones that you see up there, they can have a lot of spikes on them, and we know those spikes are going to break off, and we can actually estimate that stone with the spikes on there is about 2.3 inches. It's about 1.9 if you remove all the spikes. So how much of the hailstone are we actually missing when you go and collect those observations after the fact? So if you're interested in more, come to my talk, come to Kyle's talk tomorrow.
All right, that was really cool. Even with the glitches, I thought that was a lot of fun. So please check out all the posters. We will go ahead and continue on with our session, our last session of the day, and continue our talks.
Hello, everyone. I'm Xiao Li from China. It's my pleasure to share my presentation here. This work is mainly co-authored with Zhenghong Zhang from Peking University, Jiwen San from GNNL, and Fuqing Zhang from Penn State. Next, please. Next, please. There. For hail formation, according to classical theory, we know that a hailstorm may be kicked off under some necessary meteorological conditions. For example, instability, vertical wind shear, updraft, temperature.
I'm sorry to interrupt. Your audio is not coming through clear. You might want to change microphones. It's not very audible on our end.
Can you hear me clearly? No?
We can't hear you very clear.
Hello? How about now?
No, it's not better.
Not.
I changed my microphone. How's it now?
Much better. Much better. Thank you.
Much better. Okay. Okay.
Yes.
Okay. We go. Sorry. Also, it's necessary to go with microphysics process from cloud-based to hailstone generation. Aerosols may serve as CCN or IN to affect the storm, and the affecting process is very complicated. Next slide. Until now, uncertainty from initial condition in numerical models has long been one of the most difficult challenge for forecasting convections, especially for damaging hailstorms. The concept of predictability has been put forward very early as the butterfly effect has now been popularly categorized into practical and intrinsic predictability. At present, with these uncertainties remain sizable in initial conditions for a hailstorm, there is still a lot of room to analyze the related uncertainty and to improve the practical predictability of hail. Next, please. Many studies revealed that increased aerosol particles can be activated to form additional cloud water and lighter heating, thus intensifying convective strength. However, aerosol cloud interactions remain the largest uncertainty in climate projections. For some recent studies, it has been found that the model dynamical and the microphysical properties are sensitive to both the environmental and the microphysical uncertainties in the model. CCN concentration is an important parameter contributing to the output uncertainty if only the environmental conditions are varied. It has been put forward the idea that ensemble methods would be an effective way to investigate and to reduce uncertainties from aerosol effects, but the uncertainty in ensembles is still unclear. Next, please. Based on the above-mentioned background, we made a comparison of hail predictability with different initial observations from flow-dependent climatological and aerosols uncertainty. We firstly chose the same idealized case in China. This idealized hailstorm is triggered by a thermal bubble in WRF with NSSL scheme. This input sounding is treated as a basic state to generate flow-dependent initial ensemble input soundings. Ensemble perturbations from ECMWF operational 50-member ensemble were used. We calculated the differences between each of the 50-member and the ensemble mean. Then, these 50 profiles of differences were added to the basic input sounding to obtain 50 initial perturbed soundings. We conducted additional simulations by isolating the thermodynamic and the kinematic perturbations individually to assess the main factors. Meanwhile, the same three sets of ensembles described were repeated, but with initial ensemble perturbations reduced to 10% of their original magnitude for intrinsic predictability. Next, please. In control ensemble, the members displayed a considerable spread in peak values of hail precipitation rate. That means small flow-dependent perturbations can lead to significant differences in hail precipitation rate and cloud processes. To investigate the sensitivity of hail precipitation rate to initial thermodynamic and kinematic perturbations, correlations between hail precipitation rate and the initial soundings throughout the vertical layers were calculated. It was strongly correlated with the thermodynamic factors. However, the kinematic perturbations exhibited a different and relatively weak correlation. Next, please. Then, we compared the uncertainty in different ensembles. The uncertainty is represented by ensemble spread here. TQ here represents thermodynamic perturbations only, and UV is for kinematic perturbations only. It reveals a thought that thermodynamic perturbations always generated a larger ensemble spread than kinematic perturbations, regardless of whether the initial perturbations were of original magnitude or reduced to 10%. And a similar trend can also be found in total precipitation. Next, please. To make the comparison of hail predictability with initial perturbations from flow-dependent uncertainty and climatological uncertainty, we followed the previous method for the ensemble simulation, but the climatological uncertainty is from ECMWF ERA 20th Century project. And the generation of the input soundings are the same as the method for flow-dependent ensembles. The right figure shows the comparison between these two perturbations. The perturbation seems different, but are quite smaller than its original magnitude. Next, please. F. In this slide, F represent flow-dependent ensembles and C represent climatological ensembles. Here we can find that the response of practical predictability of hail to climatological and flow-dependent uncertainty are on a comparable order of magnitude, although the climatological perturbed ensemble generated a larger ensemble spread than flow-dependent ensemble. Next, please. To understand how the CCN will affect uncertainty in hail precipitation based on the flow-dependent ensembles, 5 additional sensitivity ensemble groups were performed by varying CCN number concentration from 100 to 3000 per milligram along the x coordinate. As a result, in total, 24 groups of ensembles consisting of 1,200 runs were configured. Next. To assess the predictability in a more qualitative way, we calculate the ratio of ensemble means to ensemble spread, which is defined as the signal-to-noise ratio. A larger signal-to-noise ratio means higher predictability and lower uncertainty. Firstly, the values for the hail precipitation rate are a few times lower than those for the total precipitation, suggesting hail is more sensitive to the initial meteorological perturbations. Most importantly, it is a non-monotonic response for hail, but a decreasing trend for total precipitation. That means the CCN modifies the predictability of hail precipitation with higher predictability in moderately CCNC environments. Next, please. We also calculated a ratio to compare every ensemble spread over the control ensemble. If we focus on the difference between the darkest red and the darkest blue in the bottom ensembles, it's more than, we can find the value is more than double. So we can say that varying the CCNC can cause even larger uncertainties than the meteorological perturbations in the hail precipitation. If we compare them horizontally, we can find that varying initial meteorological conditions does not qualitatively change the aerosol effects. And the thermodynamic perturbations always produce a larger uncertainty than kinematic perturbations. If we compare them vertically, we can find that in the very clean conditions, hail precipitation rate is more sensitive to meteorological perturbations compared with it in the very polluted conditions. Next, please. To explain it, we examined the corresponding cloud dynamics, latent heating rate, and microphysics. The enhanced updraft velocity by CCNC prior in reaching the optimal CCN value may be due to the enhanced latent heating from mainly from condensation. The season effects on latent heating and the condensation heating resemble the season effects on the hail precipitation rate, suggest a close relationship between hail and condensation. When CCN is increased beyond the optimal value, the condensation heating increases slowly, with great increase in deposition heating due to the enhanced ice-related process, particularly for the small particles. Next, please. The last is a summary of my study. I will not repeat it, but I'd like to say there is still some other uncertainties in this study. For example, cloud physics, thermobubble, convective initiation, different soundings, and so forth. So more sensitive ensemble test seems in need. Next, please. Here are the references. Next, please. Thanks for your listening, and the comments and the questions are welcome.
Here or online? Anything online? Any questions in here? Okay, I'll ask one, Xiaofei. So very interesting that the aerosols have such a strong effect. Is this also with the Thompson scheme? Can you remind me of the microphysics scheme that was used for these?
We didn't check another microphysics schemes. We used the NSSL scheme.
Okay.
And maybe we will do it in future. Thank you.
Yeah. Other questions? Oh, the question from the audience was which version of the NSSL?
Sorry, pardon?
Which version of the NSSL microphysics scheme?
NSSL. It's Wolf version 4.
All right, thank you. Other questions from the audience? No? All right. Let's thank Xiaofei again. Thank you, Xiaofei.
Thank you.
All right, next up is Jason. So.
Hi, everybody. Nice to be back in Boulder. So my name is Jason Milbrandt. I'm a research scientist at Environment Canada. Before I get started, I should introduce my co-authors, but I'm not going to. I'm just going to start. So one of the things about the challenge of modeling hail that's interesting is that practically all aspects of cloud microphysics ultimately go into hail. You can't neglect anything. Maybe to some extent you can neglect details with computation of diffusional growth of crystals and so forth, but basically everything is important. And ice microphysics is particularly challenging. Typically in microphysics schemes, and this applies to both bulk and bin schemes, ice is partitioned into predefined categories with parameters that are either fixed or within a small range for their physical properties. And so typically you've got, which gets referred to as ice, snow, graupel, and hail. Some schemes maybe have more or less or something, but this is basically the way it's done. And then besides the growth process of the individual particles categories, then you have this conversion between the particles. The problem, there's a couple of serious problems with this predefined category paradigm. First of all, real ice has a wide, it doesn't fit into sort of predefined physical parameters like density, the way water does. Here's an example of rime density, which is sort of all over the map. And the other thing is that because of the partitioning into categories, you have to convert from one category to other. And that's a purely unphysical process. There's no such thing as conversion of ice to snow or anything else. And that is problematic in models because it's artificial, it's unconstrained, and it's the reason there's so much variability in the results from microphysics schemes. So let's see. So after years of trying to improve our traditional microphysics, traditional microphysics schemes that Hugh and I each developed independently, earlier, we finally just got frustrated and decided we need to just abandon that predefined category paradigm and start with a new approach. And so the approach, and we constructed a new scheme, which we call the Predicted Particle Properties Scheme, P3. So it's based on the premise that within a single ice phase category, you can represent a spectrum of ice particles, and where the physical properties such as bulk density, et cetera, actually evolve continuously in time and space. And this has the benefit of completely eliminating the necessity of conversion between predefined categories. So this is I'm just going to give a quick overview of the P3 scheme, then get into how its capacity to model hail. So the liquid phase is a sort of a standard two-moment, two-category scheme. Ice now has a user-specified number of what we call free categories, so they're unconstrained. And so there's between 4 and 6 prognostic variables. So there's up to 3 mass mixing ratios for the ice from depositional growth, ice from riming growth, and now recently, boy, these fonts really got messed up here, from the liquid. So now we can represent mixed phase particles. It's double moment, no, well, there's a double moment option for the number concentrations. We predict the volume mixing ratio, which allows the capacity to model a continuous volume. So according to Ted, we're now in the cool kids club. And then also the 6 moment mixing ratio, which allows the representation of a variable spectral diffusion. From these prognostic variables, then you can compute these various predicted physical properties. And if you wish, you could, based on the properties, diagnose the particle type. But unlike traditional schemes, what you call it has no impact on the solution. So this is each size category is represented by a standard 3-parameter gamma distribution. But unlike traditional schemes, now we actually, in different parts of the size distribution, we apply different mass diameter parameters. And this is based on this conceptual model from Heimsfield AD2, I believe. And the thresholds themselves vary, and in some cases, depending on the density and so forth, the parameters themselves vary. So this is another sort of illustration of how that would work with different rime fractions. So if you have unrimed ice, on the left, you just basically have tiny crystals and represented as high density spheres, and then larger crystals with a mass diameter of exponent of about 2. And then on the opposite extreme, it's dominated by graupel hail. Under the hood, this is about as much details with equations as I'll get, but just one of the things about this, because so in microphysics schemes, all of the process rates and parameters like effective radius and so forth are typically computed by, they're proportional to some moment of the size distribution. And if you have fixed mass diameter parameters, you can compute these analytically. But because we have these between 2 and 4 size regimes, has to be done numerically. But that's a pro and a con. We compute these offline and store them in lookup tables. So one of the advantages of this is that the integrals are accurate and they're also quite fast at runtime. Okay, so that's enough of, boy, this, I've never seen this before in years where my symbols get mucked up. Oh, well. So this is an example of an idealized squall line simulation. I'm not showing the prognostic variables, but these are the rime fraction, bulk density, fall speed, and mean mass diameter. And this is all with a single category. And if you take a look at the X and the convective core of that, just look at the properties. It's fully rimed, very high density, fall speed over 10 meters per second, and mean mass diameter of over 5 millimeters. So you could call it whatever you want, but it sort of describes high density graupel hail. So this is another illustration of that. This is an actual operational NWP run. Again, a single ice category, whereas in the middle is the total mass, and on the bottom left is just this sort of I built this decision tree just for people that want to see the familiar categories. So it's not actually discrete like that, the way with the categories, but it's just if you apply this. And as I said, that the way you define these thresholds in terms of defining if you want to diagnose a category has no bearing on the simulation. So that's neat. You can simulate a wide range of particle types. But of course, with single category version, you can't simulate a dominant particle type in one place in time and space. But I'll get to that later in the talk. Just a brief comment. Since our original paper in 2015, we've done a fair amount of major developments to that. Ultimately now, I think with this combination of liquid fraction and triple moment, we're now ready to start seriously looking at hail simulation. And just a comment, we do actually use this scheme operationally in our 2.5 kilometer model in Barb, Canada. Okay, so this is kind of interesting because up to this point, 4 years ago at the first North American Hail Workshop, I think I got up here and bragged about how great P3 was and its unlimited capacity to represent ice. And during the workshop, I actually, this hotshot PhD student at Oklahoma University had the nerve to send us this draft paper basically showing that P3 sucks for its capacity to simulate hail. So that's good. I mean, that was useful information. So at the time it was 2 moment. 2 moment schemes do a remarkably good job in modeling gravitational size sorting. However, because the mass advects faster than the number. At the tail end, at the leading edge, you get these unlimited sizes. So we've solved that originally by brute force by just imposing an upper limit. And as a result, though, it really limited the capacity to simulate hail. So Marcus Johnson did this. These are results from idealized hailstorm simulations with run through a dual pole moment simulator. And you can see that the two schemes that actually have hail categories do not too bad, but P3 is completely missing this radar signatures, dual pole radar signatures. So we could have probably improved that, tuned that in various ways, but based on previous experience, we felt that the correct way of doing this, the best way of doing this is to go to triple moment, in which we, with that, we add a new degree of freedom in the size distribution. And so now all three of the parameters are independent parameters. Typically what happens in two-moment schemes is the shape parameter mu is fixed. It doesn't actually have to be fixed. It can vary, but it can't vary independently. And just to illustrate the impact of the shape parameter, those two gamma distributions, the red and the blue, have the identical mean mass diameter, but clearly the broader distribution has higher concentration of larger hail. So this is something I had toyed with. Oh my God, these equations really got fouled up. Looks like I'm not the only one that suffered from doing my presentation on a Mac. Anyway, so the idea is that with triple moment, you can actually exploit that even though it's a bulk scheme, you can actually, in principle, get some useful information for the maximum hail sizes just by looking at that, the number of concentration in the tail there above a certain threshold. I won't go much into the detail of the techniques that we've used. It's described in this paper, but basically, for the tendency equations for the sixth moment, we've got three groups. The first is when the formal correct way of modeling it is known. At the moment, we just do that for sedimentation. Group two is when for ice initiation, in which you have to assume something about the initial width, the distribution. So, we assign a given mu. This is exactly analogous, by the way, to like assuming a mass of an initial crystal for primary nucleation or whatever. And then group three is just we assume do no harm and keep the size or the shape parameter constant. Our next sort of piece of development is actually going to put all the group three things into group one, because we can do this numerically. We can do all of the DZDT process rates. So that will be relaxed. Okay, so some results. So this was a high-resolution, quasi-idealized hailstorm simulations using 2-moment and 3-moment, for which we've made some comparisons to some observations. And the punchline here is that with 3-moment, you get you increase the reflectivity, or some of the high reflectivity, and more importantly, you actually get hail. So this in the bottom, DH max. Okay, that's for our diagnostic based on that tail of the distribution. And if you take a look at the storm itself, you get in the bottom right, you can see this is the precipitation rate, and the red is the hail. Oh no, I think that's the total. The total accumulated and the max size, I guess. So basically, we've definitely relaxed that problem limitation with the 2-moment and increased the max hail quantity and size of the surface. Okay, more recently, our new colleague, Melissa Cholette, for her PhD, she took P3 and introduced a new prognostic field variable, the liquid fraction, in order to be able to represent mixed phase particles rather. So it's just the mixing ratio of liquid, which now we defined a new property, the liquid fraction. So I won't go through all of these processes. In blue is sort of how it used to be represented, and red is how it can be represented now with prognostic liquid fraction. And certainly some of the processes pertain to hail modeling, in particular melting and shedding. So for melting, for example, previously there's no liquid fraction, so as soon as a portion of the ice melts, it goes instantly to rain. There's no retaining any of the capacity, any of the liquid in it, and same with wet growth. So in principle, this should improve. I'm here for about a week and a half visiting Hugh at NCAR, working with NCAR. So we just decided to move on to, we're testing this now in NCAR's CM1 model. So we put in the new version of the scheme just over the weekend and ran these simulations. We got these results just yesterday. So this is quite hot off the press. But I think the results are kind of interesting. So this is just from out of the can quarter SS Clamp and Wilhelmsen sounding in the model. And these are just 1 kilometer simulations for now. Like I said, we're just getting going, but we'll go to high res later. But there's already some interesting results here. If you squint your eyes a bit, it's a little bit unclear, but you can actually in the I don't know if you call that the stratiform region or the forward flank or whatever. In the melting layer, you can see a boost in the bright band with the liquid fraction on. A bit of a change in the reflectivity. Okay, I'll get back to physical properties next slide. So now we've also got, as I mentioned, we've got the capacity to have more than 1 ice category. So we still believe in categories, just not constraining them and calling them by certain names a priori. So in the third column is with 2 categories, and the third is with 3 categories. I can't say if there's an improvement. I can't if these results are any good or not, because this is a highly idealized case. It's not even a real sounding, and certainly there's no observations. But at least this gives an indication of the impact of these new components of P3. And so maybe I think the next slide is a bit more interesting. Disregard the component, the multi-cat for a second. So Gesundheit. So you can see that this is a triple moment 1 category only, liquid fraction off on the left, on in the middle. And you can see that the mean mass diameter is reduced. I didn't get around yet to plotting the max hail diameter. So just because the mean mass diameter is smaller doesn't actually mean there's less large hail. I'll have to get to that. But and the bottom is the density. And you can see in the down forward flank right around the melting layer, as it's melting, it's densifying. So that appears to be some degree of increased realism. I'm not showing 3 cats, don't have time, but for 2 categories, now on the right, the column 3 and 4 are ice category 1 and 2 from these 2 category simulations. And so the total ice content then is the combination of the Q total from category 1 and 2. If you wanted to make direct comparisons, we'd have to add them. But these results are kind of interesting. I mean, it's you definitely in category 2, and it just does whatever it does. It's not, we don't say that one's the large hail, but it just turns out in this one that the second category is definitely where you get the larger hail. You get some high density stuff in category 1, but it's obviously quite small. It doesn't reach the surface and so forth. So that's quite neat. So this is why my claim is that we've made some progress to increasing, what's that? Oh, sorry, I thought that somebody was waving at me like time's up. I expect I have slightly 1 or 2 minutes. Hugh, do you have anything you'd like to add to this that I haven't brilliantly mentioned? Oh, one of the things before you say it is that one of the advantages of having 2 categories is, especially at high resolution, is that with 1 category, even though you can represent everything from ice crystals now to high density hail, you can't have graupel and hail in the same grid box. And in nature, you get an updraft, you get graupel, and the hail is either suspended and saying, waving goodbye to the hail as it flies up, or falling through it. So in principle, we should be able to improve the simulation of hail with 2 categories. And where are the reflectivities? There may be some evidence of that in the reflectivities. Although I know what he will say is like you're cherry picking individual cross sections and you move it over by 1 grid point and it looks a little bit different. But as I said, this is preliminary stuff. I literally did these plots last night and saw them for the first time then. But we're encouraged. And the next step is we're going to actually use a much higher resolution, probably 100 meters, so that we eliminate all complaints about it's not a cloud resolving scale. And we're going to do a modeling study on the Calgary hailstorm, which happened a couple of years ago, and which I assume Julian will be talking about tomorrow, and really investigating the capacity of this new configuration to represent hail. So in summary, I think we now have we've done various developments, and I think we're now really quite versatile with the combination of multiple free categories. I haven't mentioned it, but we have a subgrid cloud fraction version, and the variable spectral dispersion. And certainly it's quite interesting with mixed phase particles. And for winter precip, that's a really interesting thing. At least where I live in Montreal, we get a lot of mixed phase stuff. And so I would, even though Matt and his team will probably say that, yeah, you're totally missing, you're still assuming sphericity and so forth. It's a model. Obviously, there's a lot of simplifications. But I think that we're really at the point now, or at least nearly at the point where this can be used for actual bona fide process studies of hail. And since I come from an operational center, I'm always sort of thinking of operations. One might assume that this level of detail is great for research. It's completely unfeasible for operational weather prediction. I'm more optimistic of that. For one thing, as I said, the P3, all the process rates, and P3 is quite fast because it uses lots of lookup tables. And now we've got 6 variables per ice category. And if I'm arguing that we need 2 of those, then we're talking about 12 variables. It's getting to be some godly expensive scheme like NSSL. Just kidding, Ted. That's my second favorite scheme. But actually, with all of the ice categories lumped in within the same, with all the like 6 prognostic variables per version, per category, ice category, it actually lends itself really well to some new advection techniques. So in a scheme like WRF, with uses Eulerian advection, you can actually cut off a lot of the cost by just advecting one lead variable, and then the other ones is just minor costs in that. And of course, computer power, as we know, is increasing a lot. And that 2021 triple moment paper, we actually compared 250 meter, 1 kilometer studies, and 1 kilometer is actually you get more or less get the same conclusion. So the duck is being optimistic about the forecast for the likelihood of explicit operational hail prediction. By explicit, I mean where the hail size and hail swath is a direct model output, not diagnosed from environmental conditions and so forth. By the way, the duck is our mascot. Oh, I shouldn't have called it a duck. I should have said that animal there. The reason it's our P3 mascot is because without any label on it, you know exactly what it is just by looking at the physical properties. So, c'est tout. Merci.
Thanks, Jason. We might have time for a very quick question. Not, yeah, go ahead, Becca.
A realistic, explicit numerical hail forecast.
Those runs we did at 250 meters, and we reran them at 1 kilometer just because, as I said, I work in a weather center, so I want to know the answer to that question. My sense is that even though you're not resolving the updrafts as well, you're doing pretty good. I mean, the answer, operationally speaking, I'm not sure if that's my reflex is to think operationally, is it good enough to be a useful forecast, regardless of whether or not the dynamics people will say you're not really resolving it. You call that a convective permitting allowing resolving model. But if you're thinking about, actually, you're probably thinking more a research question. I mean, I think.
Right? When can you turn off your parameterization of it? Yeah,
I mean, I've worked for years on this operational 2.5 kilometer model, and it's we have the old version with 2 moment. Even at 2.5 kilometers, it does pretty well. Certainly for squall lines, maybe for supercells, but actually there were a lot of supercells this year in Alberta. And it did remarkably well. I think probably the updrafts are dramatically underestimated. The updraft strength is too weak at 2.5. But I guess the answer to your question is my guess would be about 1 kilometer, and you start to being able to do everything just within the microphysics scheme of the model. That's my sense. Yeah. I guess I talked too long ago. Thanks.
Thanks, Jason. No? All right, next up, we have Sarah Tessendorf. I think will be virtual. Oh, there you go. Okay. You've changed since I last saw you, Sarah. You want to get back to that one?
Don't leak it out. All right. So good afternoon, everybody. My name is Sarah Tessenthorpe, apparently no. My name is Lu Ling Xue. So accidentally, I'm the speaker of next talk. So right now, I'm the only person standing between you and the food. It really depends on how many questions I get, and then so that how soon you can get the dinner. I have to say sorry for Sarah. She would like to be here, but unfortunately, her daughter has the birthday party, so she has to accompany her daughter. So I'm giving the report representing the whole team. So the title is a new version of Thompson Microphysics aimed at better simulation of hail. And I have to thank Jason to really lay the foundation of a lot of important concepts that I'm talking here, because we all know to represent different hydrometeors, especially like Graupo and Hail, we definitely want to have the prediction of the density itself that closely related to the fall speed and also the growth rate and all that details about precipitation rates and the impact and size. And of course, if you look at the picture of different type of precipitation, ice phase precipitation, like rime, snow particle, and the Graupo and the hail, they're quite different. And the fall speeds, as a relationship shown on the right-hand side, varies a lot. So we really want to find a way, try to build that into the model similar to the P3 concept. So our solution to really address this using in the past, we have only single moment to predict this category, but now we're trying to do a better job. So we decided to add another moment to the Graupo category. Before, we only have one moment for mass, and I have to diagnose a lot of different parameters to come up with the distribution and also the sizes. But now we are adding the number concentration or a number mixing ratio into the scheme to make it a two moment. Also, similar to the P3, we add another prognostic variable of the volume mixing ratio to represent or to help us predict the density. And after the implementation done by Greg and also Anders, they went ahead and using a Pecan field campaign kind of IOP to test this specific version of the microphysics scheme. Here is the case that occurred in the South Dakota. You can realize you can find that the radar observation showing at about 7 UTC, the system still within the central or close to the central of the South Dakota. But in our simulation, MP20A is the original version that we have only one moment, Graupo and Hail. And the MP30A is the new version that we have 2 moments and also predicted the density features in the MP38. Now, both systems move a little bit further kind of ahead and moving faster than the observed storm. But generally, they look slightly different, and having the MP30A version, the new version, has a more higher reflectivity region and stronger bowing of the system. In order to really compare the old approach and the new approach, we assess these distribution of the reflectivity in compared to the Sioux Falls radar signals. So higher up, around 9.4 kilometer, we noticed that the new version of the scheme actually reproduced the tail distribution better than the old one, as the top 2 rows at the top row on the right-hand side indicated. And on the close to the ground, we also see that our new version slightly improved upon the higher reflectivity frequency, but both schemes still have issues in the smaller or weaker reflectivity beams that we overestimate this weaker value. And we also can use these diagnostics to look at the hail sizes on the ground. This hail report indicated by the symbols, the color represent their sizes, showing that the report shows in the arrow area, the point that the arrow pointed to, have relatively large size that the MP28, the old scheme, couldn't capture. And on the right-hand side, the new scheme actually produced a wider area of these large hail on the ground and gets a better agreement qualitatively based on these map and the spatial comparison. And we also did a quantitative comparison comparing these reports, just size, not size distribution, the PDF, the density of these reports. We noticed that the original approach of the one moment kind of concentrated in a very smaller size beam and never captured those large hails on the ground. And the new scheme, by defining the maximum size by two different ways, either through the number or through the mass mixing ratio, we're able to capture some of those occurrences in the larger spectrum. So that is a improvement in our mind. This new approaches will give us, and we also went ahead and compared the mesh analysis. So here on the right-hand side, on the top row, that's the radar kind of derived mesh value. And we noticed from the MP38, the new version, we actually have a more concentrated area that have a higher value of these maximum hail sizes compared to MP28. We're kind of over predicting a large area of relatively large particles on the ground that apparently disagree with the radar derived value. And so this also give us a kind of confidence that these new development is moving towards the right direction when we try to simulate the hail properties. And then doing the same, we just make these count the values and then do the PDF. We notice MP38 definitely capture wider spectrum of the sizes on the ground. And also in terms of the PDF itself, we also reduce this kind of a mid-level, mid-size of the particles, and then spreading out to the large end. This is the first kind of the round of evaluation and validation of the scheme itself, and it at least proved to be reasonable based on our understanding. And this plot or this slide shows a validation of the cold pool evolution from these different simulation using different schemes. And observation is indicated by the black dots, which shows the cold pool passage that have a indicating more gradual kind of a reduce of the temperature, surface temperature. And our model indicate a very quick a sudden drop of these temperature, indicating strong cold pool. And also the earlier time occurrence of these model cold pool passage also indicate we have slightly stronger cold pool strengths compared to reality. But looking at the lower right corner for those comparison, the new scheme, the MP38 in blue, shows a slightly delayed of the passage of the cold pool and gradually reduce of a temperature in better agreement with the observation at the site. So we conclude that this improved microphysics try to simulate the density and then gets these larger, faster falling particles that reduces the melting and also subsequently reduce the cold pool strengths that lead to this better agreement with the observation. But of course, we need more data and more validation cases to really prove that's the case for most of those severe storm. And here is another comprehensive evaluation case study that we did after the first round of the evaluation put into the paper. Here is another case for the I couldn't remember which experiment that is, but maybe just because this is a day that we have strong strong convection and with a lot of hail report. So we simulate this case using 3 kilometer and using error 5 as our initial and boundary conditions. And that's the regular WRF physics we use for the specific setup. And here we define using the mode in the I think that's the MetPlus software, that we identify objects using different threshold, try to compare how the model simulated objects on the ground, precipitation objects on the ground compared to the observation. So we have 2 different categories. One is more small scale, more intense, higher intensity type of a threshold that we have to define the element or the object has to have 2 millimeter per hour precipitation rate, and then have a continuous 15 kilometer in the dimension of the object. And then on the other side, we have a large scale with lower precipitation intensity and also bigger area of coverage. So by analyzing the model data and the observation, we kind of have a reasonable numbers of objects from both simulations compared to observations. But in terms of the matching objects, the population just become much smaller. So inherently, model is not perfect. So we cannot really capture these individual elements exactly as they observed. But we are actually simulating the reasonable population of these either swap or high precipitation entities. And that's where we start to composite our simulated features here to compare with observation. And first, we wanted to look at the propagation speed and also the lifetime of these individual objects. So from now on, everything on the left is every panel have 2 subpanels. So on the left-hand side, that's for the large-scale, low-intensity objects. And on the right-hand side is the smaller scale but higher intensity elements. So by looking into the propagation speed on the left-hand side, basically both schemes simulate relatively in good agreement with observations. And on the right-hand side, the duration we have slightly difference in terms of a simulated result and the observation. But no matter what, I think the distribution didn't show any statistical difference at all. So we basically have simulate very similar kind of the statistics out of these 2 for duration and for propagating speed. If we move on to look at the precipitation intensity, and now we see some slightly differences, especially for the very high percentile, 99% percentile, that the smaller, more intense kind of the elements, the model seems to overestimate it. And for the new scheme, it slightly performed better in terms of the precipitation rates for the large scale elements or precipitating elements. So basically, it's very hard to tell the difference from those analysis. Here is the place that we show some big differences. That's the hail coverage area, and the MP20A for the smaller intense elements seems to agree with observation better in terms of mean, but then the spreads are still not in a good agreement with the observation. 30A slightly reduced that coverage area, but if you look at the broader or more kind of the weaker elements as the objects, MP30A actually improve in terms of the hail coverage region and even the spread compared to observation. So we see some advantages, but also some kind of the similar features to the original scheme in these first cut of validation. So here I would like to provide a quick summary for this specific work. That is, we actually develop or actually implement a 2-moment Grapple and Hail version of Thompson-Eidhammer microphysics scheme. That these new MP30A scheme increase the hail sizes in better agreement with the report and also the meshed data based on the pecan and another validation case from May 2019. And we slightly reduce the storm duration and in slightly better agreement with observation based on the results I show. And also we have some evidence that indicating a reduced cold pool strength due to the faster falling high density particle and compared to observation. And this version of the microphysics scheme will be available soon in the next released work version. So I'll stop here and take any questions for Sarah.
Hey, Vivian. I saw Sarah's presentation in Madison a month ago. You did a great job in reproducing it. And I know you're neither Greg nor Anders nor Sarah, but I just want, I'm really happy. I think it's great development for this. Just a further up of my comment I made in the previous session with the aerosol aware component of this new development really further makes the aerosol aware component even more valuable. The point, I don't know if I was coherent when I explained that before, but because you've got more realistic aerosols, you got more realistic drop sizes, that impacts the grapple and so forth. So yeah, food for thought, anybody. That's a really, in my opinion, this is probably one of the MP38 is probably the best scheme for testing the CCN sensitivity now for in deep convection. Anyway.
Yeah, thank you, Jason, for the comment. And I remember you had that comment saying if your scheme cannot really predict the density of the ice phase precipitation, then your CCN aerosol impact might not be well reflected. And here we combine both in these MP38 that you can really look carefully into this very specific aspect. So thank you, and we're trying to do that. So yeah, thank you so much for the comment. Any other question?
Anything online?
I'm hesitant to ask this because it probably doesn't have an answer. Kind of thinking a little bit differently about the PBL scheme. Have you tried looking at, basically the same experiments, but with a different scheme just because of the biases and the YSU versus like the MYJ schemes, just to see, which obviously if you change your PBL, then you're changing your storm. So it may not actually be a question, but I don't know, just something I was kind of thinking about.
Yeah, it's a very valid question because we also believe the interactions of different physics can change your results dramatically. And in my next talk, I will not show that because we have just done it and we haven't got time to put the result together, but we did it. We actually did a test running different PBL, but exactly the same other physics. And sorry that I haven't put that together to show. So, but we'll keep you updated when we have new results.
Maybe that would be a good segue into your next talk. Sure.
Yeah, I really like Matt being the chair. He kind of pushed the session really fast. And this is the first time I actually seen a workshop or conference that's ahead of the agenda. So, okay, then I'll try to make everybody comfortable after a long day. So this is the last talk of today. So it's still given by myself. And thanks to Sarah for the layout of the foundation for my talk, because I now will use MP28 and MP38 without explaining what they are. So here we go. So we actually use the same scheme, actually simulate another strong, severe storm in the South America. As part of a relampico. So here is the basic outline of the talk. Then we talk about the goal and explain and introduce the relampico a little bit, and then we'll show you what the differences are based on this very specific experiment. So there are two goals for this very specific work. So first is test the newly developed scheme. And unfortunately, I haven't done the aerosol sensitivity in this talk, but that's also on my to-do list. So PBL, I just did it. And then the aerosol one is actually the next one I'm going to look into. Here we run these Relumpical IOP-17s, which is a very severe storm with back-building feature that produce a lot of damages you will see in a minute, and then try to see how good or how these two different versions of the Thompson scheme compare to each other. Then especially I want to show those differences in terms of dynamics, microphysics, and precipitation. Relumpical field campaign represent remote sensing and electrification lining and mesoscale microscale processes with adaptive ground observations, really long name. Here is the map showing the field campaign area. This is a very large campaign that actually accompanied by DOE funded a cacti field campaign as well. So more flights from cacti and ground observation from both cacti and Relumpical. This area is believed to be a hotspot on Earth that produced the strongest thunderstorm and largest hailstone, probably largest hailstone on Earth. So it's a great kind of a test bed for evaluating any hail model simulation. We leverage that, and here is a quick. So I saw a lot of mismatching of taxes and figures. So I apologize that some of those texts are off the line, but here are just a basic description of the Relumpical instrument deployments and also cacti instruments. And on the right-hand side, we'll summarize the different IOPs and the focus of different IOPs. And IOP 17 is the next slide. Will show just example how it looked for this specific case. It only lasts for like 6 hours for this IOP, but look the evolution of the storm from early from like 23:45 on December 13th, that the continuous building of those convective elements close to the radar site. It's a C indicated by the character C on the plot of the top left. And then the central column indicate these radar, the C-band radar observations in the middle of the field campaign from 2 o'clock to 3 UTC. That storm quickly grow to a very large MCSs and produce hail as large as 5 inches-ish, hailstones and strong wind and flood. So all kinds of damaging phenomena have been observed for this very specific case. So we really believe it's a nice test bed to show how good your model or microphysics work. Here is the model configuration. We adapted a three nested domain setup. Just by looking to the grid numbers, it's a quite large effort to run. And the innermost domain cover centered at this radar site. And then we have more than 1,000 by 1,000 grid spacing for 1 kilometer. And here are the details for the configuration. In order to run this model over this very complex terrain region, we have to use a very tiny time step, 5/3 seconds for the innermost domain, so that we apparently have much finer time step for the other 2 larger coarser domain. This case, we use a GFS analysis. And then we just run three domains together using 72 vertical levels. And we have run this case from 06 UTC, 6 UTC on December 13th to spin the model up for about 15 hours. And then looking into the IOP periods of data for analysis. So only difference is that between the experiments is the microphysics option, either MP28 or 38. So the rest of the plots you are going to look at are from the results from the 1 kilometer domain. So let's just look at how the model, this is the maximum reflectivity or composite reflectivity from the model view. And they're exactly the same time period and every 30 minutes. And the letter C indicate the radar location. So by looking into this two different animation, first thing we noticed that the storm evolution looks very similar, timing-wise and size-wise. But if you pay attention to the circle area, that the MP30A actually produced a large area of very high reflectivity, but smaller area for moderate, kind of a yellowish color. So that is a difference that we notice. And then if you're looking into, I don't know why these two are not synchronized. It's weird. Let me go back and forth again. They're not synchronized anyhow. But this is just the vapor pass, so integrated vapor column vapor integration. So we notice for the Andes, the air is quite dry. There's basically very, very dry air actually interact with this very moist air in the plant. So there's definitely interactions of these two different air masses that kind of trigger convection somehow. So we hopefully next slide will show the same synchronized. Okay, and these storms basically have the similar behavior in terms of evolution, and then the liquid water pass that you saw between these two are very similar. So I won't. Maybe in, later in the simulation we saw more liquid in the MP38 run. And if we're looking into the ice water pass, now you realize when the storm started to develop and merge into a MCSs, we see much less integrated ice in the 38. So it could be that most of the ice being thawed out due to their higher density and terminal velocity. But this is a big difference, in my opinion, that between these two simulations. By the way, the red line indicated on this animation will be the cross-section you're seeing next slide. So that's a cross-section location, and we show on the top row the vertical velocity from the model, and second, this is the cloud water. Third panel indicated Graupohl mixing ratio, or not mixing ratio, the Graupohl water content, and then the last row is the rain content. So they are good, they're synchronized. So we now notice that these storms kind of develop even before they hitting the Cordoba mountain. And then it seems like MP38 actually have a slightly faster moving speed, even though our cross-section is not aligned with the development of the MCSs, but still in the same kind of the directions. So here we make another effort to make a difference between these two. Now you can see in the MP38, which is the one minus MP28, that we see extra higher vertical velocity positive or updrafts ahead of 28, and also more ice water content or Graupohl content in the MP38. That's indicating a stronger or faster moving speed of the storm. That kind of in contrast or contradict to what we found in previous work that Sarah's talk showed. And we then want to just double check if that's the case. And so we plot the differences of the T2 and surface temperature and the precipitation rate on the right-hand side to indicate that it seems to be the cold pool being strengthened in these MP38 simulation that move this line even faster than the MP28, so that in the precipitation rate, you see more reddish color further downwind, like right here. So everything in red and yellow indicating higher precipitation rate, and green means lower, which is a dislocation of your line from original place to even further downwind. So that contradicts to what we found from the Pecan and another case just shown in previous slide. And we then did a analysis on the size of the hail particle on the ground using the diagnostic value, the hail maximum K1, and the red outline on the left-hand side showing the area that we performed this analysis. So we want to see the downwind kind of the area of the storm, and also want to focus in the period of the strongest convection. So anything moving beyond this box actually are kind of outside of our IOP. So this indicate the MP38 does produce wider distribution of the maximum hails on the ground, and 28 produce much narrower distribution. So that's in agreement with the previous work. And I actually have done several other simulations using different configuration, even different PBL. And somehow we notice another thing is if you are looking into the area that's later in the life cycle of the storm, the maximum size distribution between 20 and 38 are much smaller. So they actually produce very similar distribution of those sizes. So here is my summary of these second episode of the talks. We successfully simulate this case. This is a quite large domain and area to simulate with 1 kilometer domain. And then comparing the result, we first want to make a comment that this MP38 requires a lot more memory compared to 28 option, probably due to much larger lookup tables and a lot of things that put into the scheme that have to change my job script to actually make it work. Because if I use the same configuration as my 28 run, the simulation will fail. So that's the interesting point I want to make. And the second, from second point up, we notice that we have observed larger area of high reflectivity and small area of moderate reflectivity from these 38 compared to 28, and also less totalized condensate in the storm simulated by 38 scheme. And next point, I said no obvious evidence of reduced strength of a cold pool is actually on the other hand, it's actually on the other side. It seems to be that in this case, MP38 enhanced the cold pool strength, which was not found in previous simulation. And then no obvious change in precipitation rate between 38 and 28 in this case. Finally, I think the common theme between the two works that is the spectrum of the largest size of hail on the ground is wider from the 38. So that's all I have, and thank you.
Thank you, Llewellyn, and for staying on time as well. Any questions from the crowd or online?
Everybody is ready.
Everybody's hungry. Well, I have one. I won't let you get away yet.
Okay.
So you made a comment at the end that later in the storm's life, the hail size differences. Is that a storm mode issue, or?
I haven't got a chance to look into the details, but it feels like, yeah, hard to say. It feels like when you develop on the initial stage of this convective storm, you can see those differences quite obviously. But later on, maybe there are more condensate start to build into the storm itself that's more efficient for those systems that produce very similar size distributions. So I cannot say for sure, but that's what I observed.
Other questions? Jason? Oh, does someone else have a hand? Nope. Oh, you go ahead and say something.
No, really nice talk. That third last bullet, no obvious evidence of reduced cold pool. Didn't you make the argument that one had an obviously stronger cold pool?
Yeah. So I should change that line saying for this case, actually MP38 induced stronger cold pool.
Okay, but you're basing that on that the precip rates are displaced?
No, it just yeah, maybe. Okay, that's true. You're right.
See, I think that for it to be a stronger cold pool, they have to not just be displaced, but they have to be increasing in size. And it doesn't look. It just looks like there was an initial displacement. See right there. Yeah.
Yeah, right there.
Maybe it is a bit. Maybe it is a bit, but
yeah, maybe only a certain period that increased the cold pool, and then it stays that way. You're right. You're right. You have to do a lot more analysis to really dig that out. But this is different than what we show in the previous talk. So I want to point that out. Thank you.
I think we've got a hand raised on the virtual side. Great. So for whoever that is, I can't see it right now, but feel free to jump in.
Yeah, this is Charles Jackson. So there was a pretty big impact of going from, between these two schemes, but yet the M38 doesn't go all the way. So I was wondering if doesn't that argue that you should just go to like a binned, like totally free ability to resolve all aspects? Because then you might get qualitatively even better results. I'm trying to understand like the implications of this is that you've made a big improvement, but yet it seems like you can go another leap.
Yeah, thank you very much for the comment. And I think we make this development based on the conceptual model. It's a better approach, and also in agreement with the paradigm shift that Hugh and Jason proposed to really looking into more kind of a prognostic density approach for these precipitation type. So we have that in mind and make this change, try to have a scheme available for more operational application in mind, so that when operation applications can actually do more tests and evaluation and see the application of it. But from the fundamental understanding point of view, I agree with you. Maybe the right or the best way to move forward is similar to the Hailcast, but now we're actually working with Kamal, Hugh, and Wojtek from MCube. We're trying to develop the full ice phase or mixed phase Lagrangian microphysical approach. So in that framework, everything evolved dynamically, and also we track them Lagrangianly. If you see a hail type of a precipitation on the ground, we can actually trace back his history in the cloud or even from the ground, so that we can really understand what this particle has experienced in the cloud and what actually happened to it to lead to this very specific features on the ground. So that's our goal, and we're actually developing that capability right away. Hopefully next workshop, we can report on that. So hopefully that's not overstate anything, Hugh. Hopefully that's fine with you. Okay, good. Thank you, Hugh. Yeah, thank you for the comment.
All right, anyone else? All right, well, let's thank all of our speakers again. Couple of very short announcements. Just a reminder, we do have the shuttle that's headed back to the Hyatt that'll leave here after dinner at 7:30. So please, if you can, join us for a reception and dinner. Also tomorrow morning, we have our shuttle running from the Hyatt over here that departs from the Hyatt lobby at about 7:30 tomorrow morning. I know that's early, but that's when our shuttle will head over here. So please, if you need a lift from that part of Boulder, please take advantage of that. Speakers, if you have not gotten your slides uploaded, please do, or see Shelly out front at the registration desk. She can help with that. Also, she will be around tomorrow to do the same. I need to practice what I'm preaching and do mine. I think that is it. And thanks again. What a good first day. We made it through the hiccups. I think all the virtual side worked really well. So let's give ourselves a round of applause and call it good for day one.